Hello, and welcome to the full course session on Multibody Dynamics for automotive applications using MotionView and MotionSolve, your gateway to mastering the simulation of complex mechanical systems in automotive engineering. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're committed to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on multi-body dynamics and other automotive applications. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll introduce you to the basics of multi-body dynamics. You'll learn about the importance of MBD in the industry, how it differs from finite element analysis, and the industries utilizing MBD. We'll also explore the evolution of MBD and the foundational force equations that drive multi-body simulations. In the second chapter, we'll focus on motion assemblies and interference checks. You'll learn how to assemble automotive motion systems and review or modify the kinematic and dynamic characteristics of these assemblies to ensure accurate simulations and performance analysis. In the third chapter, we'll explore how to simulate complex time-dependent dynamic systems. Using the example of a compound pendulum, one of the most chaotic systems in mechanical dynamics, you'll learn how to accurately predict the location, velocity, and dynamic forces on frames and joints over time. In the fourth chapter, we'll dive into model building with a simple crank mechanism. You'll learn how to create and organize parts, connect them using joints such as hinges, sliders, and couplers, and simulate the system. This chapter will also cover practical exercises like building and simulating a simple pendulum model, incorporating complex motions and transient force profiles into your system. In the fifth chapter, we'll introduce you to flexible bodies. You'll learn the technical aspects of flexible body generation and how to perform static ride analysis for an automobile's lower control arm. We'll show you how to capture stress and strain contours on flexible components, an essential aspect of real-world automotive simulations. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with multi-body dynamics for automotive applications using MotionView and MotionSolve.
Hey everyone, hope you're doing good. To get the student edition of HyperWorks and its products, open Google and type in HyperWorks student edition and hit enter. Click on the first link that appears in the Google search and hit the download now button. You will be directed to a page where you need to fill in all the details to request for the student edition. If you are a student, you can fill all the details here, and in case if you don't have a university given email address, you can use your personal email ID. For the Ethernet host ID, click on the link here and execute the file that is downloaded. You will have the Ethernet host ID of your device, copy it and paste it in the column given. Now approve the terms and conditions and click apply. Now if you are a working professional, follow the similar steps, and for the email address, fill in with your personal email ID and proceed. After requesting for the student edition, you need to wait for 2 to 3 days until Altair sends you an email regarding the request approval. Meanwhile, you would have received an email from our side to fill in the details. If you are a student, click on the student tab and fill in all these details which has been asked. And in case if you are a working professional, you click on this non-student general tab and fill in all these details. Once you receive the license email from Altair, you may follow the steps in the email to proceed with the installation. Thank you guys, and hope to see you in the next video. Bye.
Hey guys, this is Sarang from Skill-Lync, and I wanted to make a quick announcement regarding Altair licensing. The license process typically takes 1 to 2 weeks to complete, so make sure that you request for a license as soon as possible. The exact instructions that you need to follow are provided in the next video. Now, one thing that I want you to remember is, if you don't follow that process correctly, there will be a delay in your license processing, which means you won't be able to practice any of the simulations that the instructor is demonstrating. All right, so I hope this makes sense and you fill in the license request quickly. Thank you so much. Bye.
So guys, in this video what we'll be seeing is how to install Altair HyperWorks in your desktop. So in the previous video you would have seen like how to apply for license for in the Altair. Like Altair gives us trial versions for 1 year time in HyperWorks software. So after applying for license, after 48 to 76 hours, this is going to be the email from Altair after approving the license request. So they would have attached the DAT file at the bottom, and they would have given links to download the setup files. Okay, so this is how Altair mail looks like. So you can see like the installation package is being bundled. So if you click anything, the installation package for all these softwares will be given. So yeah, let me click on that, and yeah, you can see that it is started download. So I've cancelled it because I've already downloaded the license file and the setup file. So let us just open that setup now. Clicking on that setup. Yeah, click on S. So since it is a big software, it might take some time to install. Okay. So the installation is finished. So this is a general setup for Altair HyperWorks. Click on your OK. Now it will just run those pre-works and all before entering the setup. So yeah, accept the license file. In terms of agreement, click on next and make sure that it is going to be the C folder program files. Okay. And yeah, if you want your desktop shortcuts, then click on yes, or else yeah, it's up to you. And yeah, it will start install. Okay, let us begin the installation. So it has been installed, the setup has been done 100%. So now it will be zipping the files required and it will be expanding it. Okay. So yeah, the installation has been done. So click on done. Now what you should do is go for the setup file over here. That is on the C drive. So you go for program files and click on Altair. So this has in this folder. In this folder, what you should do is go for downloads. Copy that license file which you have downloaded earlier. So yeah, copy that, and yes, you can paste it over here so that the software opens. Click on continue. So click on search for HyperWorks Student Edition, the 2017 version, and I think you can see like, yeah, click on yes. Okay, and it has been given over here so that you can just vary it over here. See over here, advanced pre or post processing, hyper mesh. You can just switch it between. So this is how you will be installing HyperWorks, and thank you guys.
Welcome back. So this is your MotionView graphical user interface, and we will continue with the demo on exercise 1. In this exercise, you will learn to open and save HyperWorks desktop session, switch between different HyperWorks clients, manipulate the appearance and orientation of animations and plots, create and modify HyperWorks desktop windows, open and save a model in MotionView, navigate through the project browser, and also select and modify a MotionView entity. So let's go to the File option in the main menu, and then go to the Open option, and then click on Session. So all the model files, they are organized the chapter wise in this particular folder. So you can go to chapter 1, okay, and then click on this particular session file that's already been created. Indie Full New, and then click on Open. So when you open the file, you can see the session file that's created. So it is the MotionView model that's already been built, and these windows that you can see is basically Altair's post-processing software. Hypergraph is used to plot, and HyperView is used for animations. Here we have this particular toolbar, which is a client-specific toolbar. This is the play button, and these are the animation controls. So you can play and pause using this button. So this is for fast forwarding it, going back, and this bar can be used to adjust the frame rate to increase the speed of the simulation or decrease the speed of the simulation. And as you're seeing, all the windows are synchronized, so you can take a look at the animation. So this is in Hypergraph and this is in HyperView. So the full page here is divided into 6 windows. Okay, so we basically choosing this option, and we'll be basically dividing one single page into 6 windows, which will have different post-processing results. So let's experiment with a few things here. So as I mentioned, this is for the animation control, and now we can go to, you can see this blue color highlighting line when I click on this window. Okay, so this particular thing calculates the CG acceleration with respect to the center of gravity for this particular model. So what we can do is we can go to this option here, or we can click on this particular window and then click on this option. This is for expanding or reducing. The window. If you click on this option, we can expand that particular window in one page, and if you click the same option, it goes back to its previous state. And then this option is basically to swap the windows. If you click on this option, and if we move the first window to the last window, this gets swapped here, and we can swap it back. So this is used for swapping the windows, and this one is for synchronizing the results that's being played in the different windows. So now they're already synchronized. All these windows are already synchronized here, and you can click on this. So here I'm holding the control key on my keyboard, and I'm using the left mouse button to rotate it. Okay, and for panning we have to use the right mouse button along with the control key pressed on the keyboard. And this is for zooming in and zooming out, wherein we basically hold the control key on the keyboard and use our scroll button on my mouse for zooming in and zooming out. So these are some basic controls that you have to know when you're navigating through your model. So now let's switch between the different HyperWorks applications. So this is the icon that you see for HyperView. As I mentioned, this is for looking at the animations. So we have this drop down arrow here. We can click on that, and we can switch between the various applications. So we can go back to MotionView. So in this window we had HyperView, and now it's switched back to MotionView. Okay. So all this is possible. So now let me just go ahead and create a new session. File, new session. So this erases the previous session that's there on the screen right now. Say yes. So this is your fresh new session. And now here, let's open the model. Go to File, Open, and last time we had selected Session, so it opened a .mvw file, but now we'll be opening a model. So let's go to Chapter 1, and in Chapter 1, we'll be selecting the single cylinder engine model. A very simple basic model, which has already been built. So let's review this model. So this model, it has 6 bodies. The ground body is always created by default whenever you open a MotionView window or when you start the software, the ground body is always created by default. Along with that, we have the crankshaft. So what happens is, first you need to create the body, and then you have to create the graphic and associate the graphic with the body. So this is the crankshaft, and then we have the connecting rod here. We have the piston, which is inside this gray stuff that you can see on the screen, and the pin is the blue part, and we have the outer cylinder. Okay. So these are different bodies which are used to create this model, and the graphics that are used, we're using all these are the primitive graphics which are available in MotionView. So we're using a cylinder for crankshaft, cylinder again here for the crankshaft. This part, this highlighted part that you can see is also part of the crankshaft, which is modeled using the cylinder. Same thing even here. So the whole crankshaft is modeled using 4 cylinders. Cylinder 1, 2, 3, 4. And then we have the connecting rod here, again which is modeled using a cylinder. We have the second part of the connecting rod, which is again modeled using cylinder. The piston, the gray part which is inside, modeled using the cylinder. This is the engine cylinder, and the pin again, which is modeled using the cylinder. So all these parts that you are seeing on the screen are modeled using just one graphic, one type of graphic, that is cylinders. Okay, and we have 6 joints in this model. So if you click on this, you can get to know that we have a joint here. You're not able to see it because the whole model is opaque. So let's go to the graphics option here, and then we can select all. So this selects the full model, and you can make it transparent. So now you can see the various joints here. Okay. So this is your first joint, which is the cylinder pin joint to the connecting rod. So it's basically a ball joint that we have here. And then we have a fixed joint between the pin to the piston. We have a fixed joint. And then we have a revolute joint here between the crankshaft and the connecting rod. We have another revolute joint here between the crankshaft and the ground body. And we have the cylinder, and we have a cylindrical joint between the piston and the cylinder. Okay, this particular joint that you can see. And we also have a fixed joint between the cylinder and the ground. So this is how the model looks like, and this global frame marker is created by default when you open a new MotionView window. And there is one motion that's applied on the crankshaft for the crankshaft rotation. So you can either define a motion on a joint, or it can be using markers, but here it's defined about this particular revolute joint. Okay, and they're requesting 2 outputs to measure the displacement, to measure the piston motion. So the displacement output, and for the crankshaft rotation we have the velocity output. So we are requesting these 2 outputs. Okay, so now we've finished exploring the model. So now let's open the motion folder and click on this crankshaft rotation. It highlights this motion, and if we go to the connectivity tab, it will show that it is 1. So, and by default it is in radians per second. So 1 radians per second motion has been applied on this particular revolute joint. So it is going to rotate this crankshaft at 1 radians per second. So let's see that. Go to run option and then click on run. You can leave the simulation settings as it is by default, and then you can run. So the model is run. You can click on close and click on the animate window and click on the animate button, so that it divides the page into two windows, and the right side is now the HyperView window and the left side is the MotionView window. So now you can click on play, and you can see that the crankshaft, it rotates at 1 radians per second. Here you can just see it rotating, but you can't see the actual value. So to see that, we need to plot the graph. So for that, we need to go ahead and use the Altair's post-processing software, HyperGraph, for plotting the results. So let's go back to MotionView and click on plot. So if you click on animate, it automatically brings up HyperView, which is Altair's post-processing software for animation. And if you click on plot, it is gonna bring up HyperView, which is used for plotting. Okay, so it divides the screen now into 3 windows, and it brings up the HyperView window here. So you can go to marker velocity and then click on the crankshaft rotation, and then it is in the X direction. So the Vx, Vy, Vz is basically the XYZ component in the linear, it's the velocity in the X direction, Y direction, or the Z direction. But now it's rotation, so we need to select either WX, WY, or WZ. And we can see from the screen that here it is oriented along the global reference frame, and this will be the rotation about the X axis. So let us select WX and say apply. And you can see that it is at 1 radians per second, and both these are synced with each other, so it is moving at, or it is rotating at 1 radians per second, right? Okay, now what we'll do is we'll come back to this our MotionView model and make it and enlarge it. Once we enlarge it, we will do a slight modification. We'll go to the motion here and we'll change the value from 1 radians per second to 10 radians per second. Okay, and now we'll run the model. So go to the run option here, and then now save it with a different name. Okay, we'll save it as single cylinder engine model underscore 10 radians per second, and click on save, and then click on run. Okay, now let's go to the animate option to bring up HyperView, and you can see that the crankshaft is rotating faster and at 10 radians per second. So to go to the plotting, we can just go back. Okay, we can go back here and go to plot. So this is the fresh plot window. So let's go to the marker displacement and go to piston motion here, and then select let's go to marker velocity option here and go to crankshaft rotation and select the WX for the rotation along X axis and click on apply. You can see that now it is at 10 radians per second. So you can see these peaks like this only because that's the disturbance in the model. Don't worry about this, but you can see that the value in the y-axis is all 10 and it is at constant 10 radians per second. So this brings us to the end of the exercise demo on chapter 1. Thank you. Now let's continue with the demo on exercise 2. We will cover the following topics in this demo: building the rigid bodies, simulating via the run panel, basic post-processing using HyperGraph 2D. So this is your MotionView graphical user interface. The first thing to create is a simple rigid body, which will fall under the influence of gravity. So to create a rigid body, we go to this particular icon on the client specific toolbar and right click on it. So the body or the body pair dialog box opens up. So here we have the label name, which can be changed anytime during the model building process, but the variable name cannot be changed during the model building process. So we can change it only at the time of creation of an entity. And here we can either select a single or the pair body type. So first, start off by giving meaningful names to your model or the modeling entities. So here we are creating a free body. So let's rename the body as free body. And we can give a variable name, free body. And one more thing which you'll have to make note of is for the label name, we can have spaces. But for the variable name, we need to separate it by these underscores, and there should be no spaces given in the variable name. Okay, so once this is done, say OK, and a free body is created. You can see even in the model browser that it gets populated with this free body that you just created. So a body will always have mass and inertia. And since it's a free body, it can have any mass and any inertia properties. This is the panel, the body panel. So let's go to the properties tab here and enter some random values for its mass and inertia values. So 1 kg. And here we can just give some random number. So anyway, we're going to make it the free falling of a stone. So a stone can have any mass or inertia property. So we're just giving these two values. And if you just give it along the diagonal matrix, that's sufficient. That is, if you just give Ixx, Iyy, Izz, that's sufficient. Now you can go to the center of mass coordinates. Here you can basically check this box which says use the center of mass coordinate system. And here you need to orientation for your body that you've created. Okay, so you can go to the point here, and in point you can select the global origin. As I mentioned in my previous presentation, the global origin is created by default, so which will be at 0, 0, 0. So you can create this free body at 0, 0, 0. So it will be at the global origin. So previously this particular option here was unresolved, and now you can see that it is, after selecting this option, this body, which is the free body, is oriented at the global origin. So, and by default, the gravity is on. So you can just check that. You can expand this folder and also expand its subfolder, which is forms. And if you click on gravity, you can see that the gravity effect is on. Now let's go to the run panel and we'll give a name for this. So let's say this in chapter 2. We'll call this free body. Save. Okay. So here the simulation time, we can just give it as 1 second, and you can hit on run to run the simulation. Okay, so the simulation is done. Now the body is expected to fall through space. Okay, now let's plot the results to confirm the behavior. So let's go to plot. So this divides page into two windows. The left window here being MotionView, and the right window is the post-processing software of Altair HyperWorks, which is Hypergraph. So here we can do the plotting. First we need to pick up the file, so we can go to this data file option, and the plots will be stored in this file extension using .abf. Okay, you can select this particular file, say open, and the Y type here you can measure body, because you want to measure the displacement of the body with respect to the ground, right? The displacement of the stone with respect to the ground. So you select the free body here. Okay, and the height is basically, because it's at the global origin, the height is basically the z-axis. So the y component is going to be z. And if you hit apply, you can see this. So these results of the type body are with respect to the local body reference frame. Okay, this will be described in detail in the upcoming chapters. Okay, you can see this plot. So this is free falling of the body in space. And this is your time in the x-axis, and this is the displacement in the y-axis. So we completed the chapter 2 demo. So we'll go back to the MotionView window and we'll just save this model as free body completed. Hit on save. So I also want to explain about one more important thing here about saving a model. What's the difference between saving a model and saving a session? So right now what you have on your screen is a session, because here we have the model and on the right hand side we have its results. Okay, so together it's called a session, wherein you have the model file as well as you have your results file. So if you want your colleague, or if you want someone else, or if you yourself want to view your session file again, in the sense if you want to view both the model as well as the results in one single file, then you need to save it as session file. So we need to go to file and go to save as and then click on session. So if you save it as a session file, you can see that we saved using the .mvw extension. So if you save it in this particular file format, once you open a new MotionView window and you basically open a session, exactly it will open it up in exactly the same way, wherein you have your free body on the left hand side, the model file on the left hand side in MotionView, and the right hand side will be your the results that you've got after post processing. Okay, but if you save it as a model file, then you just get your MotionView model file. There will be no results that will be attached to it. Okay, so that's the difference between a model file and a session file. A model file just has the model which is present in MotionView that will be saved, and if you save it as a session file, it will be saved along with its results also. So now I just saved this as a model file because I don't want the results. I just want to save this free body, so I just saved it as a model file. So I hope it's clear for everyone. So this completes the demo on chapter 2. Thank you. Welcome to the third chapter of Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. Today, I will be teaching chapter 3, which will cover the topics on points, expressions, and geometry. Points are also referred to as hard points in the MBD world. They are one of the most fundamental construction elements for MBD built in MotionView. Almost all the entities that are created in MotionView need to be referenced using these hard points for defining their location. There are two types of entities in MotionView. They are design time entities and runtime entities. Points fall under the category of design time entities. You will not find points in a MotionSolve model, that is, nothing but the input deck, since their purpose is only to help create other entities for MotionSolve. There are three types of points. They are the single point, a symmetric pair point, and symmetric pair point, and symmetric pair point. Now let's understand each of them in detail. By default, point pairs are always symmetric, and the left side is the master. For symmetric pairs, the changes made on the left side will automatically reflect on the corresponding right side, and vice versa. This helps in building suspension models, for example, where the left control arm is symmetric to the right control arm. The pair entities help in creating models which are symmetric about the ZX plane of the model. Their properties can also be symmetric about the ZX plane. That is, the y property is mirror. In case you need to assign different properties for the left side and the right hand side, then you can turn off the symmetry by unchecking the symmetric checkbox on the properties tab. I will show that to you in the graphical user interface in a while. Now let's move on to the methods used in creating points. I had already mentioned regarding this in my previous lecture. MotionView allows us to create points in three ways. The first way is to go to the model browser and then go to the add option and then click on the reference entity and then click on point. This is your MotionView GUI. So the different ways of adding a point is basically going to the model browser, right clicking on the model, going to the add option, and then under the add option you can go to the reference entity and then select the point. This is the lengthy procedure, but it's a good method for the beginners because they will know what this entity falls under, whether it's a reference entity, constraint entity, etc. Okay, and the second method to add point is basically right click on the existing point or the points folder and just select add point. And the third and the most easiest method is to right click on the icon which is present on the client specific toolbar and then say OK. So a point gets created. So these are three different ways of adding points. And when you add a point, so you need to give its label name, its variable name, similar to what we created in bodies, and we also have to define its type, whether it's a single point or whether it is a pair point. So if you go ahead and create a pair point, then you can see that in the points panel you have the left hand side and the right hand side tab. And if you want symmetric properties, then you can leave this checkbox as it is, and if you want asymmetric properties, then you can uncheck this. Okay, and then you get a warning message asking, so do you want it to have asymmetric properties? If you want to have that, then you can just say retain. Otherwise, you can just go ahead and click this box if you want to have symmetric properties for these pair points. Okay, I hope it's clear. And by default, as I mentioned, the left hand side is the master and the right hand side follows whatever properties you give for the left hand side. But you can also change that by swapping the tab to the right hand side if you want to make the right hand side as the master. Okay, I hope it's clear. Let's go back to the presentation. Now let's understand the methods used in editing points. Points can be edited in the points panel or they can be edited by using the data summary. So what I mean by edited is entering the values for the x, y and z coordinates. And in the points panel we have one more option, which is basically the measure tab. It can be used to measure the distance between the 2 points. So I will show how we can edit points using both the options. Using the XYZ coordinates in the points panel or by going to the data summary option and then changing the XYZ coordinates there for all the points altogether. Okay, so I'll show that to you in the graphical user interface. So we've already created points 0, 1, 2, 3. Okay, so what you can do is you can either go to each of these points here and give the coordinate values. Okay, or you can just click on the data summary here and it brings up this particular dialog box wherein you can directly change the values of all the hard points that you've created all at the same time. We can follow either of the ways. Let's go back to the presentation. So this is what I'm showing here as a screenshot, and the easiest way to go to the data summary dialog box is just by clicking on this option which is there on the points panel, and the other way to do so, you can also go to the data summary by using the model option in the menu bar. Okay, there is also another option in MotionView to select a point coordinates from the node of a graphic that exists in the model. And here it should be noted that the file should be in the .h3d format. I will explain about this file format in detail in the upcoming lectures. Now let's move on to another important method of creating points in MotionView, that is by using the point macro creation option. This option can be accessed by clicking the macros option on the toolbar and then going to create points. And this option is also found in the client specific toolbar. I'll show this to you in the graphical user interface so that it is more clear. So the first way of creating a macro is by clicking on macro option here in the file menu and then going to create points. So here you can create points using coordinates. This is the first option. Okay. And here you can also choose the coordinate. Either you want the Cartesian coordinate, that is by default, or you can go to the cylindrical coordinate and you can give the values for this. So this is one way. The second way of creating the macro is by using the client specific toolbar. So this brings up the same dialog box. And there are 3 different ways to create these point macros. So if you go to the macros option either here, it will give you like basically 4 different ways. So basically there are 4 different ways to create these point macros. The first one is using coordinates. Second option is along a vector. The third option is along a curve. And the fourth option is at the center of an arc. So you can create the points along all these 4 options. So say you want to create a point along a vector, then you need to specify the first starting node, say point 0, say OK, and then you need to give the ending node, which is say point 2. And also you can also specify the number of points that you need between point 0 and point 2, say 3. So if you click create, you can see that between point 0, which is this point, and point 2, which is this point, we have point 3, 4 and 5 which are created and which are equidistant from each other. So this is the power of macros. Okay, so this is along a vector. Similarly, you can do it along a curve by switching the radio button from points equally spaced along a vector to create points equally spaced along a curve. And if you want it at the center of a circle or an arc, you can go to the third radio button and you can give the corresponding options and you will get a point at the center of an arc or a circle. So these are the different macros, point creation macros that are available in MotionView for the easy model building process. So I'll just open a new session. Let's go back to the presentation. So the same thing has been explained in the presentation as well. So this is basically the point along a vector. This is creating the points along a curve. And this is creating a point at the center of a circle or an arc. Okay. Now let's move on to one of the most important topics in MBD, which is parameterization. And we need expressions if we want to parameterize one particular entity with respect to another. So here the coordinates of the points can be entered as numbers or expressions on the property tab. Once the value is entered, it basically, and it is parameterized, you can get to know a particular value is parameterized if it is highlighted in blue color, as shown in this slide. So I will take you back to the MotionView graphical user interface and I will show you the power of parameterization and how to parameterize one point with respect to another. To make it more clear, so this is your MotionView graphical user interface. So here I want to create a point called point A, add a point. So I call this point A and I want it to be a single point. Okay, so that's created and I will leave it at the global origin 0, 0, 0. Then I go ahead and I create a second point B. Again, I want a single point, say OK. So now I'll use parameterization to parameterize point B with respect to A. So what happens is, say for some reason you moved A, and if B is connected to A, point B will also move with respect to A. And if you don't parameterize, then you will have to do more work, wherein you'll have to give separate hard point values for point A, and then to move point B, you need to again go ahead and give separate hard point values for point B. So I'll show that to you in a while. So how to connect this point B to point A? And say point B, I want it to be at 10 units in the X direction, 0 in the Y direction, and 10 units in the Z direction with respect to point A. Okay. So what I'll do is, I am now giving the coordinate values for the point B. So I'll place my cursor here and I'll click on this FX option. Okay, so this is nothing but the function builder option and it will open the function or the expression builder dialog box. So here you can delete this. So now what I'm trying to do is trying to relate or trying to create a relationship between point B and point A with respect to point A. Okay, so I will expand under points folder, I will expand point A and I will select the X value of point A. So this is selected, P of A dot X. So this means the X value of point A and I'll click on add. So the X value of point A is selected and I want point B's X value to be 10 more than point A's X value, which is nothing but 0. So this plus 10 and I hit enter. So then to see if this expression is evaluated or whether MotionSolve has understood it properly or not, you can just click on evaluated and it will give you the number. So now it's making sense, right? So it has taken the correct value. So then click on OK. Now you can see that this box is highlighted in blue, which means that the X value of point B is now connected to the x value of point A. So if point A, which is now at 0, moves by 10 units, then point B will also move by 10 units and this value will become 20 automatically. Okay, I'll show that to you once I create the relationship between even the y and the z coordinates. Now I want the y value also to be connected to the y value of point A. So I go to the y box here and click on the expression builder. So here I delete this, then go to points, point A. In that I select its y value. So and then I hit on add. So here I'm selecting the y value of point A. So as I mentioned earlier, I want the y value of point B, I want it to be at 0. That is exactly where point A's y value is. So I'll just leave it as it is. If I say evaluated, it should be 0. And then I say OK. Now what I do is I'll go to the z value, go to the expression builder. Here I will again go to the points option, point A. I'll select the z value and say add. So this I will be adding plus 10 because I want the z coordinate of point B to be 10 more than the z coordinate of point A. So it will be 0 plus 10, which is 10, and say OK. So you can see that the point B's x, y, z coordinates are now in relationship with point A's x, y, z coordinates. Okay. So now what happens is, if you move point A by 10 units in all the three coordinates, what do you expect to see in B? You see 20, 10, 20 from 10, 0, 10. Okay, so this is how you relate one point to another with the help of parametric expressions. So I hope it's clear to everyone. So here in the presentation, I'm just giving a different example. So it's the same thing what I showed to you in the graphical user interface, but I took a different example there. But here, whatever I've given here is a different example. Okay, but it's the same thing. So the MotionView graphics can be broadly categorized into three types. So that is the implicit graphics, the primitive graphics, and the external graphics. So the implicit graphics are the small icons that you see in MotionView, like when you create points, bodies, joints, you can see some graphics. So those are called the implicit graphics. They are just provided for the guidance during model building process and are not visible when you're animating it. The primitive graphics. So these graphics, they help in better visualization of the model and are also visible in the animation. So there are some primitive graphics which are readily available in MotionView, and they include the cylinder, box, sphere, etc. So we'll all be dealing with the primitive graphics in this chapter. And then we have the external graphics. So MotionView has this CAD import utility wherein we can import CAD formats or even the hypermesh files into MotionView. So it's called the import CAD or FE option. So here we can import any file that is from CATIA, SolidWorks, HyperMesh, etc. So I'll show you the list in the upcoming lectures. So this is an example to create a graphic. Again, it's the same manner. There are three options of creating a graphic. You can go to the model browser, right click, go to the add option, and you can go to the reference entity, and under reference entity we have the graphic option. So this is one way of adding the graphic, and the other way of adding graphic is just right clicking on the graphic folder if there is a pre-existing graphic, and then say add graphic, and you can select any type of graphic that you want to add from the drop down list. And the third way of adding a graphic is directly from this client specific toolbar. Right click on the graphic and then you go ahead and add. So these are the different ways of adding graphic or any entity into MotionView. And so once you add a graphic, you can see that this particular panel is created. Okay, so this is the graphic panel. So here you need to give three different options. That is, you need to specify 3 different options. That is, in the body option, you need to associate the graphic to a particular body. So here we just have the ground body which is created by default. So say we are associating the cylinder that we have created with this ground body. Okay. And then we also need to specify the origin at which the graphic has to be placed. So here we can place it at global origin, point A or point B, anything. And then we also need to give, because it's a cylinder, so this will be its starting point, and the direction here we need to give the ending point. So you can go to the point and you can say point P. So you can see that the graphic is created. And always use this option to fit to screen. Okay, or the shortcut is just click on this graphic window and press F key on your keyboard so it fits the model to screen. And we can go to properties tab here and you can change the properties. Say you want to give 2 mm as a radius. And here also you can see that the radius 2 is parametrically connected to radius 1. Okay. If you just click on that, you can see that. So if radius 1 changes, radius 2 will also change automatically. So if you don't want that, say if you want a cone wherein you want the radius 1 to be different from radius 2, you can just click on this and remove its parametricity. Okay. So now you can see that after removing the parametric relationship, so you can see that these two are totally different now. The radius 1 is different when compared to the radius 2. Okay. So that is what I am trying to explain in these slides. And one thing what I forgot to mention is regarding the inertia properties. So, and also the visualization tab. So here, if you go to the graphical user interface in the next tab, we have the inertia properties. So we can also give the inertia properties. Okay. And if you go to the visualization tab, we can select this particular graphic and give a different color. Okay. Give a different material. You can just select mesh to make it look like a meshed model, and you can make it opaque or you can make it shaded. So you can play around with the appearance of this particular geometry that you create, the primitive geometry. Now it's time to go ahead with the demo exercise. Now we'll continue with the demo exercise on chapter 3. Here you will build on the free body model you created in the previous exercise. Here we'll be creating the points and the geometry, and then we'll be simulating and animating the results. Okay, so let's open our previous model. So the free body completed. So we can open that. Okay, so we got a free body. Now let's create a point 0 at the location 0, 0, 0. So let's go to this particular option on the client specific toolbar. We'll leave it as it is, point 0, and let the coordinates be at 0, 0, 0. And now let's create another point, which is point 1, and the coordinates for this, let's give it as 10 in the x-axis, y in the 0 axis, and 10 in the z-axis. Press enter. The points are created, but you're still not able to see anything on the graphic window. So just click on the graphic window and press F key on your keyboard and you can see the points. So the point 0 is at the global origin where the free body is there, and this is point 1. Okay. So now it's time to create the graphics. So go to the graphic option on your MotionView graphical user interface. Right click on this and we can leave the names default right now. Okay, and then it's a cylinder that we want. So by default it will be cylinder, and we can change it to any option that's in this drop down menu. But for now we just want a cylinder, so keep it as it is and press OK. Okay, so first we can go to the connectivity tab. So in the connectivity tab, we need to provide this information in order to see the graphic. So here, under the parent option, and in the body collector, you can click on this and select the free body. This means that you're associating the graphic that you're going to create, the cylinder, with this free body. Say OK. And the origin point, you can give it as point 0, which is at the global origin. So it starts from this, the cylinder radius 1 starts from this point and it continues up till point 1. So you got a huge cylinder, so just fit to screen. I think this is of radius 10, so let's give a lower radius. By default you get a cylinder of radius 10, so let's just decrease it to 1 mm. Okay, so now you have the cylinder. So now we can click on the graphic attributes and click on this particular graphic, which is a cylinder, and make it transparent. Okay, to see what will happen in the next steps. Now what I'll be doing is I'll be selecting this free body from the model browser, which is this. Now I will select get the properties from the associated graphic. So remember, for the free body we had given random mass and inertia properties, right? So now when I click on this option, when I check this option, the center of mass, it moves to the center of mass of the body, okay? And also it gets the properties from this associated graphics. So it gets meaningful mass and inertia properties now. So it has this value for the mass and these values for the inertia. So once this is done, I can now run the simulation. So in the previous demo, there was no graphic that was created. There was just a free body which was created and we could just plot the results to see that yes, the body is free falling. But now we have a graphic associated with the body and we can visually see in the animation the cylinder just falling down with the effect of gravity. Okay, so now the simulation is run. You can click on close and click on animate to bring up HyperView, which is the post-processing tool for Altair HyperWorks to see the animations. Okay, now just click on play. Can you see that? The cylinder just falling off the screen under the effect of gravity. Now you can pause this, okay, and this is where you can control the frame rate or the speed of your simulation. Okay, so now to make sure that we get the same plot, let's go back and click on plot. So it will be now divided into 3 windows and you get hypergraph in this section. So now click on body and it's the free body. So and we want its displacement along the z-axis. Say apply and you can see the same curve. Okay, the x-axis is the time, y-axis is the displacement, and you can see the free body falling from free space. So this concludes the exercise demo on chapter 3. Thank you. Welcome to the 4th chapter on Multibody Dynamics using Altair HyperWorks, MotionView, MotionSolve. In this chapter, you will continue to build on the free body model from the previous chapter. We will assign initial conditions, that is, velocity to the body. We'll create an output for specific measurements of interest. We'll also learn about the coordinate systems and the markers. And we will also simulate and plot the results. So in the body panel, and if we go to the initial conditions tab, it will allow us to define the initial conditions of the body. If we put a check mark on any of these boxes, we can turn on the initial conditions of the body. The initial conditions of the body pairs are made symmetric by activating the symmetric properties button. So we use Vx, Vy or Vz to set the initial conditions for the translational velocity. We use Wx, Wy and Wz to set the initial conditions for rotational velocity. We use VM to make the marker to specify the direction of the translational velocity initial conditions. We use VM to set the marker to be used to specify the direction of the translational velocity initial conditions. And we use the marker WM to specify the direction of the rotational velocity initial conditions. Now let's move on to one of the most important topics in MBD, which is markers and coordinate systems. So in the FEA world, we refer to the markers as systems, and in MBD, we refer to the coordinate systems as markers. So markers are nothing but coordinate system, which is used to uniquely measure the position of a geometric element. MotionView uses a Cartesian coordinate system. A marker is nothing but a coordinate system that is attached or fixed to a body. So we have different types of coordinate systems in MotionView. They are the global coordinate system and the local coordinate system. So this local coordinate system is again divided into two parts, that is the body coordinate system and the different markers. So now let's talk about the markers. So markers come under the reference entity, just like the points, graphics, bodies, etc. So I would like to discuss some key points on markers. Markers play a very important role for defining the local part reference frame for the rigid bodies, flexible bodies, and the point masses. They are also useful in specifying the connections in the constrained elements such as joints and motions. Markers also help in specifying the connections in the force elements. They act as reference coordinate systems for reference curves, reference surface, and post graphic. Markers are also useful for defining output channels for the measurement of displacements, velocity, and acceleration. So, if we have a body with marker M and we have another body with marker N, then if the body A's or body M's displacement has to be measured with body N, then it will be measured with respect to these two markers as shown in the figure. Hence, markers play a very important role in MBD. Now coming to the creation of markers in MotionView. So markers can be divided into two types: the implicit markers and the explicit markers. Implicit markers. Some markers are created implicitly when creating another body, such as bodies, joints, etc. They get created automatically. Implicit markers are quite useful for the measurements and the force definitions. Explicit markers are the markers which can be explicitly created in the marker panel. It can be created in the same way like how you create a point or a body, either by going to the model browser, right clicking, going to add, and then the reference entity, and then you can click on markers. And the second option is to right click on the marker folder in the model browser and just say add marker. And the third option is to select the marker from the client specific toolbar. So I'll show that to you in the graphical user interface. So the first option is to go to model, right click, go to add, and then go to reference entity and click on marker. This is one way of creating it. The second way is to click on either the folder or any of the pre-existing markers and then say add marker. This is the second way of creating it, and the easiest way is to just click on this option on the client specific toolbar and say OK. So when you add a marker, you get this following panel. This is the marker panel. So it requires a body on which the marker is fixed, the location for the marker, and also the orientation. So these three are the key points which are required when you create a marker. So if I go to the graphical user interface, so this is what I see. So I created here three markers. So I need to basically select its parent body. So right now by default we just have the ground body. Say OK. And by default we just have the global origin. So it gets created, and we should also define its axis. So its axis can be at a point, it can be along a vector, or it can be along this component. So these three entities have to be defined when you add a marker. So now moving on to the next slide, which deals with the markers in the body panel. So the body panel in MotionView will create markers for the body based on the data specified in the panels. So these markers will be implicit markers, which means that they'll be created automatically. So we have the center of mass marker, which is also called as the CM marker. We have the inertia marker or the inertia coordinate system marker, and then we have the body coordinate system marker. Now let's see what these mean in detail. Center of mass marker. Only the location of the marker is used for the center of mass. Orientation is important if the inertia marker is defaulted to the center of mass. So here the location is of utmost importance. If you put a check mark in this dialog box, then the location of the marker becomes very important, but the orientation also becomes important if the inertia coordinate system is defaulted to the center of mass coordinate system. If the center of mass coordinates are not specified, then the center of mass coordinates of the body will be default to the global coordinate system. Inertia marker. The inertia properties of the body are defined relative to the inertia coordinate system. If the inertia coordinate system is not defined, MotionView uses the center of mass marker by default. And the reason is that the moment of inertia is a function of mass and the distance of the mass as measured from the particular axis, which is why the orientation of the marker is very critical for the definition of inertia. Body coordinate system. So this defines the local part reference frame or the local reference frame for the body. This is used by the MotionSolve to compute the position as well as the orientation of the body. So please note that Adams, which is another Multibody Dynamics software, it defines all the markers associated with the body with respect to the local part reference frame, that is nothing but the body coordinate system, whereas MotionSolve defines all the markers with regard to the global coordinate system. So this is the main difference between MotionSolve and Adams solver. So now let's just summarize the importance of marker. So the marker is basically the coordinate system that is fixed on a body. It's often created automatically. They are nothing but the implicit markers. Next point is every part has one to define reference for mass, inertia, etc. And the markers are also used by other entities like joints, forces, outputs, etc. Now move on to our next topic, outputs. So you can create outputs in MotionView in the same ways you created bodies, points, markers, etc. The outputs panel allows you to define what information is to be placed in the output file when the simulation is run. It's basically the user's request. What results we want to see once we run the analysis. That is defined by these outputs. There are basically 6 types of outputs that are available in MotionView. They are displacement, velocity, acceleration, force, expressions, and then the user-defined outputs. So I'll show this to you in the graphical user interface. So there are 3 ways of adding the outputs. You can go to the model, right click, go to add, you can go to reference entity and see that you don't have any outputs here. So where can you find outputs? You need to go to the general MDL entity. So that's the reason you need to know all the 3 ways of creating an entity so that you know a particular entity falls under which of these domains. Okay. So go to general MDL entity and then click on output. This is one way of creating it. Second way of creating it is if there's a pre-existing output, right click on this and say add output. Okay. And the third way of creating it is from the client specific toolbar, which is this option here. Okay. So once you create the output, this is the output panel, and these are the different types of outputs that can be requested by the user. And the outputs can be between the 2 points, it can be on a particular entity, or it can be on a particular entity set. So you can change that in this drop down menu. And then here we need to select body 1, between which 2 bodies you want to measure a particular output, and also define the reference marker and the point on body 1 and point on body 2. So all these options need to be resolved before requesting the output. And then here we have this particular option wherein we have the eye marker. We can either request the output just on the eye marker or just on the J marker, which is nothing but the marker on the body 1 is the I marker, the marker on the body 2 is the J marker, or you can request the outputs on both, okay, with respect to both the bodies. So these are the options available after creating the output. Let's go back to the presentation. So I'm trying to explain the same thing here, whatever I showed you in the graphical user interface. So here, if you pick 2 points, then it is for measuring displacement, velocity or acceleration between 2 points and not to forces. It's not applicable for forces there. If you pick entity, then it will pick just one entity to measure any of these parameters. And if you pick an entity set, you need to pick one entity type, like for example bodies, to measure, and MotionView will create outputs for all the same type of entities that are present in your model. The second thing is, outputs can also be defined by using expressions. Up to 6 independent expressions can be entered per output in your output panel. And outputs can also be user-defined or subroutines. So the user-defined output is requested by entering a subroutine parameter in a text box that calls a solver request subroutine. So the function types can be written in the following scripts. It can be either in Fortran, C++, C, Python or MATLAB scripts. Okay, now it's time for me to do the demo on exercise 4. Now let's continue with the demo on exercise 4. Let's open the model that we had created in the previous chapter. So we can either go to chapter 4 exercise start, or we can go to chapter 3 exercise completed. So either of the two should do. So I'll just bring up this model, which is where we had stopped in the previous class. So now for this free body, I'll be giving it some initial conditions. Okay, you can click on the free body in the model browser and then go to the initial conditions tab. You can put a check mark in the Z direction, VZ. So we are basically giving it a translational velocity in the Z direction to set the body to have an initial velocity going up. So, and the units and the value I'll be giving it as 1000 millimeters per second going up. So this is the initial velocity that is given to the body. Now let's create an output request. So we can go to this particular icon on the client specific toolbar. We can leave the defaults as it is. So the type of output request that we are requesting is the displacement. We want the output to be on an entity, and that entity should be a body, which is nothing but the free body. So we are requesting the displacement of an entity, which is this free body, in the global reference frame, and here we'll be keeping the option as both. So many of the entities in MotionView or MotionSolve, they require markers to define them, which include an I marker on one body and a J marker on the other body. For example, measuring the displacement between the two bodies will be measuring the displacement between the I marker of one body and the J marker of the other body. So this drop down menu here, it specifies whether the output measurement should be of the I marker on the body or the J marker of the body with which we are measuring with respect to, or both. So here I'm selecting both, and now I'll be running the simulation. So I'll save this as chapter 4 exercise complete, save, run. Okay, it's complete now. Let's close this. Go to the plot option here, which brings up hypergraph, and here you can try two things. The first thing is click on the free body and the Y component is the Z direction, and click on apply. You can now see that the body is going up and then it is coming down under the action of gravity, and the body here going up is because of the initial velocity that we provided in the Z direction. Okay, so now let's see what difference is there between this curve and the marker displacement that we've created. So technically they should be the same. So let's verify. Go to marker displacement on the free body, and in the Y component I'll select DZ and say apply. So here if you zoom out and see, the curves look like they overlap each other. But if you zoom in, you can see that There's actually a difference between these two curves. I hope you're all able to see that. Okay. The graphs are nearly coincident but separated by a y displacement of 5. Okay, which is the z difference between the center of mass, which is at 5, 0, 5 in the Cartesian coordinate, and the body coordinate system, which is located at the global reference frame 0, 0, 0. Okay, to set this right, okay, to correct this, what we need to do is we need to set the body coordinate system to have its origin at point 2, just like the center of mass. So let's do this. We will change the body coordinate system of this body to point 2. So this will change the MotionSolve default output to measure at the center of mass for this body instead of at the ground point. Let's do that. Let's go back to MotionView here and let's click on the free body. So to bring up the body panel, here let's go to the body coordinate system and put a check mark on use the body coordinate system. You can see that this marker comes and sits on top of this point 2 now after I give the origin point as point 2. Okay, you can now see that. So now it's perfectly aligned. So once this is done, you can run the model again and compare the results. So let's go to plot. Okay, so first I'll plot the body, free body in the z direction. We have this curve. Now I'll go to the marker displacement on the free body and the y component is dz. Say apply. Now they should exactly overlap on top of each other. Yes, and we can see that happening. So I hope you got the difference between what happened earlier to this plot. Okay, so this brings us to the end of the demo on chapter 4. Thank you. Welcome to the second chapter of the Introduction to Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. In this chapter, I will cover the concepts of free body creation, simulation, and plotting. After explaining the theory, I will give you a demo on exercise 2. This slide illustrates the basic entities required to build a model. They include the bodies or the parts, which may be categorized under rigid bodies or flexible bodies. Constraints can be further subdivided into joints and motions. Forces consist of actuators, connectors, springs, dampers, contacts, etc. Geometry and special entities such as markers, built-in outputs to measure displacements, velocity, acceleration, forces, etc. So the basic entities also include other model-dependent solver design variables, state variables, sensors, systems, etc. Now, I will explain about the different types of bodies used in MotionView, MotionSolve. There are 3 types. They are rigid body, point mass, and flexible body. A rigid body is one which has both position and orientation, and the deformation is considered negligible. Rigid body motion is always represented by its center of mass and orientation. They are used when both mass and inertia are significant. It is a 6 degree of freedom element. Point mass. We use this 3 degree of freedom element when the moment of inertia of the component is negligible, but its mass is significant. Flexible body. We use this element when the component deformation has a significant effect on system dynamics or when component stresses are of interest. Now, let's move on to the procedure of adding various entities in MotionView, MotionSolve. You can add the basic entities in 3 ways. For instance, let us consider adding a point. For this, let me go back to the MotionView GUI. So there are 3 ways of adding points or other entities in MotionView environment. So the first option is to go to the model browser here, right click on the model, go to the add option, and under the add option you can go to the reference entity and then click on point. So this is one way of adding point. The second way is in the model browser, right click on the folder and then say add point. Even this does the same thing. And the third and the most easiest way of adding an entity in MotionView is going to the client specific toolbar and then right click on the particular icon and then say OK. So please note that there are two important points here. The ground body and the global origin and even the global frame. So these are some of the entities that are always created as default when you open a new MotionView session. So, and the second point that you got to remember here is right clicking on an icon is for adding an entity into MotionView, whereas left clicking an icon is used for selecting an entity. Now let me go back to the presentation. Let's move on to collectors. Let me highlight a few key points on collectors. A collector is a button on a panel that enables selection of an entity type either graphically or from the Select an Entity dialog box. A panel can contain any number of collectors, but only one can be active at a time. Entities can only be selected from an active collector. A collector is active when it is enclosed in a blue rectangle as shown in the image. The label on the collector indicates the current entity type. So the yellow box that you can see is the label. Some collectors have a switch, as you can see here on the slide, with this drop down menu to change the type of entity. So here the entity type, it can be changed from point to vector. As I mentioned in my previous presentation in chapter 1, gravity and units are created by default in a model. It can be accessed by going to the model browser and then selecting the MISC option and then expanding the forms folder. Both the English and the metric units are available. So if you go to the model browser here and if you expand this folder and if you go to its subfolder called as forms and we expand that folder, then we can see these two entities, the gravity as well as the units. So by default, gravity is always on and it can be turned off anytime by the user if in case the effect of gravity needs to be neglected for any purpose. Now I will give you a hands-on demo on exercise 2, which will cover the topics on free body creation, simulation and post-processing using Altair's post-processing software Hypergraph 2D. Welcome back to the 5th chapter on Multibody Dynamics using Altair HyperWorks, MotionView, MotionSolve. In this chapter, we will deal with the topic on constraints. In Multibody Dynamics, constraints are the algebraic equations that restrict or dictate the relative motion between the interacting bodies. In MotionView, joints and motion fall under the category of constraints. So by making use of constraints, that is the joints or the motion, you can control the behavior of the interacting bodies. Constraints generally restrict two types of motion. The translation motion along x, y and z axis and the rotational motion along the x, y and z axis. The sizes of all the models in CAE are measured in terms of degree of freedom. First, let's try to understand the meaning of degree of freedom. The degree of freedom of a mechanism is basically the number of independent relative motions used to define the configuration of a system. Every rigid body has 6 degrees of freedom, meaning all the joints are constrained on the rigid body. The degree of freedom is calculated by using the Gerbler's equation, which is equal to 6 times the number of rigid bodies in the system minus the summation of 6 minus the degree of freedom of each joint varying from j is equal to 1 to j is equal to the total number of joints in the system. Now let's try to understand the meaning of degrees of freedom with the help of animations, because I personally believe that practical examples are easier to understand when compared to definitions and formulae. Consider the example of a box shown in this slide. It represents a rigid body. So please watch this animation and we can conclude how many degrees of freedom this particular system has. You can see this is the translation about x-axis, translation along y-axis, translation along the z-axis, rotation about the x-axis, rotation about the y-axis, and the rotation about the z-axis. So thus, this rigid body has 6 degrees of freedom. From this slide onwards, we start reducing the degrees of freedom by making use of constraints. In this animation, one entity is chosen as sphere and the other flat body is considered as a fixed body. So this means that the sphere inside this box is not allowed to translate in the z direction. Now I will be playing the animation. The sphere can move freely about the x-axis, about the y-axis. It can rotate about the x-axis. It can rotate about the y-axis, and it can rotate about the z-axis. So this means that only the translation movement along the z-axis is not possible. So hence, this system has 5 degrees of freedom. Now let's further try to reduce the degrees of freedom by changing our system. We will now replace the sphere with a cylinder. So now let me play the animation. So this cylinder is free to move along the x-axis, along the y-axis, rotation about the y-axis, and rotation about the z-axis. This particular system has 4 degrees of freedom. I'm just playing this animation once again so you can take a closer look at it. Okay, so you got to know by changing the sphere to cylinder, we could now reduce the degrees of freedom for the same boundary condition. Now, if we replace a cylinder with a cube in the same boundary condition, let's see how many degrees of freedom does this system have. So let me play the animation. So it can move along the x-axis, it can move along the y-axis, it can rotate about the z-axis. So the movement in all other directions, either the translation or the rotational movements, are all constrained. So thus this system has 3 degrees of freedom. Now, what if we assemble a round shaft in a coaxial cylinder? How many degrees of freedom does this system have? Let me play the video. This cylindrical shaft can move along the y-axis and it can rotate about the y-axis. Let me play the video again. So this is a translation in the y-axis and the rotation about the y-axis. So these are the only 2 degrees of freedom this system has. So hence the degree of freedom of this particular system is 2 degrees of freedom. So hence the degree of freedom of this particular system is 2. Finally, when we reduce the degree of freedom of a system to only 1 degree of freedom, then we can obtain a unique motion. For example, in the current slide, if the translation movement of the shaft is constrained, then the shaft is only allowed to rotate about the y-axis, making it a 1 degree of freedom system. So I'll be playing this video again. You can see that we have applied one more constraint wherein this cylindrical shaft is not allowed to move in the y direction. So it is just able to rotate about the y-axis. So thus making it have just 1 degree of freedom. In this slide, imagine we have a cubicle box with a rectangular slot. So which is just enough to fit this wooden sledge. So now if I play the animation, you can see that there is just translation movement along the y-axis. That's possible for this particular system. So thus making this system a 1 degree of freedom system. At this point, I quickly want to give you the differences between the kinematic and dynamic simulation. So if we consider the current system as shown in this slide and provide an initial velocity to the sledge in the y direction, since it has only 1 degree of freedom, we can perform dynamic analysis to calculate the acceleration, force, etc. required to move the sledge from point A to point B. Okay. However, if we apply translation motion on one end of the sledge along the y-axis, then the degree of freedom of the system becomes 0. As a constraint, motion will remove the 1 degree of freedom of the system and the analysis becomes a kinematic simulation. I hope the concept of degree of freedom and constraints is more clear now. So we'll get into the details of dynamic and kinematic simulation in our future classes. As we all know, joints serve as interconnections between components. So the table in this slide shows the list of joints that can be created in MotionView along with the degree of freedom each joint removes. So we have a constant velocity joint, a cylindrical joint, a fixed joint, a planar joint, revolute joint, screw joint, spherical or ball joint, translation joint, and universal joint. So in this slide, I've given you some examples of the joints that was shown in the previous slide. So here, for example, the cylindrical joint, it removes 2 translation and 2 rotational degrees of freedom, thus totally removing 4 degrees of freedom. So thus totally removing 4 degrees of freedom. The spherical or the ball joint removes 3 translational degrees of freedom, thus allowing the connected entities to rotate freely about the 3 axes. So this joint removes 3 degrees of freedom. The fixed joint is used to fix one body to the other. In other words, it removes all 6 degrees of freedom in total, and so on. Now, let me briefly touch upon the significance of markers in context to the constraints. As mentioned in the previous lecture, markers are required for defining a joint in order to restrict or dictate the relative motion between the bodies. A marker on one body is called as the I marker, which must be constrained to a marker on the other body, which is referred to as the J marker. In this slide, I'll give you a brief introduction to the compliant joints. Compliant joints are similar to bushings and allow the relative motion in all the 6 degrees of freedom. In MotionView, in order to make a joint as a compliant joint, we need to check this particular option which says allow compliance at the time of the joint creation. Please note that you cannot switch to a compliant joint if you've already started creating a joint that is not defined as a compliant joint. So now I will show you the 3 ways of adding constraints, that is joint or motion, into a MotionView model. Let me show that to you in the graphical user interface. So one way of creating joints is by right clicking on this model browser, go to add option, and then we have to select the constraint entity and you can go click on joint. So this is one way of creating it. So here in this drop down menu, you have the different types of joints available and you can select any joint that you require. So this is one way of adding joints, and the second way of adding joints is just by right clicking on a pre-existing joint and then say add joint. So this is the second way of creating joints, and the most easiest way of creating joints is on your client specific toolbar. You can just right click on the joints option and then say add. Right click on the joints option and then select the type of joint you want and then say OK. So the similar thing can be done with the motion. So this is the option on the client specific toolbar to add motion to your system. Now let me go back to the presentation. In this slide, I will explain regarding motion as a constraint. It is used to define a motion input at a degree of freedom in a joint. This input is only allowed on 3 types of joints: the revolute joint, the translation joint, and the cylindrical joint. So motion can be applied as a displacement, velocity, and acceleration in a form of linear parameter, curve, 3D spline, expression, etc. Okay, now I will give you a quick demo on exercise 5 to highlight the importance of constraints in the MBD models. In this exercise, we'll be adding a revolute joint to the free body that was created in the last exercise to create a simple pendulum. We will also add a motion to the revolute joint to create and simulate a kinematic model. So you can either reuse your model from the previous exercise, which is recommended, or you can open a file which is called as chapter 5 exercise start, which is saved in the chapter 5 folder, and you can start building a model. So file, open, model. You can go to chapter 5 and select chapter 5 exercise start. But if you have saved your previous model, then that is recommended to use. Okay, so now I'll be adding a joint to this particular free body. So to add a joint, I'll go to the client specific toolbar, right click on the joint, and I want to add a revolute joint. So I go to the drop down menu and select revolute joint. By default it is the ball joint, but I have to go to the drop down menu and select the revolute joint here. So this revolute joint will remove 3 translational degrees of freedom and 2 rotational degrees of freedom from the body. Now you can leave the label name and variable name as it is and just click on OK. So once you start the creation of a joint, you need to go to the panel area, the joint panel area, and specify which two bodies need to be connected with this particular joint that you've created, and also at what point the joint has to be created, and also its alignment axis. So for this, for body 1, double click on body 1 and you can select free body, and then this blue highlighter, it automatically moves to body 2. Okay, so then it means that we need to select body 2. So double click on body 2 and then you can select ground body as your option. So this means that you're creating a revolute joint between the free body and the ground body. Now you need to select the point of origin of this particular joint. So double click on, you can just single click on the point and then it brings up this particular dialog box. You can select point 0 and say OK. So now you can see the joint that's created. Okay, now you need to align the joint. So thus, because it's still not aligned the joint, it says as unresolved here. So click on this. You can either align a joint about a point, or you can either align it along a vector. So I would like to align it along a vector. So I go to this drop down menu and change it to vector, and I will choose global Y as my alignment vector and say OK. So you get global Y here. So you can see that this particular revolute joint is now aligned about this global Y axis. Okay. So now you have set up your joint. Okay, so before I move on to the next steps, I'd like to show you one thing in MotionView that's really helpful, wherein at each and every step you can go and check your model if your model building is right. Okay, for that, first you need to go to the tools menu. Here you can go to options. Okay, and then here you can go to check model and make sure all these things are enabled. For me, they're already enabled, but when you're using MotionView for the first time, these boxes won't be enabled. So make sure you put a check mark on all these and say OK. So now when you want to check your model, you can just go to tools, say check model, and you get this particular dialog box. You can go to the DOF, degree of freedom, to check how many degree of freedom your model is. So it shows that it is 1 degree of freedom, which means if you run a simulation now, it will be a dynamic simulation. Okay, I hope you're getting what he's saying. So please make sure that you enable this particular option in your MotionView graphical user interface. Say OK. Now let's move on to the next steps and we will run this analysis. So click on this green icon that you can see on the toolbar and let's save this particular model. So I'll open this and I will save this as simple pendulum. Okay, say save, and then let the simulation time be for 5 seconds. Okay, and also the simulation type, let it be transient. We can leave it as it is and just hit on run. So the MotionSolve runs in the background and you'll be getting the results. Okay, so it says simulation complete and this is your message log. If you just scroll up, you can see it has written out in the message log, it has written out each and every step that MotionView does in the background. Okay, and you can see this particular statement here, starting dynamic analysis. This is because the degree of freedom of your model is 1 and hence it's a dynamic analysis. Okay, so I just want to show you that. Now you can directly click on animate button. So this splits your screen into 2 parts, and on the right part it invokes HyperView, which is Altair's post-processing software, and now you can click on the play button to see the animation. Now I'll just slow down the animation. So this is how it looks like. Okay, you have just revolute joint there, so it is still not your simple pendulum. We are just getting to that. So this is how it rotates. It rotates 360 degrees now. Okay, because we haven't given any other constraint apart from this joint. Okay, now you can stop the animation, click on your MotionView window and maximize it. Now let's move on to the further steps. Let's add a motion to this particular model. So click on the motion icon, right click on this to create a motion. Okay, you can accept the defaults and say OK, and then you want to create the motion on this particular joint. So you want to define the motion on a joint. Yes, and now you need to select which joint you want to place your motion on. So select the joint 0, and there's only one joint in a model, that's this joint 0. So you get this red arrow here, which means that a motion is now created about this revolute joint. Okay, so once this is done, you can go to properties. So you need to give a property for the motion that you've created. So let's define the motion of that particular joint by an expression. Okay, and now you can click on the expression or the function builder. So you have these two codes here. Okay, so please make sure that you need to use these back quotes which are found in the upper left corner of your keyboard. If you use single quotes or double quotes, then your expression builder won't work. So please make sure you use the right quotes. Okay, so place your cursor in between these two quotes and then you can give an expression. For example, say sine 2 into pi into time. So sine 2 pi time. So the time that we've taken here is the simulation time, which is 5 seconds. So it is basically sine 2 pi into 10. Okay. Sorry, in sine 2 pi into 5. So say OK. So you've defined an expression for your motion now. And now what do you expect? If you go and check your model, you need to see that it is the degree of freedom of the model should be 0, because it had 1 degree of freedom, but you're constraining that 1 degree of freedom with the help of this motion. So thus you are converting a dynamic model into a kinematic model. Okay, so let's go and check what the software says. So if you go to degree of freedom, yes, MotionView is right. It says that the degree of freedom of this entire system is now 0, because the 1 degree of freedom which is remaining, we've constrained it by using this motion. Say OK. So now whatever you run, it will be a kinematic analysis. Okay, so now I hope you get the difference between kinematic and dynamic analysis. Okay, so the simulation is complete. Now if I just scroll up on the log, message log, you can see that it says starting kinematic analysis. Okay, because the degree of freedom was 0. So now you can go to animate and say refresh, because it needs to refresh the previous results. And now you can click on play. So this motion now, whatever you see, is basically as per the expression that you've defined by using the motion on the joint. Okay, so it's rotating about the y-axis with the help of the revolute joint, and it is dictated by the expression that you've defined for the motion on the joint. Okay, so now I'll stop this animation, go back to MotionView, expand this. So now what I'll do is I want to deactivate the motion that I've created. So I'll just click on this motion in the project browser. I can just right click on this and say deactivate. So you can see that the red arrow disappears. So this means that the effect of this particular motion from your system has been now deactivated. Okay. So now after doing this, I hope you all remember that you had also given an initial condition to your free body in the z-axis. So if you now just go to the body and click on free body and go to the initial conditions tab, you can see that this particular option was checked. So we had given 1000 mm per second velocity in the z direction for our free body. So I want to deactivate the initial condition too. So I will click on this. So I've deactivated the initial condition for this body. Okay. So now what I want to do is I want to go ahead. I've deactivated the motion on this joint, and also I've deactivated the initial velocity for the free body. So now what I'll be doing is I'll be giving an initial condition for the joint. So I'll just click on joint from the project browser, and then I can go to the initial conditions tab in the panel, and then because it's a revolute joint, only this particular option can be selected, that is the rotation. So I'll check this rotation and then give 10 units as the velocity. So basically it will be 10 millimeters per second. Okay, so I'm sorry, so here by default the rotation will be in radians per second. So once I've given the 10 units here, it will be in 10 radians per second. Okay, so now you can check the model first and see what type of analysis it is. If you go to degree of freedom, you can now see that it is again gone back to 1 degree of freedom, because you've removed that constraint which you had defined in your previous analysis. So now again it's a dynamic simulation. So now go to run option and then click on run. So this performs the analysis and MotionSolve runs in the background and it gives you the results. If you can just scroll up, you can see that it says starting dynamic analysis because the degree of freedom was 1. So now close these two and say animate, say refresh to refresh the results from the previous simulation, and now click on this button. So basically this cylinder now, it rotates at 10 radians. It rotates at 10 radians per second. So the initial velocity what we had given at the revolute joint here. Okay. So this brings you to the end of exercise 5. Thank you. Welcome back to the 6th chapter on Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. This chapter covers only the theoretical concepts on the MotionView, MotionSolve process overview. I thought it is important to include this chapter since I need you to understand the entire process that is involved in building a MBD model in MotionView and not just the graphical user interface, so that you will be confident in building your own MBD models by the end of this course. This is a flowchart that explains the process overview of MotionView, MotionSolve. MotionView is a preprocessor where the model building is done. You can either import an existing model in the .mdl format or save the MotionView model file in the .mdl format. After the simulation is complete and you have the results, you can either choose to save the model along with the result files in a session file which has an extension of .mvw. Similarly, a session file can also be imported into the MotionView graphical user interface. After the model is built, the next step is to save the model. You need to save the model before running the simulation. When you save the model gets saved in the .xml format, which is recognized by the MotionSolve solver. Once the analysis is complete by running the MotionSolve in the background, the files such as MRF, ABF, PLT, etc. for plotting and .h3d for animation are created to post-process the results using Altair's post-processing software for plotting, which is the hypergraph, and animation is done using HyperView. There is also another stream to the process. Once the model is built in MotionView, the model can be exported and run using other solvers such as Adams, and the results can be further post-processed using Altair's post-processing software HyperView Hypergraph. This is a very convenient provision in MotionView. This is basically the process overview of MotionView MotionSolve. Now, I will continue to explain regarding the MotionView model, that is, the .mdl format. So, MDL stands for Model Definition Language. The MotionView model contains the information in the form of this language which is required to describe a mechanical system. Complete model information is stored in the MDL format. An MDL is basically a ASCII programmable language. Now let me highlight some of the benefits of using the model definition language. You can open and edit the model in any text editor easily. It is very easy for model debugging. It also has the capability to build modular and reusable models. It is very easy to create a parametric relation between the entities in the model. In this slide, I will highlight some key points regarding the syntax of MDL format. All the models need to begin with a begin MDL open and close synthesis, and they need to end with the end MDL open and close synthesis statement. The syntax of the MDL statement is an asterisk, followed by a valid statement with its arguments defined. Statements without a leading asterisk are considered as comments. Example: I will be opening the simple pendulum.mdl file in a text editor, and I'll be reviewing the model for a body, joint, and a motion. So let's do that. I will open the model file. So we have the simple pendulum.mdl file here. So we have the simple pendulum.mdl file here. So I'll right click on this and I'll say edit with Notepad++. So you can easily open it in any text editor. So I'm using Notepad++ here, and you can see the various things that I already explained. So it always begins with an asterisk and begin MDL statement, and then all the standard statements, it always starts with an asterisk sign. So here we have the information about the body. So we created a free body, so that's given here, and also a point, and we call it point 0, and we also have two other points, point 1 and point 2 in this MDL file, and we also have a graphic which is a cylinder, which is basically representing the free body, and the other details of the cylinder is given here, or the other details of the graphic, for example the radius of the graphic, everything is understood in this statement. So, and we've set the body inertia, and also these are the location of the points, and this is the initial condition of the body. So we had given the initial condition in the z direction to be 1000, so that's what is given here, and the output, we're requesting the displacement of the free body, so that's what is mentioned here. And then we've created a revolute joint, we've also created a motion, and for the motion, the properties we've defined it using an expression which is sine 2 pi times time, and you can see the other statements here. And also we've given a joint initial condition, that is the rotation with 10 radians per second. So this is the entire model information that is stored, and the ending of this particular code, it ends with an asterisk and end MDL open and close parenthesis. So this is your whole model file that is stored in the background in the .mdl format, and it can be easily opened in any text editor, and it's very easy to understand. As you saw, I just quickly went through the entire script, and it was pretty simple to understand what is being written in the background when you create entities in the graphical user interface, right? Okay, now let's get back to the presentation. So here I'm going to explain about the MotionSolve input file. So as I mentioned in the second slide, once the model building is complete, we need to save the model, which gets saved automatically in the .xml format, which is the only format recognized by the MotionSolve. All the model data is contained in the MotionSolve.xml file except the flex body information, which is stored in the .h3d file. The input file contains both the model and the simulation command. Here is an example of how the data is stored in the .xml file. If we consider, for example, the rigid body that we created, it has the information on the ID, label, center of mass, inertia marker, the local part reference frame ID and its mass, and the inertia about the x-axis, y-axis and the z-axis. So this is basically the inertia about the diagonal matrix. So we have the values here. So this information gets saved in the .xml file. Now let me briefly explain regarding the H3D files. So there are three types of H3D files. They are the graphic H3D file, flex body H3D file and the result H3D file. It is very crucial to understand the differences between the three types. Graphic H3D. So it's created by either the CAD import utility or by using HyperMesh. It does not contain any result information and generally it is used to represent parts with realistic geometry. It is useful for visualization, but it cannot be animated in HyperView. Moving on to the next type of H3D file, which is the flex body H3D file. So this is basically the modal representation of a finite element model, and this comes into picture when you're building a model using flexible bodies. So it is generated by using MotionView FlexPrep utility or by using the HyperMesh OptiStruct interface. So the modes and the displacement, stress, strain, contours can be post-processed using HyperView. Now coming to the last type of the H3D file, which is the result H3D file. So this stores the result from the MotionSolve and can be post-processed using HyperView. In the present and the next two following slides, I'll be explaining regarding the run option that you can see in the toolbar, which is used for running the simulations after building the models. So let me go to the graphical user interface. So this is the run option that you see on the client specific toolbar. The run panel basically allows you to edit the solver parameters. You can also change the type of simulation and also the simulation parameters such as the print interval and also the simulation time in the run panel. We can also control the type of result files and also their contents by changing the simulation settings and the output options in the run panel. So you can find the simulation settings and the output options in the same run panel. So you can also adjust your other parameters by clicking on these options, and then the particular dialog box appears and you can play around with the various parameters which are present in these particular dialog boxes. So I'll be illustrating this in detail when we go to the exercises. So this brings us to the end of chapter 6, and as I mentioned here, we do not have any demo exercise for chapter 6. It is just a theory. It is just a chapter which was based on the theoretical concepts. I hope now you've got a brief understanding of what happens in the background when you run a simulation in MotionView. Thank you. Welcome back to the 7th chapter of Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. In this chapter, we will cover the concepts of redundant constraints, joint primitives, and motion function. When you are trying to build a model in Multibody Dynamics, it is always possible to over-specify the constraints in the model. In such scenarios, the system is said to be over-constrained. To make this concept more clear, I have tried to explain it using a mathematical equation in this slide. Consider a constraint equation, x minus y equal to 0. If we add the same equation, we get 2x minus 2y equal to 0. Clearly, you can see that this equation constrains the variables x and y identically to the first equation. Thus, the second equation is called a redundant equation. Now let's consider the example of a door to a frame with the hinges as shown in the figure. We all know that a rigid body has 6 degrees of freedom. Door, being a rigid body, has 6 degrees of freedom. Hinge represents a revolute joint in multibody dynamics. As I had explained in the previous chapter, a revolute joint constrains 3 translational degrees of freedom and 2 rotational degrees of freedom, totally constraining 5 degrees of freedom. This means that it only allows rotation about one particular axis. So if we consider that a door is fixed to the frame with the help of these 3 hinge joints, allowing the door to open and close, the total degree of freedom of this system will be 6, which is basically the degree of freedom of this rigid door, minus 5, and -5, which will give you a total of -9 degree of freedom. Hence, when the degree of freedom becomes negative, the system is said to contain redundant constraints. In this example, a couple of points is worth noting. They are: the hinge axis is required to be perfectly collinear. Otherwise, the door cannot be opened and closed. Only one hinge out of these three is actually necessary to perform this simulation in Multibody Dynamics, and the remaining two are redundant in nature. If such a system is introduced to MotionSolve, the solver will detect a redundancy in constraints and remove the equivalent of two hinges, or in this case the two revolute joints, from the model. Now, if you run the analysis, although the correct motion might get predicted, the effect of removing the two hinges from the solution process is that the reaction forces or torques will be zero, and they no longer contribute to the equations of motion. In reality, all the three hinges 1, 2, and 3 have reaction forces and torques. But say you want to request the reaction forces on hinges 1 and 2. If MotionSolve removes the first and the third joints as redundant, then you will not be able to recover the reaction forces or the torques at these locations, even though the motion prediction, that is the animation, may look right. It is very rare that a model requires or has some use of redundant constraints. So now, it is very rare that a model requires or has some use of the redundant constraints. So we now understand that these redundant constraints need to be removed. There are three different ways of removing the redundant constraints. They are: the first way is combining the degree of freedom with the lower pair joints or the joint primitives. I will explain about them in detail in the upcoming slides, making use of the compliant joints or the bushings. And the third way is to use flexible bodies in your model building process. This is a very effective approach, but of course at the expense of computation time. Now let us understand how the constraints are classified in MotionView. Constraints are basically subdivided into 5 different categories, as shown in this slide. They are the lower pair constraints, joint primitives, or also called as J-prims, the higher pair constraints, motion, and other joints. Now let us understand the definition of each of these constraints in detail. The lower pair constraints. A lower pair constraint is an ideal joint that constrains contact between a point, line, or plane in the moving body to a corresponding point, line, or a plane in a fixed or another moving body. These have physical analogies, for example, a revolute joint. Joint primitives. The joint primitives constrain combination of individual degrees of freedom between the bodies. In most of the cases, there are no mechanical equivalents for joint primitives. Higher pair constraint. In higher pair constraints, the two bodies are in contact at a point or along a line, as in the case of ball bearing or disc cam and the follower. As in the case of a ball bearing or disc cam and follower, and the relative motions of the coincident points are not the same. A motion is a prescribed displacement, velocity, or acceleration on a body along a specific direction. When a motion is applied on the body, the free degrees of freedom of the body are replaced by the prescribed movement as specified by the motion, and thus motion is considered as a constraint. Other joints. This classification consists of constraints which are used to specify algebraic equations, which are used to specify algebraic relations between two or more joints. So in total, there are 27 types of joints in MotionView. The flow chart on this slide illustrates the classification of constraints in MotionView. So under the lower pair constraints, we have the constant velocity joint, cylindrical joint, fixed joint, planar joint, revolute joint, screw joint, spherical or the ball joint, translation joint, and the universal joint. Under joint primitives or J-prims, we have at point, inline J-prim, in-plane J-prim, orientation J-prim, parallel axis and perpendicular axis J-prims. In higher pair constraints, we have point to curve joint, point to surface joint, curve to curve joint, curve to surface joint, surface to surface joint, point to deformable curve joint, and point to deformable surface joint. And we also have a constraint made joint. Under motion, motion can only be applied either on a joint or motion can be applied using markers. And under others and under other constraints, we have couplers and gear. So these are the 27 types of joints that are there in MotionView to build the model. In the current and the next slides, I'll be explaining about the J primitives in detail. Joint primitives or J prims don't have a direct physical analogy, but they have similar functions like the joints, basically to remove the translation and rotational degrees of freedom. J prims are usually used to model more complicated mechanisms. They are often used in combination with other joints during the model building process, without introducing redundant constraints into the system. The table on this slide shows the different J prims available in MotionView. They are at point, which is used to constrain 3 translational degrees of freedom, the inline constraint or the inline joint, which is used to constrain 2 translational degrees of freedom, the in-plane J prim, which is used to constrain 1 translational degrees of freedom, and the orientation, parallel axis and perpendicular axis constraints are used to constrain 3, 2 and 1 rotational degrees of freedom respectively. In this slide, I will explain one of the popular J prims, that is the in-plane J prim, in detail. This is a constraint primitive that requires that the origin of the reference marker on body 1 in the figure which is shown in this slide to stay in the XY plane, defined by the origin of the J reference marker and its Z axis. The in-plane primitive constrains 1 translation degrees of freedom. It restricts the translation along the Z axis of the reference marker J on body 2. However, all the rotations are allowed. One of the most important application of this in-plane J prim is the 2 or 4 post test rig for the suspension system. In this slide, I will be explaining briefly about the motion function, since it will be used in the demo exercise for chapter 7. Generally, there is a function to measure the force and or torque in every type of entity in MotionSolve that produces a force or a torque. For example, we have a bush function to measure the force or torque produced by the bushing entity. We have a joint function to measure the force or a torque produced by the joint entity. And similarly, we have the motion function to measure the force or the torque produced by the motion entity. The syntax for the motion function is motion followed by its arguments, which are ID, J flag, component and the reference marker. So the ID of the motion joint or the motion marker, so the ID represents the ID of the motion joint or the motion marker element. The J flag is basically equal to 0 or 1. It means that the forces and the moments are reported at I or J marker respectively. So if you give 0 here, then the forces and the moments are reported at the I marker, and if you give 1 here, then the forces and the moments will be reported at the J marker. And the third argument is basically the component. If you have 1, it returns the force magnitude. If you have 2, it will be returning the value of the force X component. 3 will return the forces Y component. 4 will return the forces Z component. 5 will return the torque magnitude. 6 will return the X component of the torque. 7 will return the Y component of the torque. And 8 will return the Z component of the torque. And Rm in this argument, it refers to the reference frame in which the components are reported. So if you have Rm is equal to 0, then it implies a global reference frame. Now I will be giving a demo on the exercise 7. Thank you. Welcome back to the demo on exercise 7. In this exercise, you'll reuse the simple pendulum model created in the previous chapter to add 2 more bodies and 3 more joints to create a 4-bar mechanism. In the process of creating this, you'll also investigate the redundant constraints and modify your model to remove them. You'll also use a motion function to measure the torque from a motion driving the model and also plot this. So you can either reuse your model from the previous exercise, which is recommended, or you can open a model which says chapter 7 exercise start in chapter 7 folder, and you can start building a model building process. So go here and select this. So this is where we had stopped in the previous exercise. So let's begin by renaming the points. So let's go to the model browser and expand points folder. So I want to rename point 0 as point A, 1 as point C, and 2 as point B. So now I also want to add 2 more points. So let's go to this option. I'll call it point E. So here I'll change to point E, say OK, and then 1 more point, so that's point F, say OK. So I've created points from point A to point F, which does not have point D. Okay, so now I'll be giving the coordinate values for these hard points that I've created. So for point A, the x coordinate is 921, y coordinate is 580, and the z coordinate is 1124. So next for point B, it is parametrically connected to point 0 or point A. So I will delete this parametricity and give specific values for its coordinates. So 918 for the x coordinate, 580 for the y coordinate, and 1114 for the z coordinate. Similarly for point C, it is 915, 580, 1104. For point E, the x coordinate is 878, y coordinate is 580, and the z coordinate is 1108. For point F, the x coordinate is 878, y coordinate is 580, and the z coordinate is 1118. So don't worry, the model hasn't disappeared. You just have to fit the screen. So just click on the graphical user interface and hit F key on your keyboard. This is the shortcut to fit the screen. So you can see your model. Now once this is done, let's use our knowledge of macros and create a point between these 2 points and also another point between these 2 points. Okay, so let's go to the macro option. So I want to define a macro along a vector. So the first starting point, I will select it as point C, and the second point is point E, which is this point, and I just want 1 point in between these 2, so I'll leave the number of points as 1 and I say create point. So you have a point 3 which is created between these 2 points and which is equidistant from these 2 points. Now similarly, I'll do the same thing and create a point between the point E and point F. So here I will change this to point E and this one to point F, and I say create point. So you got another point between these 2 points which is equidistant from point E and point F. Now I'll be creating 2 more bodies. So I'll go to the body option on the client specific toolbar. I'll create a body 0 and I say apply, and I create a body 1 and I say okay. So the 2 bodies, body 0 and body 1, they get created. they are created. And now I'll click on body 0 and I need to specify its properties. So mass, I'll be randomly giving it as 1 kg, and the inertia properties, just random values, just 4 ones. And let's go to the center of mass coordinate. So I'll put a check mark on this, use the center of mass coordinate system, and then here the origin point I will choose 0.3. So body 0 is created at this particular point. So now I will go click on body 1 and I'll specify the properties for body 1. So here again I'll give a random mass and random values for the inertia properties. And center of mass, put a check mark on this, and the point will be 0.4, just this point. So you created a point, you created a body at 0.3 and also at 0.4. Now let's go ahead and create geometries for the body. So right click on this particular icon on the client specific toolbar, which is the graphic icon, and by default it's a cylinder itself. So just say apply and again say OK. So you got 2 cylinders, but it is not shown on your graphical user interface because we need to specify the properties for these graphics. So click on cylinder 1 in the project browser, and then let's go to the connectivity tab. Here for the parent body, we'll be specifying it as body 0, which is this body, and origin for this body, for this particular cylinder will be the point C, which is nothing but this point, and the direction or the end point will be point E. So you got a cylinder. That's a pretty huge cylinder. So let's change its radius. So let's go to the properties and let's just give 1 mm as radius. Now let's go to the second graphic, which is the second cylinder, and do the same. Let's go to the connectivity tab first. So its parent body will be body 1, which is this particular body. And the cylinder starts from this point, which is point E, and it goes up till point F. And the properties, by default the radius of the cylinder that's created is 10, so we just want 1 mm radius for the cylinder. So now we have this particular model. So let's click on this, and this is basically the cylinder 0 that was already there. So we can now change the radius to 2, and let's continue doing the same for all the cylinders. Let's give the radius for all the cylinders as 2. Okay, so you have this now. So we've finished one particular stage in this model building process. So let's save the file. So file, save as, you want to save it as a model. So, and please try saving it in the same folder so that it's more convenient to find your models. So I'll be saving it as 4-bar bodies. So let me save it, 4-bar bodies, and I'm just giving it a suffix of class because I want to know that I've created it in this particular class. So, and then I'll just hit save. Okay, now it's time to create the joints. So we need to create 3 revolute joints. So for this, right click on the joint, okay, and change the joint type to revolute, and just click on apply twice. So this creates, if you can say OK. So now it's created the 3 joints that we want. Okay, so if you, by clicking apply, it won't close the dialog box. So that's the advantage if you want to create 3 or 4 joints at a time, then you can just go on clicking apply instead of OK, so that it doesn't close the dialog box. Now click on joint 1. So this is joint 0, which is already created. Okay, and these joint 1, 2 and 3 are the joints that we created right now. So click on joint 1, go to the connectivity tab. Here, select free body for the body 1, and for body 2, select body 0. And you got to select point C for the origin. So a joint gets created at this particular point. So one thing that's remaining is its alignment. So we have aligned this particular joint, this particular revolute joint along the global Y axis. So let's do the same thing for even this revolute joint. So global Y, it gets aligned. Now we do the same thing to create 2 more joints at this location and this location. Okay, so we click on joint 2. So here in the connectivity tab, for the body 1, let's give it as body 0, and so that's this body, and body 2 will be body 1, that's this body. So a joint gets created between body 0 and body 1. So at this particular location is what we want, so that's point E. So the origin point is point E, and the alignment axis is the global Y. And say OK. So it's got created. Let's go to joint 3 now. Let's do the same. Body 1. Let's give it as body, select body 1 here for the body 1, and body 2 is the ground body because we need to create a joint at this location. So between this is body 1 and the ground body, which is created by default. So we need to create a joint over here, and the origin is going to be point F, and we want it aligned to the global Y axis. Okay, so you can see the model that's created now with the 3 revolute joints, with the 4 revolute joints. Okay, so once the joints are created, now let's create a motion at joint 3. So at this particular location. So right click on the motion, let the names be default and say OK. So we want to create the motion on a joint. So at the location 3, so joint 3, select that. Now let's go to the properties tab, and we want to define the property by an expression. So click on the expression builder, and you can specify 1 times time, and the time I mean the simulation time here. Okay, so then hit on OK. So we've defined a motion on this particular joint, which is the joint 3. Okay, now what we'll do is we'll check our model using the check model option in the tools menu. So if you do that, if you go to the degrees of freedom, we can see that, let me just bring it up again. Here we can see that the total number of degrees of freedom of this particular system is -3. So what does this indicate? The system is having some redundant constraints, right? So the negative value indicates this. So how did we get this -3? I will show you the calculation. So please concentrate on this particular slide in the presentation. So each revolute joint, right, it removes 5 degrees of freedom. And in the entire system, we have 4 revolute joints. So which makes it -5 multiplied by 4, which is -20. And we created one motion on joint 3, which removes 1 degree of freedom. So in total, the total number of degrees of freedom removed is basically minus 20 and minus 1, which is minus 21 degrees of freedom, right? And now we have a rigid body which is of 6 degrees of freedom, and we have a free body, body 0 and body 1, which means we have 3 rigid bodies. So that makes it 18 degrees of freedom. 3 into 6, 18 degrees of freedom. So now let's calculate the degree of freedom of the entire system. It is minus 21 plus 18. That will give you the negative 3 degrees of freedom. So that's what we saw here. Okay. We saw negative 3 for the entire degree of freedom of the system. Okay. So now let's run the model. So I'll be saving it as just 4 bar. Okay. Save, and I run the model. So once the model is run, I want to review the log file. Okay. So if you just go back and review your log file, it will show you this particular warning. Okay, the row deficiency detected. So it also gives you the warning, and it tells you that this may indicate a kinematic or over-constrained model. Program will continue with redundant constraints removal. So MotionSolve takes a decision on removing some of the redundant constraints. So in that process, it might remove some of the joints, some of the constraints that are very necessary. Okay, so it gives you this particular warning in the message log. Okay, so now let's, out of curiosity, let's just go and animate the results to see what the animation looks like. Okay, so I'll slow down the animation. So this is the hyperview that it's opened, and now you can see the animation. Okay, so this is what it looks like. Now this may or may not be the right output that we want, because we haven't removed the redundant constraints. Alright, so now we go back to MotionView and try removing these redundant constraints. Okay, so in order to remove the over constraint, the middle revolute joints, what we have here, they can be replaced with an inline joint. Okay, so the ways how we can remove these redundant constraints, there's no single answer to it. There are multiple answers, and I'm just giving one answer here, and I want you guys to think about the other possibilities which are there to remove the redundant constraints in this particular system that we've created. Okay, so let's click on joint 2 here, which is this particular joint, and let's go to the drop down menu and select inline joint. Okay, so you can see that it's converted to a inline joint now. So now what happens is, the inline joint, basically it removes 2 translational degrees of freedom. Okay, so I'll show that to you in a presentation in a while. So how it removes the degrees of freedom and removes the redundancy. So I'll show you in a while how, by replacing this revolute joint with this particular inline joint, will help in removing the redundancy. Alright, so let's quickly check using the check model utility. You can see that the negative 3 degrees of freedom for the entire system is now gone, and it is 0. Okay, so this is now converted to a kinematic simulation. So how did we get that? Let's go back to calculations in the slide. So this is what happened in the background. So we have the 3 revolute joints now instead of 4 because we removed one of the revolute joints. So it is -5 into 3, which is minus 15 degrees of freedom. And we have one inline joint which will remove 2 degrees of freedom. And we still have that one motion which will remove 1 degree of freedom. So thus the total degrees of freedom removed will be -15, -2 and -1, which is -18 in total. And a rigid body will have 6 degrees of freedom, and there are 3 rigid bodies in the system. So 3 into 6 will give you 18 degrees of freedom. So -18 and +18 will give you 0 degrees of freedom, thus making it into a kinematic simulation. Okay. So let's go to this inline joint, and you can see that here the point is unresolved. So here I'll be changing it to axis, and it automatically takes it as the global y-axis, since all the other joints are along the global y-axis. Okay. So now we know that the model is kinematic in nature. So let's now run the model. And yes, before running the model, let's create outputs because we want to measure outputs now. So let's go to the output option on your client specific toolbar. It is this option here. So right click on this. So it says output 1, say OK, accept the defaults. And now let's select expressions from the drop down menu. And in the F2 field, let's create the motion function to measure the force or the torque created by this particular motion. So go to the expression builder here. Okay. So it brings up this particular dialog box. Here you have multiple tabs open. So you need to go and click the force tab. In the force tab, we have the motion option. So you need to select that. It automatically gives you the 4 arguments, right? So then you go to properties tab back again, and you open you expand the motions folder, and then you expand the motion 1. In motion 1, you select its ID string. Okay, from the list of options, and then say add. So the ID string of the motion 1, which is created on the joint 3, it gets written here, and then I can just put 0, 7 and 0 for the rest of the arguments. So what does this indicate? If we go back to the presentation, so 0 here, it represents that the force or the moment will be reported at the I marker, and we've put 7 here in the component. It basically returns the torque's Y component because we know all the joints that we have created are aligned about the global Y-axis, and here also we've mentioned 0, so it is measured about the global reference frame. Okay. So we have this, say now evaluated to check if there are any errors in the expression that you've built. So if there are no errors, it doesn't give you any warning, so just say OK. So now this is done. So now let's run our model. So click on run, and then click run option here, and MotionSolve now runs in the background and gives you the results. So the analysis is complete. So you can close this. Now what you want to do is, you've requested an output, so to see the plots you need to go to hypergraph. So you can click on the plot option here. So this will invoke hypergraph. Now you can click on this particular option, which is basically build plots. Now in the Y type you'll be selecting expressions because the output request what you've given is in the form of an expression. So you'll select this one and F2 as the Y component and click on apply. So this is what you see. So this basically gives you the torque that's generated by that particular motion. So here you have the time in the x-axis, which varies from 0 to 5 seconds, and in your y-axis you have the torque, and its units will be Newton mm. Okay, so you can now go back to your MotionView model and save it as 4-bar motion in the same folder. That's chapter 7 itself for your convenience. And this brings you to the end of the exercise 7. Thank you. Welcome back to the chapter 8 of Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. In this chapter, we will concentrate on the forces, some important functions like the BISTOP function, AZ and the WZ functions. So when you refer to the term force, it can be either applied forces or applied moments. The force elements that are commonly used in modeling in MotionView are the applied or the driving forces, the compliant connections such as springs, dampers, bushings and beams, the effect of the environment on the system like the effect of gravity, and last but not the least, the 3D contacts between the bodies. In this slide, I will highlight some important points on using different types of force entities in the MBD model. These rules are applicable to all the MBD software tools you use and not just MotionView, MotionSolve. Forces should ideally be smooth. Okay, what do we mean by this statement? This means that when you are modeling a force entity in MotionView, you must make sure that the force is continuous in nature. It is always from the solver perspective if you are solving forcing functions that are smooth and without any kinks. It's always better. So basically, the force function that you define in MBD model should not dramatically change with respect to the independent variables. Now let's move on to the force creation methods in MotionView. So I will show a quick demo in the graphical user interface. So the ways how we create a force entity in MotionView is by either right-clicking in the model browser and going to the add option and clicking on the force entity, and you can add any of these force entities. So this particular option is the force. We have the modal force, bushing, field, spring damper, beam, poly beam, 3D contact. So you can choose any of these options and say OK. The second method is if you have a pre-existing force that's already available, then you can right click on this and then just click on add force. And the third way is the most easiest way, to just add the force entities from the client specific toolbars. Okay, so just you have to right click on these icons and just say OK. So these are the 3 ways how you can create forces in MotionView. Let's go back to the presentation. So in these upcoming slides, I'll be explaining about some of the force functions that will be used in MBD modeling. I have concentrated on the BISTOP, AZ and the WZ functions since I'll be using these functions in our exercise 8. Forces can be added through expressions by using the expression builder in MotionView. Okay, now let's understand the importance of the BISTOP function and its application. The BISTOP function models a gap element. It can be used to model forces acting on a body while moving in the gap between the 2 boundary surfaces. This function can be used to limit the motion of a joint. So the BISTOP function has this particular syntax wherein the x stands for the independent variable, x dot is the derivative of this independent variable, x1 and x2 are the lower bound and the upper bound of the independent variable x, k stands for the stiffness of the boundary surface interaction, e stands for the exponent of the force deformation characteristic, C max stands for the maximum damping coefficient and D stands for the penetration. The AZ and the WZ functions are used to measure the rotational displacement and velocity respectively of marker I with respect to marker J. So these are the syntaxes of the AZ and the WZ functions, wherein the arguments are I, J for the AZ function and I, J and K for the WZ functions. So I stands for the marker whose rotational displacement is to be computed. J stands for the marker with respect to which the velocity is to be computed. And K stands for the resultant velocity vector, and it is resolved in the coordinate system of the K marker. So before we close this chapter, I would like to briefly explain the approach used by the solver to arrive at the solution. MotionSolve uses the Newton-Raphson method to compute the solution. In this method, the non-algebraic equations are repeatedly linearized at a given time step to find the solution to a system of equations. This method may not be effective if the system starts too far away from the final solution. If this happens, the integrator may report that the solution has not converged and will go back and take a smaller time step, hoping that this time it will be closer to the final solution so that the Newton-Raphson method can converge. Okay, now I'll give you a quick demo on exercise 8. Welcome back to the demo on exercise 8. In this exercise, you will add a driving torque and a torque to limit the motion of a joint to the 4-bar mechanism you built in the previous chapters. You'll also compare the results of a kinematic simulation to a dynamic simulation to help illustrate their differences. You can either reuse the model from the previous exercise or you can open the file called Chapter 8 Exercise Start in the Chapter 8 folder. So I'll go to File, Open, Model. In Chapter 8 folder, I'll be selecting Chapter 8 Exercise Start. So this is the same point wherein we had stopped in the previous exercise. So now, first let's go ahead and deactivate the motion that we had created in the previous exercise, which is motion 1. So let's deactivate this motion. So right click on this and say deactivate. Now next let's go to joint 0, which is this particular joint. And we had given some initial condition for this joint 0, which is the velocity. So let's uncheck that to remove the initial condition on this joint. Now let's create a driving force. So right click on the client specific toolbar. So let me give some meaningful name to it, called the driving torque. Okay. So here I will set the force option to action reaction, and then in the properties I'll go to the drop down menu and select rotational. So click on body 1 and I will select body 1 here. For action force on, I'll be selecting body 1, and for the reaction force on the body 2, I will keep it as the ground body. So the force I want it to be applied at point F, so at this particular location, and the local reference frame I want it to be same as the global reference frame, so I just keep it as it is. Now I'll be going to the rotational properties. So here I'll enter a linear value for the torque in the y direction as 150 Newton mm. So I've applied the torque in the y direction. So let me now save this model. As 4-bar torque. Okay, so now let's run this analysis. So MotionSolve is running in the background and the simulation is complete. So let's invoke HyperView, click on Animate, and HyperView is on the right hand side here. Click on the play button. Okay, it's too fast. Let's decrease its speed. So here we can see that we can decrease the speed. We can see that the small bar, it completes one full rotation. Okay, so this is what we observe. And it's rotating very fast because we've given it a driving torque of 150 Newton mm. So that's the reason it's rotating at a very fast speed. Okay, it's this particular small bar that you can see, it's completing one full rotation. Now pause this animation and go back to your MotionView window. Now let's create a BISTOP function to limit the motion. So right click on the forces and call it BISTOP torque. Click OK. So here you can go to action reaction for the force option, and here in the properties select rotational, and for body 1 you can select free body, and for body 2 it's ground body, and for point 1 you can select point A, so which is at this point. So we are applying the BISTOP torque at this particular location. And the local reference frame, I want it to be same as a global reference frame, so I keep it as it is. Now let's go to the rotation properties. So here you change the selection from linear to expression. So, and you go to the expression builder, and now you'll start creating the BISTOP function. So the BISTOP function is found in the general tab. Click on BISTOP, and please make sure that you use the backquotes, the right backquotes, to create this expression. It's going to be a really long expression, so make sure you watch it carefully. So first we need to go to the motion tab. So after adding the BISTOP function, let's go to the motion tab to find the AZ function. So here is the AZ function. So we add that. Okay. So once this is done, we go to the properties tab. So in the properties tab, we'll expand the joints option, and under joints option, let's expand the joint 0 and scroll down. So expand the marker I's ID string and say add. Okay, so you got that. So the AZ function or the AZ function will measure the Z angular displacement of joint 0, which is basically the first argument needed for the BISTOP function. Okay, so now let's close this particular, let's delete that closing bracket, closing parenthesis, because the expression has to still go on. Now you can leave a comma and come to the next, you can come to the place which is after one comma, and here let's select the ID string of the J marker. Okay, so you minimize this, you expand marker J and select its ID string and say add. Okay, so this gets done. So once this is done, here you can go ahead and put this in the curly braces. Okay, so this should be in the curly braces and it should be closed with this close parenthesis. Now you can go to the next comma. So the second term in the BISTOP function is the derivative of the first term. Okay, so you need to go to the motion tab again and select the WZ function, which is this. So you need to do the same thing what you did before. Okay, select the ID string of the I marker and then the J marker of joint 0. So go to properties, go to expand joints, expand joint 0, expand marker I, and then select its ID string, say add. Okay, this gets added. Now go out of this, put open and close the curly braces. Now come here, minimize this, maximize the marker J and select its ID string, which is here. Say add. So this is done. So the WZ function will measure the Z angular velocity of the joint 0 with respect to the ground, which is the second argument needed for the BISTOP function. Now you can move to the next comma. So once this is done, the third argument is basically the lower bound of the independent variable, and the fourth argument will be the upper bound of the independent variable. So for that, I'll be choosing minus 10 into pi by 180. So minus 10 into pi by 180. That's the lower bound. So I'm doing pi by 180 because the lower bound of the allowable deflection, it has to have a resisting torque that has to be entered in radians. So to convert into radians, I'm multiplying it by pi and then dividing it by 180. So 10 into pi by 180, that's the lower bound. The upper bound will be positive 10 into pi by 180. Okay. So all these should be separated by commas. So we've entered the lower and the upper bound. So the fifth argument for the BISTOP is the stiffness value, right? So you can enter 1e to the power 4, and the sixth argument will be the deformation characteristic. So you can add 2 there. So these are some of the values that are entered out of experience. So once you've once you've run the simulation and you've faced a failure, so it basically comes by experience. So these values. Okay. So first you can try to use some nominal values, and then after you get experienced, you can try using the exact values. So after entering the deformation characteristic, the last thing is to enter. So 100 is the maximum damping coefficient, and the last thing that we'll have to enter is the penetration. So that's 0.1. Okay, you see this expression is too huge. It's very easy to make mistakes here, but if you do it carefully, then we can enter the expression without any mistakes. So let's see if there are any mistakes in the expression. You can check that by clicking on this evaluated option. Okay, so this shows that there are no mistakes in this expression. Say OK, and it gets populated in the expression tab. So now you can save this model as 4-bar BISTOP. Then click on save, and now you can run the model. Okay, the analysis is complete. So let's go to animate and bring up HyperView. Okay, so click on the play button. So you should notice that the driving torque, it moves the mechanism until it hits the limit of the BISTOP torque. So we've defined positive 10 into pi by 180 as the upper bound and the lower bound as negative 10 into pi by 180. So this causes the bounce back motion of this particular mechanism. Okay, so you can pause this. Let's go back to MotionView. Now let's create an output measure for the BISTOP function. So for this, click on the output option in the client specific toolbar. Let's call this BISTOP torque output. Okay. And then say OK. So here, let's go to the drop down menu and select expressions. Let's go to the F2 field to activate it. Go to the expression builder. Now, let's create a VTorque function to measure the BISTOP torque. Okay, so this VTorque is found in the Force tab. So select the VTorque function. Now you can go to the properties. Under properties, you can go to the forces. Expand the forces. You have the BISTOP torque. You can expand that and take its ID string. Say add. The next argument for this is the J flag, which means the forces or the moments are reported either for I or J. So I will be entering 070, which means I want the BISTOP torque reported for the I marker, and 7 represents the torque component along the y-axis, and the last one, 0 value here, represents the reference marker is along the global reference frame. Okay, so you can click on evaluate it to check if your expression is right, and then click on OK. So now you can run the analysis again. The analysis is complete. So let's go ahead and plot the torque output. Okay, so go to the plot option, and this brings up hypergraph. So here in the Y type, we'll go to the expressions, and then the Y request, we select the BISTOP torque output, and in the Y component, we select F2 and hit on apply. So this is what you're supposed to see. This is the x-axis, which is the time from 0 to 5 seconds, and this is your torque value. So the bouncing effect what we saw in the animation is recorded in terms of this particular curve in hypergraph. Okay, you can stop this. You can now go back to your MotionView graphical user interface. Now let's compare this dynamic simulation with a kinematic variant of the same model. Okay, so now let's go back and let's go back and deactivate this particular driving torque. Okay, so we go to the torque option in the forces. Okay, so we go to the driving torque first, this particular driving torque, and we deactivate it. So right click on this driving torque and say deactivate, and then you right click on the motion, basically right click on the motion 1 and then click activate. So now this recreates a kinematic system for our model. So previously it was a dynamic system, but now what you did is you deactivated this driving torque and you activated this motion. So this removes another degree of freedom, so thus making the total degree of freedom of this entire system 0. Right, you can check that. You can go to tools, check model, degree of freedom. You can see that the total degree of freedom for this entire system is now 0. So thus now you'll be running a kinematic simulation. So once this is done, run the analysis. So go to the run panel, save your model as 4-bar BISTOP motion. And run the analysis. Okay, so the analysis is complete. Let's animate. So now you can see that even though the BISTOP torque has been applied, the small bar, it completes a complete revolution. So notice that the joint with this motion, it keeps moving the mechanism regardless of this BISTOP torque that we have applied here. So this is how kinematic models behave. That is, the motion driving the mechanism must be followed. Okay. So what I'm trying to say is, when it is a dynamic model, the BISTOP torque that we had applied on this end, it had an effect on the entire system, wherein we had the bounce back effect and the animation was completely different. But in this case, even though we have the BISTOP torque, but since it is a kinematic simulation, that effect of the BISTOP torque is completely disregarded. Okay. So I hope now you understand the difference between the kinematic simulation and the dynamic simulation. So now you can stop the animation. Go back to your MotionView window. And you can finally save this file as. Just want to save the model. So you can save this model as 4-bar BISTOP. Okay, so this brings you to the end of exercise 8. Thank you. Welcome back to the 9th chapter in Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. In the previous chapters, you built up a working model of the 4-bar mechanism. So in this chapter, you'll learn about the CAD import utility within MotionView environment. And you'll be finishing up with the first module, wherein you'll be able to simulate the automotive trunklet mechanism. Let's talk about the MotionView CAD import utility. So MotionView CAD interface relies on the HyperMesh CAD import engine. MotionView has a CAD import tool which supports importing from different types of CAD tools and FE formats. So MotionView has the following capabilities that can be used on the CAD geometry. So they include importing of each component in the full geometry as an individual separate part with mass, center of gravity, and inertia calculated automatically. Moving on to the second point, we also have the option to import the geometry alone without its associated mass and inertia properties. In this case, no part is created. The major advantage of using this tool is that the part or the geometry gets meshed automatically. The surfaces of the components are meshed and exported to a specified graphic file format called the H3D file format for visualization in MotionView. Each component collector is brought into MotionView as a body, and the mass and inertia properties are determined on a unit density basis, provided HyperMesh is able to create solid entity successfully. You then have the option to specify the density for each body based on which the actual mass and the inertia are assigned to the body. So the import tool also has a feature to launch HyperMesh, and you'll be able to work interactively to mesh the surfaces as chosen and select the nodes that can be imported as points. We also have the option to position the geometry in the MotionView model. Now let's discuss about the various CAD or the FE formats that are supported in MotionView model. So MotionView supports the following CAD or the FE formats. So you can import files from CATIA, HyperMesh, OptiStruct, Parasolid. So it can be a Parasolid file, or from ProE, you can import a step file, JT file, any file from SolidWorks, and UG. So now let me invoke the CAD import utility by going to the graphical user interface of MotionView and show the various options available in this particular dialog box. And switching back to the graphical user interface of MotionView. So there are two ways of importing this CAD import utility. So there are two ways of invoking this CAD import utility. First thing is to go to this file option that you can find and then go to import, and from there you can go to geometry. So this brings up the CAD import utility dialog box. This is one way of doing it, and the other way is by simply clicking on this particular icon which says import geometry on the toolbar. So if you click that option, you come to the same dialog box that you got earlier. Okay, so this is just a shortcut. So here it's divided into several sections. For example, the import option section, input output file name section, the MDL section, the meshing options for surface data section, and the locator point section. So these are the various sections in this particular dialog box. So let's see what all these options refer to. So under the import options, you have two radio buttons. So the first radio button, as the name suggests, is to import the CAD or the FE model along with its associated mass and inertia properties. So say you've built a model or you have a model in CATIA and you want to import that particular model along with its mass and inertia properties, then you'll be using this first radio button. But you'll be using the second radio button, which is only to import the CAD or the FE model without bringing in its mass and inertia properties. It will be just importing the geometries from either a CAD file or from a FE file. So these are the two options that you have available in MotionView. Next, let's go to the input output file name section. So in the input file name drop down menu, here are the different file names you can file formats you can specify to import your particular model. So these are the extra file formats that have been added in the latest version, okay, apart from the ones mentioned in the presentation. So you can select any of the particular file format, and this top folder that you can see, if you click on that, it has to direct you to the particular file that you want to import. So in this case, I've chosen the Parasolid file. So if there are any Parasolid files in the directory, then it will point to that particular Parasolid file. Once after selecting that, you can say open, and then this particular second folder that you can see is to save the file in the H3D file format. You can give whatever name you want and it will be saved as a .h3d file that can be accessed in MotionView. I hope it's clear. Next, the MDL options. So here, the first radio button is used to specify the system under which the geometry is imported, and you can give the necessary details for the body, point, graphic name, etc. So you can usually leave all these options as default under this section unless you have to specify something for a specific case. Okay, otherwise you can leave this particular section as default. So you can just minimize this and expand this based on your necessity. So now let's move on to the meshing options for the surface data. This is an important section in this particular dialog box. So if you select the first radio button, it will automatically mesh the geometry. But if you select this particular radio button and say OK, it will launch HyperMesh and you can interactively create the mesh. So if you select the first option, it does an automatic meshing. But if you want to interactively mesh by launching HyperMesh, you can select the second option. So when you select this first radio button, which allows its automatic meshing, you can also check this particular option, which controls the mesh coarseness for the contacts. And this is a very useful option when you come to contact simulation, which will be covered in chapter 11. So you need to be very careful because when you're dealing with 3D contact simulation, the two mesh geometries must have a relatively finer mesh when compared to the other simulations. So you can adjust the slider. So as from a scale of 1 to 10, if you go towards 10, you'll get a finer mesh. And if you're closer to 1, you get a coarser mesh. So the recommended value is to keep it somewhere between 5 and 6, okay, for the 3D contact simulation. Okay, so as a rule of thumb, you have to try maintaining, as I mentioned, 5 or 6 mesh coarseness. Now, if you select this particular option, wherein it opens HyperMesh for interactive meshing, then you need to be familiar with the HyperMesh environment. And also you need to have some basic idea about meshing to go ahead with this particular option. So it depends upon whether you're an MBD user or you know some basics about FEA and HyperMesh. So you can select either of these two options. Okay, so coming to the last section in this utility is it is used to specify the coordinates or the node IDs of the FEM file for positioning the geometry or the graphic. You can go ahead, you can select which coordinates you want to position it in, and you can select the node IDs of the FE file, and you can give this particular information in this section. So, but usually you can leave it as default. So after selecting all these options, you need to hit OK. So now it's throwing an error message or a warning message saying that we don't have any files that are selected. But if you've selected all the options and if you click OK, it will go to the next part of the CAD import utility. It will pop up another dialog box which will list the bodies with the volume and mass information. So you can then change the unit type for the input file from the drop-down menu and also select the bodies or a single body that you want to modify, either the density, etc. Okay, and finally when you hit OK, the CAD will be imported. Okay, so to become more familiar with this particular option, we have an exercise after this theory session. So I'll be showing that in the demo exercise. So let's go back to the presentation. So this is what we already covered. And we also covered this slide wherein I explained each of these options that are available in the CAD import utility dialog. And this was the second part of the dialog box that I was talking about, wherein after you select a particular file and hit OK, so this is what you're going to get. So in this, you can change the unit type in this option. You can also change, you can select a particular body and change its density. And please be aware that this can only be done during the time of the import of the file. You can't change its density later on during the model building process. So if you need to change any of the density values for any of these bodies that you're going to import, this is the time that you need to do it while you're importing the particular model. So now let's move on to the next part of the presentation, which is regarding curves. So curves in MotionView are mainly used as forces, motions, and constraints. So the non-linear characteristic of a force, such as spring force versus deformation, or damping force versus deformation velocity, etc., can be represented in the form of a 2D spline. Similarly, when the displacement versus time or the velocity versus time, etc., also can be represented in the form of a 2D curve. So we will now concentrate on how the curve can be used as a constraint. We will concentrate on how the curve can be used as constraint in the next chapter when I explain regarding the curve to curve joint. So once you import the curve, it can be previewed in MotionView as shown in this particular slide. So you have this option in MotionView wherein you can specify a particular relationship between two entities using a curve. So you can have an Excel file having the X and Y values, and you can import that particular file, .csv file, into MotionView. And before moving forward with your model building process, you can check if you've imported the right curve by previewing, by clicking on the preview button that you have on this particular panel. You can preview the curve before moving forward. Okay, so I'll be showing that in the demo video that's there today. And one more important feature in MotionView is that you also have the option of importing a 3D spline as well. Not just a 2D spline, we can also import a 3D spline as well. Okay, which is basically a graph that contains the data in the X, Y, and Z coordinates. So here you can say, you can give an example of a plot that has an RPM, engine RPM, versus the frequency versus the cylinder pressure of a particular engine. So you can take that as an example and you can import that when you're trying to simulate a single cylinder working, single cylinder of an engine that's moving up and down, the piston moving up and down. So you can import a 3D spline which has the data in XYZ format for the RPM, frequency, and the cylinder pressure. So the curves panel, it allows you to add and edit curves, and the X and Y data vectors for a single curve can come from any of the sources such as file, a math, or values. So for example, the X data vector can come from a file and the Y data vector can come as a mathematical function of X. So you have that flexibility in the import spline utility. Okay, so here this is what I was talking about. So when you have when you select the X option, the values where you have to input as the X values, then you can go to the drop down list and you'll have further options. Maybe I can show that in the graphical user interface so it's more clear. So let me go to import import curve. So this option that you see on the screen, let me cancel this. So this option that you can see on the screen is to import a curve. Okay, so I'll say okay. The X values for that curve can either come from a file, as I mentioned, like a .csv file, an Excel file, or it can also be in the form of a mathematical expression, or you can just put X and Y values here. So what I'm trying to say is you can try to get the X values from either a file, math, or values format, and Y values need not necessarily be from the same source. So you can give this as, say, a file. You can import the X values from the file, and the Y values can be imported by giving a mathematical expression to create a function between the X and Y. So these are the flexibilities that you have while importing a curve in Motion. So in this slide, I'm trying to cover the interpolation or the extrapolation functions using curves. So since the data in a curve is at a discrete point, okay, a function must be used to either interpolate or extrapolate the data for times when there is no direct data available at a point in the curve. So the interpolation can be done either by using Akima or the AKI SPL format, or the cubic, that is, it's specified as CUB SPL, or the quintic QUI SPL interpolation methods. So these are the three interpolation methods that are available in MotionView. So these functions are supported in MotionSolve expression language. So now I'll try to explain each of these in detail. So both the Akima and cubic use cubic polynomials to perform interpolation, but differ in many ways that you need to know. You need to understand the difference when you'll have to use a Akima interpolation or when you'll have to use a cubic interpolation. Okay, so I'll get into that in a few seconds. So the Akima fitting algorithm, it uses local methods to calculate the spline coefficients. So here in this case, when you talk about the mathematics behind the Akima curve fitting, so no matrices are ever inverted. So for this reason, it is preferred when the reference spline that you have has many data points. So try to use the Akima interpolation method when the X and Y, or the 2D spline or the 3D spline that you're creating has many data points. If it has very discrete data points, then try to refrain from using this particular method. So the main disadvantage of this method is that it has non-smooth derivatives, especially when the data points are not equally spaced. So the Akima method consequently must never be used for interpolating motion data. On the other hand, the cubic fitting algorithm, it ensures a much smoother fit by utilizing natural splines. Okay, it is much better at calculating derivatives of the resulting spline, but it has its own disadvantage. It is not good at modeling sharp corners in the data. Okay, for splines with two independent variables, such as the 3D splines, the interpolation along the second independent variable is always linear, regardless of the choice of interpolation along the first independent variable. So the interpolation or the extrapolation algorithm that you need to use is completely application dependent. So I have tried to use some of the the best algorithms that can use in a couple of cases, but you'll have to explore if you're building an own model, then you'll have to explore which particular interpolation method suits the best for your model. Okay, so it's totally application dependent. I'll be explaining about one of the functions that we'll be using in this particular chapter, in this particular exercise demo. That's the dx function. So this dx function, it computes the x component of the relative translational displacement of marker I with respect to marker j as resolved in the coordinate system of marker k. So the syntax for this particular dx function is dx, and the arguments will be I vector, j vector, I marker, j marker, and the k marker. Okay, so the I marker, it is the marker whose displacement is to be computed, whereas the j marker is the marker with respect to which the displacement is to be computed. So this argument is optional, okay, and it can be omitted if it defaults to the ground coordinate system. And the k marker is a resultant displacement vector, and it is resolved in the coordinate system of k marker. Okay, so this, if it is omitted, then again it defaults to the ground coordinate system. So this is the syntax for the dx function. I think it will become more clear when I try to explain this function when I'm using this in the exercise demo. Okay, now let's move on to the HyperView collision detection algorithm. So in this chapter, we'll try to simulate the automotive trunk-lid mechanism, as I mentioned earlier, using the 4-bar mechanism that we have built so far. So this is the first module that will be using all our basic knowledge that we have learned so far, and we'll try to stitch that together and use it in this particular exercise demo. When we simulate this model in HyperView, it allows you to view and detect the collisions between the graphic objects of the current animation model during simulations. This is a very special capability that is present in HyperView, and we'll be making use of this in our exercise demo. So in order to activate this option, you need to do the following. Just follow, I'm going to switch back to the graphical user interface to show that. So from MotionView, I'll be switching back to HyperView. So in order to have that option enabled, for me, it's already available on the screen because I've already enabled it, the collision detection icon. But if it is the first time, you won't be having this icon on your screen or on your toolbar. So in that case, you have to go to View and then go to Toolbars and then go to HyperView, and you need to enable the Tools option. So you can see that if I disable this, that particular collision detection algorithm icon disappears from the toolbar. So you need to go to View, Toolbars, HyperView, and select the Tools option to get collision detection algorithm icon on your toolbar. So now let me try to explain the different options available in this collision detection algorithm. So there are 4 important things that you need to know in this particular panel. The first thing is the collision sets. So the collision set is defined for a current model in this particular section. Okay, and then the next section of this panel is the selection. So you'll be selecting the components which you need to add to the group A and group B. And then it is the proximity section. So if you enable proximity, it will allow the objects to get detected at the distance that's specified as the minimum distance. Okay, and then you have the animation event section. So this is to control the animation that will be running on the screen. Okay, so let me explain each of this one by one. So a collision set is activated or deactivated using the radio button. Okay, so here you need to come, and if there is if you've imported a particular result file on your screen, so you can go ahead and select any of that and go and add it to group A. So you can go create because now it's not creating anything because we don't have any component on the screen or any results that are available on the screen. So you need to go, for example, for the automotive trunk lid mechanism, the body in white structure of the car will be added to group A, and you can add the trunk to the group B. Okay, once you do that, you can enable proximity checking, this particular option. Okay, so it allows the objects to be detected at a distance specified as the minimum distance. So if you say, hey, detect the collision 1 unit before the collision or 1 mm before the collision, so it will do that. So you can vary this particular parameter. Okay, and then the next radio button is show the results by elements or components. So the difference in this, I think it is better when you visualize this. So I'll just try explaining this now. So when you select elements, it will try to show the elements that come into contact. So when 2 objects come into contact, the elements that are associated with those 2 geometric bodies will be highlighted as red if you select this option. But if you select the components option, then the elements that will be placed in that component, if the trunk lid geometry, it belongs to the trunk lid component, then the entire geometry will get highlighted. It's not just the elements that will be in contact, but it will be that entire component that will be highlighted in red. So that's the difference. I think it will become more clear if I show an animation on the screen. So I'll be doing that in the exercise demo. And next thing is the animation event. So here they have in the drop down menu, you have two options: to ignore collision and to stop on collision. So this means, so when you're trying to simulate the particular mechanism, and if there is a contact, so even if you've chosen ignore collision, it will still continue doing the same simulation even after the collision has happened. If you choose the second option, stop on collision, then it is going to stop when the collision occurs. Okay. So this is the basic idea of the collision detection algorithm. Okay. Now let me go back to the presentation. Okay. So this is what I explained. So, and I think I'll put a picture on the screen. So this is what I was talking about. If you've selected elements, then only these elements, wherein this is the trunk lid and this is the body in white structure of the car. So only at the locations, elements that come in contact with each other, you see it's being highlighted in red, like at this location and at this location. But if I had selected the components option, this entire trunk lid would be red in color. Okay, the whole thing would be highlighted. Welcome back to the demo on exercise 9. We'll be completing the model building for the 4-bar mechanism, and we'll be attaching it to the BIW structures of the automotive passenger car, and we'll be also importing the CAD for the trunk lid, and we'll be trying to simulate the automotive trunk lid mechanism. So here, this particular link is called the follower, the second link is called as the coupler, and the third link here is called as the input link. Okay, so we'll finish our model building process and then import the CAD and attach this particular 4-bar mechanism to our automotive trunk lid. Okay, so let me go back to the graphical user interface. So here you can either reuse your model from the previous exercise, or you can go to File, Open, Model. So let's go to Chapter 9 and let me import this particular file. So this is nothing but the file where you had stopped in the previous exercise. So either you can use the same model, or you can import this model, which starts at the beginning of basically imports the end model that you've built in chapter 8. Let's continue finishing the 4-bar, building the 4-bar mechanism. So you'll have to create 3 new points using the points panel. So let's go and add. So I'll be naming these points as point G, apply. I'm clicking apply because I want this dialog box to remain open, because I'll have to create 2 other points. Then point H and then point I. Say OK. So you can see that in the model browser, you will be getting these 3 points. So once you're done with that, go to point G, and in point G, X coordinate, you can give A30, and the Y coordinate, it is 580, and the Z coordinate, it is 1080. For point H, it is going to be 790 in the X direction, 580 in the Y direction, and 1088 in the Z direction. And for the point I, going to be 825 in the X direction, 580 in the Y direction, and in the Z direction 1009. So we've given the coordinate values for the X, Y, and Z for these points: point G, point H, and point I we just created. Okay, but you're not able to see anything on the screen. That's because you need to fit the screen. So just click on your graphical user interface and press F on your keyboard, and you can see the points that you've created. So these are the points that you've created. Now go back to the graphics icon on your toolbar, and then you need to create a new cylinder that are fixed on the body 1 from E to G, and then from G to H, and then from the point H to I with a radius of 2. Okay, so let's get started. So let's first create 3 cylinders, and then we'll give its connectivity. So cylinder, let be default like this, say apply, apply, and OK. So you got 3 cylinders here. So this cylinder I want it to be between, they all need to be fixed, okay, on the body 1 from E to G. So parent body will be body 1, and then it will be from point E to point G, but its radius should be 2 mm. So you have that now. Next, let's go to cylinder 1, go to connectivity tab. Its parent body is again the body 1, and it is going to be connected from point G to point H. So that's this. So go to properties and change the radius to 2 mm. And if you're getting confused between which body it is, the parent body of this particular graphic, then I've defined as body 1. So just click on body 1, it will show you. So this particular body, so all these graphics will be associated with this body. Okay, that's body 1. Okay, now let's go to the last cylinder, give its connectivity. So the parent body for this will also be body 1, and then the origin will be from point H to point I. So you have that, and you can go to properties and change the radius to. So now we have all the cylinders or the graphics that are connected. Okay, so it should appear, your model should appear somewhat like this. So now what you've got to do is you need to move the center of mass of this body, which is body 1, from point 4 to point G. So let's go to body 1. So when you click on the model browser on body 1, it brings up the panel of this body. So you need to shift the center of mass of body 1 from point 4, which is currently this particular point is at point 4. You need to shift it from that location to a new location, point G. So let's go to center of mass, and in origin you can go to the point. You can just double tap on this point option, and from instead of point 4 you need to select point G and say OK. So you can see that the center of mass has shifted here. Maybe now let's go back, and in order to visualize this, let's make it transparent. So this is the graphics window here. Let's select this cylinder 0, cylinder 1, and then try making it transparent. So this option to make it transparent. So just for you guys to see how the body's center of mass has moved from this point 4 location to point G. I hope now you can all see it, right? Because I made it all transparent. So I prefer keeping the model like this because I know what's happening in the interior of the model. Okay, so now let's do this. Let's go back to the torque. So I'll minimize this. So that should be in under forces. This BISTOP torque that we've created, you need to deactivate it. So it's already, grayed out, which means it's already deactivated. So you can see that it's already deactivated. So you can just activate it. So instead of activating it, you need to deactivate. Okay, so you need to deactivate the BISTOP torque. Okay, and right click on the driving torque also, which is this torque that you've applied, and also deactivate that. So basically you'll be deactivating both the BISTOP torque as well as the driving torque. And now you need to specify the motion for the mechanism. Okay, so the motion for the mechanism that we'll be specifying, it will be in the form of a 2D spline. Okay, so the motion can be either linear, you can give an expression, you can give a curve, or a 3D spline. And we are trying to use the case of a 2D spline and give the motion for this particular mechanism. So from the project browser, you can right click, say add a reference entity, and from that you can go to curve, or you can simply go to this option on your toolbar. Okay, so you just go ahead and add a curve. So leave the names as default and say OK. You move your radio button to the X values here and click on this file option. So in the model files, you'll already have this particular file called as the motion curve. So click that CSV file and say open. Okay, so you can see that it is attaching the particular CSV file that's been created in Excel. So this X, so you have in this, let's go ahead and see what's there in this particular CSV file. It will open up Excel, so that it has two columns. These are the X values and these are the Y values. So if you go back, the X values will be associated with the block 1, column 1. Okay. And the Y values should be associated to block 1 but column 2. So just make these necessary changes so that it knows what to consider as X values and what to consider as Y values. So once you've done that, you can go to show curve option here to preview the curve that you've just imported. Whether it's imported the right X and Y values. To confirm that, to double check on that, you can go to the show curve option and you get this curve. So this curve looks good. Close this. Now what we'll do is we'll select the motion 1 that we had created. Let's go to motion, and we have created a motion 1, nothing but this motion on this particular revolute joint, right? So let's go to its properties. We'll try to assign the curve that we have just imported to this motion. So let's go to properties and then define by, instead of expression, I'm going to select curve. And I will be selecting the curve that I just created. So if you just double tap on the curve option, this is the only curve that's there in the model. So it brings up this option. So select curve 0 and say OK. Okay, so now that's done. And you can leave the rest as it is. So, and then you can just save your model at this point. So file, save as model. So you can call this for power mechanism. So I'm just calling it class and then save. Okay. So you saved this particular model. Now let's start renaming the bodies. Okay. As you had seen in this particular presentation, this link is called as follower. This is called as coupler, and then the input link. Let's try to rename this model by giving meaningful names. So now let's go to the bodies. You can right click on the free body and then click on rename. So, and you can rename it to follower. So this body here is associated with this link, which is nothing but the follower. And then the body 0 can be renamed as coupler, which is nothing but this body. And this entire body whose center of mass is at this location is input. Okay, it's the input link. So let's rename it as. Now, once you've created all this, it's time for you to create outputs. So you can create outputs on bodies, points, joints, and markers. Okay, you can also directly request for the force, bushing, and spring damper entity outputs. So another way to create the outputs will be using mathematical equations. Right. So in this step, you'll be adding a displacement output between the two bodies using the default entities. For this, let's go to project browser. So this is your project browser, and you right click on your model, say add, and go to general MDL entity and then say output here. Okay, so you'll be creating outputs. So once you do this, you can leave it default. Okay, and so just say OK. So once that's done, you need to create a displacement output between the 2 points on the bodies. Okay, so for body 1, so you can select the input, and for body 2, you can select the ground body. You're trying to measure the displacement of the input body with respect to the ground body. So that's what this means. So okay, the point on body 1 option. So you can select point I, and for the point on body 2, you can select the global origin. So it needs to know from what point will be taken as the reference. And then in this option, you can leave it as both. So next, we can go ahead and add another output. So this was one way of adding the output. The other way is directly clicking on this option on the toolbar, which will allow you to add the output directly. So right click on this. So it's the next output, okay, that you're trying to measure. So in this, say OK. You can accept the defaults and say OK. And this time we'll be trying to input an expression. So we'll be choosing the expression option from the drop down menu. Okay, once that is done, in the F2 field, so this is where we need to go. This is the F2 field. Click on this. This is the expression builder, and we need to build the expression. So you can delete this 0. So these are the codes in between which you need to enter the expression. So that's fine. Now let's, so what expression do you want to use? So I think if you just rewind back and go back to the theory of this class, you'll get to know that I told that we'll be using something called as the dx function in the exercise demo. So that's the function I'm going to use here. Okay, so let's go to the motion tab, click on the dx function. Okay, and from the properties tab, now that's the function name, and now we'll be trying to input the arguments inside this bracket, okay, for this dx function. So let's in the properties tab, go to the bodies, okay, expand bodies, and in bodies go to the ground body and then select its center of mass. You can expand the ground body. In the ground body, center of mass marker, okay, so it is nothing but this marker's string ID or the ID string. Okay, so we need to add that here, so you get this, and then you need to input the ID string of the center of mass of the second body. So this was the ground body, right? Now you need to do that for the second body. So go to put a comma, come out of this parenthesis and put a comma, and then open two other parentheses, and in between these two parentheses try to do the same thing. So this one you expanded ground body, but this time it will be the input body. Okay, so you can minimize this, go to the input body and then go to its center of mass and then get that ID string. So you added that now. So after doing this, click on OK, go here. So you've got this expression that's you've been added here. So in order to check if there are any errors in your model, you can go to tools and check model and see what it says in the dialog box. So it says finish checking models and you haven't got any error message. So your model looks good. Say OK and close. And you've got the IDs of the center of mass of the ground body and the input body here. So now it's time to import the BIW models for the car and the trunk lid. So for this, we'll be going to import geometry menu. So you can either go to File, Import, Geometry, or you can just directly use this shortcut on the screen. So here, please follow the steps very carefully. So you need to import geometry. So select the second option because I want to just import the CAD. I don't want to import the mass or the inertia associated with it. So I'm going to select the second option. So once that's done, here I'll be selecting HyperMesh. So I'm going to import an FE file. So I'm going to select HyperMesh, and then in this, the input file, I'm pointing it to trunklid.hm. So .hm is an extension for an HyperMesh file. So it's in this particular working directory. Say open. So it gets loaded in, and the output file I want it to be saved as. You can change it. By default, it takes the same name. You can also change it to say something like mytrunklid.htd. Okay. Say save. So once that's done, just click on this option. You can leave it to allow HyperMesh to mesh it automatically. So you can leave it to 5. If you check this, it will go to 5. But if you uncheck this, it will select its own coarse roughness, coarse mesh size. So for this particular simulation, you can allow it to have coarse mesh size. So you need a fine mesh size only when you come to 3D contact simulation. So then just say OK. So if the import is successful, you need to get a message saying your import is successful. Okay, so you got that. Importing the file succeeded. Okay, so you can close this. So you can see that the automotive trunk lid, which was already created, it got imported here. And the reason I created the hard points here, so you might be wondering why I created these hard points at these specific locations. That's only because I didn't want to change it after I imported this. I didn't want to position this the HM file after I imported it. Instead, I wanted to create this at the right location. So that's the reason why I input these numbers. Okay. So when you're trying to build a model from scratch, then you have to experiment and get the right location of this CAD based on where your input model is. Okay. So once you've got your trunk lid here and there were no importing errors. Okay. So just follow the message log very carefully. Okay. Now let's go to the graphic option here. So you have this. Okay. You need to select this. So if you go to this option on the project, on the project browser, you can go to connectivity tab. And if you go to the connectivity tab, you can see that the model is imported, but it is not connected to anything. It seems connected on the screen, but still in reality it is not connected to anything. So you need to basically connect it to a particular body. So here in the body, double click on body option and then click on this trunk lid. It should be attached to the input of the 4-bar mechanism. So select this and say OK. So now it gets attached to that. Now let's do the same thing for importing the BIW of the car. Okay. Now I'll be using the shortcut option, which is the to invoke the CAD import utility. I will be importing just the FE model, okay, without importing its mass and inertia properties. So, and then I'm going to open this. I'm going to import this. Okay, this is the BIW of the car. Say open, and maybe you can save this as the HTTP file, my trunk graphic. Okay, so say save. You can leave this to default and say OK. So that got imported and there was no issue while importing. So just follow this message log. So once this is imported, again, you can go to the BIW of the car. You can see that it says it's unresolved, which means it's still not connected to anything. So you got to go to body and connect this to the ground body. The trunk was connected to the input follower. This one, which is the BIW of the car, is connected to the ground body. So once this is done, you can save your, so you try saving your models at every major step, because if something happens then recovering the file will be a problem. So it's a good practice if you can try saving your model at every step so that you can keep a track of it. So I'll just call this as 4-bar mechanism. So with the trunk lid. Okay, so I'll just save it like this. Okay, now let's go and simulate the model. Come to this run option here. Okay, and the end time you can keep it as 4 seconds, and you can leave the print interval as it is. So here you can save the model as trunk test. So let's just test the model. So I'll just call this as trunk test something, and then go to save. Okay, so once that's done, you can go to the run option. Okay, let's see if there were any error messages. It has run successfully, so you can close this and then you can go to animate. So this brings up your hyperview. So one more thing that you got to notice is in MotionView you could see this 4-bar mechanism that you've built, right? If I go back to this, let me fill this to screen. So you can, and let me try to make this transparent so that you can see the 4-bar mechanism. If you zoom in, if you keep zooming in, you can see that the 4-bar mechanism that you created. All right. So that was created only using the primitive geometry. So that's the reason it's not shown in hyperview. Okay, but that does exist. The 4-bar mechanism does exist here. Okay, so let's go back to hyperview and then you can hit on play. Yes, so now you can see that this trunk lid, it is going beyond this, right? Beyond this particular location. So in reality, it is supposed to stop when this section here meets the BIW of the car, but the way you define it, it's going beneath that. So that's the reason, that's one of the assignment questions that I'll be giving. How can you restrict the motion of this lid to stop exactly when it collides? Okay, that is something using the collision detection algorithm. It's very easy. As I mentioned in my theory class, you can give an option saying in hyperview, stop on collision. So as soon as this lid meets the BIW of the car, there is a collision and hence the animation stops. So that's just the, for the crude way of doing it, but you can alter many things. You can either play around with the BISTOP function or the CSV file that you used to import the motion. So this is basically doing this because of the motion that you get. So you can either play around with that and make this trunk lid stop exactly when it meets the BIW of the car. So let's go back to MotionView. Let's stop the simulation here and go back to motion. So I hope it's all clear. So this basically brings us to the end of module 1. So using all the fundamental knowledge that you've learned so far, you could finally build the automotive trunk lid mechanism. So now let's do one thing. Just to confirm if we got the right curve imported and if the motion is making sense, what we can try to do is to plot that result, okay? Because we've requested output, so we can try to plot it, okay? So let's go to hypergraph, okay? So you got your hypergraph here. So here you can choose marker displacement, and then you can choose this particular option on the input link, okay? For the component, you can choose dm, which is the magnitude of the displacement. Say apply. So this is your displacement of the input link with respect to the ground body, okay? So this is how it looks like. So this means that you've done the simulation in the right way. So the maximum displacement is around 1545 units, okay? So if it's in mm, then it's in mm, so it's like 1545 mm. Now let's go back to MotionView and expand this. So now it's the time to go to HyperView and check how the collision detection algorithm works. So let's try to do that. Let's expand this. So I'll click on this icon. So I think I've already mentioned this in my theory class. If this icon is not already present, then you need to enable this by going to View and then going to Toolbars and then Hyperview and then clicking on Tools. So this will bring this icon on the toolbar. Okay. So before going to that, I want to show you one thing. You don't see any mesh right on the screen, but actually it is meshed. So to visualize that, you can go to this particular option, which is the graphics option, and just say all. So it selects the entire thing and click on this. So this is the automatic meshing. It's done, but this is how you visualize it. So usually it will be switched off. It will be, in this particular, so you select everything, say all, this option here. So you can't see the mesh, okay? So if you want to activate it, in the sense, if you want to visualize it, then you have to go and click this particular option. So now let's go back to collision detection algorithm. I did this because I want you to see the difference when you say in proximity section, when you select elements, what happens, and what happens when you select components. To make it very clear, I've made this particular, I've got this particular visualization for you guys. Okay. So the way how it works is you need to add a collision set. So to this, I'll be selecting this trunk lid and adding it to group A, and the entire structure of the car will be added to group B. Okay. Once this is done, you can enable proximity and you can say minimum distance can be 1 mm. So once you say this, say apply. Now you can play the animation. So now the radio button is selected to components. So what happens here is this trunk lid, as it goes and meets the BIW of the car, you can see that the whole thing turns red, okay, because the components are selected. Now see what happens. Observe very carefully what happens when I select elements. So go to this particular radio button and say apply. See what's going to happen. So only the elements that come in contact will get highlighted. So I'll try to zoom in so you can see clearly. So only at these locations and these locations, so it gets highlighted. So this is what happens between when you select elements and then components. And one more thing is here in the animation event, you have these options. Okay. If you say ignore, if now by default it is ignore collisions. That means even after the collisions happen, still it is continuing to do the simulation. So see what happens if you select stop on collision. So as soon as it collides, it's going to stop. Okay, it's not going to further do the animation. Now if you select stop on proximity violation, okay, let me select this and simulate this, and then see what happens if you when you select stop on proximity violation. So as soon as this particular condition here is violated, okay, when the minimum distance becomes more than this, it stops the simulation. So that's the use of this animation event. So I hope now this collision detection algorithm is clear for all of you guys. Okay, if you have any doubts, we can discuss that in the support session. So this brings you to the end of module 1, where the end result was to create an automobile trunk-led mechanism by using the 4-bar mechanism that you built so far. So I hope now it's clear to you all by using the basic knowledge that you learned till chapter 9, how you could finally use that and build a pretty, it's basically switching from a beginner level to an intermediate level. So this is where the transition is happening. You used all those tools that you learned so far to come to this point wherein you finally simulated the automotive trunk lid mechanism. Let's go back to MotionView. You can enlarge this. You can save this final model. So please save this model because you have, as I mentioned, you have an assignment on this. So I'll be sending that assignment in the form of a presentation shortly. So, and if you have any other doubts, we'll be discussing that in the support session. Thank you. Welcome to the 10th chapter of Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. So in this chapter, we will take a deep dive into the constraints and mainly concentrate on the higher pair constraints. So now let me take you quickly through the different types of constraints available in MotionView, MotionSolve. So we have the lower pair constraints. A lower pair constraint is basically an ideal joint that constrains the contact between a point, line, or a plane in the moving body to the corresponding line or a plane in a fixed body or another moving body. So these have physical analogies, and for example, a revolute joint can be correlated to a hinge joint. So then you have the joint primitives. They constrain combination of individual degrees of freedom between the bodies. In most cases, there are no mechanical equivalents for the joint primitives. Moving on to the higher pair constraints. Generally, a higher pair constraint is the one that requires a point, curve, or a surface in moving body to maintain the contact with a curve or a surface in the fixed body. Motion is a prescribed displacement, velocity, or acceleration on a body along a specified direction. When motion is applied on a body, the free degrees of freedom of the body are replaced by prescribed movement as specified by the motion. So thus, motion falls under the category of constraints. And the other constraints include the coupler or the gears. So here, they're used to specify algebraic relations between two or more joints. So as you can see on the screen, the classification of constraints, there are the various types of constraints available in MotionView, MotionSolve. And we've already gone through the lower pair constraint and joint primitives in the previous chapters. And in this chapter, we will be concentrating on the higher pair constraint. So we have the following higher pair constraints: the point to curve joint, point to surface joint, curve to curve joint, curve to surface joint, surface to surface joint, point to deformable curve joint, point to deformable surface, and a constraint mate. So let us start with the point to curve joint. So a point to curve joint is a higher pair constraint. This constraint restricts a specified point on a body, as you can see in the animation on the screen, to move along a specified curve on another body. So this hammer-like structure that you can see, it has a particular point that is resting on this curve and it is moving along. So the curve may be open or closed, planar or in 3D space. The point may be a rigid, flexible, or a point body. So this constraint can help in avoiding the 3D contact modeling, okay? Because the 3D contact modeling is very time consuming and it involves many complex equations. So you can use this particular point to curve joint in some of the cases to substitute the contact modeling. So it may prove advantageous since the proper contact modeling in many cases involves fine-tuning of contact parameters. And one good example for that is the knife edge cam follower mechanism. So in the left hand image, you can see a robotic arm. So this is another example of the point to curve joint. So, and on the right hand side, it is there's an example of this hammer-like structure moving along this particular curve path. So in the left hand side image, so this is the robotic arm trying to move along this particular curve that's been prescribed by the user. Okay, so these are some of the examples of point to curve joint. Now let's move on to the next slide. So this slide it gives us a brief description of the point to surface joint. A point to surface joint, also called as the PTSV joint, also falls under the category of higher pair constraint. This constraint restricts a specified point on the body to move along a specified surface of another body. Okay, so in this slide, you can see that this needle-like structure is, say, a body I, and this irregularly shaped structure is body. So it will allow this particular needle-like structure, the tip of this needle, to move along a particular trajectory on this body J, the surface of body J. So the tip of this body I moves along a prescribed path on the surface of body J. So in this case, we can define a point to a point to surface joint. So the next one is a very important joint, which is the curve to curve joint. So curve to curve joint is a higher pair constraint, and it's a constraint. This constraint consists of a planar curve on one body rolling and sliding on the planar curve of a second body. So this constraint can act as a substitute to the contact modeling in many cases. Okay, so this will eliminate the complex formulations of the contact model and thereby making it much easier for the solver and also reducing the run times. So one such case is a cam follower mechanism, so which is showed in the next slide. So in this case, the follower is in the form of a roller. So instead of modeling the contact between the cam and the follower, we can specify a CVCV constraint between their curve profile. We can go on to the next slide. So here, one thing that you need to note is the curve to curve constraint removes 3 degrees of freedom from each of the systems. Okay. So when the body of the first curve, let's move on to the next slide. So when the body of the first curve is in space, the second curve is allowed to move in 3 ways. Okay. So say this is the curve profile of this roller is the first case. So in that, so consider when the body of the first curve is in fixed space, the second curve is allowed to move in 3 ways. It can slide along the first curve, it can roll along the first curve, and it can rotate above this common tangent that you have. Okay, if you have this roller in the form of a curve, the path of this roller in the form of a curve, and the path of this cam as another curve, then you can see you have a common tangent between the roller and the cam, right? So it can rotate about the common tangent at the point of contact. So these are the 3 degrees of freedom that are removed. So the curves can thus rotate about the common tangent at the point of contact, and therefore it can move out of the plane even when both the curves are planar. So I think this becomes more, this will be more clear to you guys when we do the exercise demo on chapter 10. Let's move on to the slide 8. So this is basically the curve to surface joint. This joint is used in very rare cases where the curved region with a very small thickness of a body A interacts with the surface of body B. In these cases, we use the curve to surface contact. It is basically the interaction of the 2D spline with the 2D plane. So now let's move on to the next slide, which is the surface to surface joint. So if we want to constrain the surface of one body with the surface of another body, this constraint can serve as a very good substitute again to the 3D contacts, which can increase complexity and so this will help in decreasing complexity and simulation time. So we can use this constraint to calculate the friction losses between the two bodies that have surface to surface interaction. Now moving on to the next slide, it is the point to deformable curve constraint. It's also called as the PT-DCV constraint. So it again falls under the category of higher pair constraint. So this constraint restricts a specified point on the body to move along a specified deformable curve on another body. The curve may be open or closed, planar or in 3D space. So the point may be a rigid, flexible, or a point mass. So we can consider the example of a long stick supported by revolute joint at both of its ends, and a ball or a mass is constrained to move along this particular stick with a PT-DCV joint, okay, with a point to deformable curve joint. So here what happens is this long stick can act as a slender beam. So that can be the deformable curve, and this point mass, it moves along that curve. So please note that this type of constraint does not always ensure that the contact point between the two bodies will always stay within the range for the specified curve. So additional forces at the end need to be defined by the user to satisfy this particular requirement. So if the contact point goes out of the range of the data specified for this particular curve, the solver encounters an error. So the solver is going to throw an error saying that this particular simulation cannot be converged. So in that case, one has to basically change the initial velocities for the ball, okay, or increase the range of the data specified for the curve, or run the simulation for a very short interval of time. So these are some of the workarounds that we can do to get this particular constraint running. Point to deformable surface constraint. So the point to deformable surface is a higher pair constraint that restricts a specified point on a body to move along a specified deformable surface of another body. So here you can consider the example of the ball or the mass, okay, on a sheet of paper, okay, that's constrained on two ends. So the sheet of paper acts like a flexible body on top of which the ball is resting. So if this constraint here is applied, as and when the ball moves on the deformable sheet of paper, the z displacement of the ball can be calculated. So again, this can serve as a very good substitute for the 3D contacts involving flexible bodies. So that will be explained in the next chapter, wherein I cover the 3D contacts. We in MotionView, we do not have the 3D contacts established for flexible bodies. So in that case, this particular constraint can serve as a very good substitute. So in this particular slide, we've tried to summarize all the constraints that we've studied so far. And you need to note that in the higher pair constraints, the two bodies are in contact at a point or along a line, and the relative motions of these coincident points are not the same. So this is just a summary of what all we have covered so far. So this slide here explains quantitatively the number of translational and rotational constraints that can be eliminated by using each of these higher pair constraints. Okay, so a point to curve constraint, it removes 2 translational degrees of freedom and 0 rotational degrees of freedom. So totally this point to curve constraint has the ability to remove 2 degrees of freedom. The point to surface constraint can eliminate 2 translational degrees of freedom and 3 rotational degrees of freedom. So totally it can remove 5 degrees of freedom. The curve to curve constraint, it eliminates 2 translational degrees of freedom and 1 rotational degrees of freedom. So in total it can eliminate 3 degrees of freedom. The curve to surface constraint can eliminate 2 translational degrees of freedom and 3 rotational degrees of freedom. So in total, it can eliminate 5 degrees of freedom. The surface to surface constraint can also eliminate 2 translational degrees of freedom and 3 rotational degrees of freedom. Hence, it can totally eliminate 5 total degrees of freedom. The point to deformable curve constraint eliminates 1 translational and 3 rotational degrees of freedom. So thus eliminating 4 degrees of freedom. And the point to deformable surface constraint totally removes 2 translational plus 3 rotational degrees of freedom. So in total removing 5 degrees of freedom. So this slide basically gives you the quantitative information on the number of degrees of freedom that can be removed by each of these higher pair constraints. So in this slide, I'll be explaining regarding the demo that we'll be doing in exercise 10. We'll be modeling a cam and then the follower. The follower is resting on this cam and it is attached to a follower shaft which reciprocates as cam performs its rotation. Okay, so this constraint again can act as substitute for contact modeling. So instead of creating a 3D contact between the cam follower and the cam, you can try to use the profile of this particular cam. You can capture that as a curve, a 2D spline, and also capture the path along which this cam rotates. You can take that path as another curve, and you can try to establish a curve to curve joint between these two profiles. So this totally reduces the runtime and also the complexities of the equations that are involved in formulating it. So this is something that we'll try to simulate in the exercise 10. Thank you. Welcome back to the demo on chapter 10. You will start this tutorial with a partially built model. The points, bodies, graphics, and the joints are created for you already. So you need to create the curves and the curve to curve constraint. So let's get started. So let's open the file from model files that are available. So go to chapter 10 and you have the cam follower constraint start.mdl. So double click on this and this imports the model. So you'll be getting one more assignment in this particular chapter, wherein you'll be asked to replicate this model and basically to build this model from scratch. Okay, I'm using this partially built model in order to save time, but you guys will be doing this particular demo. You'll be practicing it once I'll be showing it to you by building this model from scratch. So before we get into the further model building, let's explore what all this model already contains. So it has 4 bodies. One is the default ground body, and then you have a cam, so which is this particular green graphic that you can see, and then you have a follower shaft, which is this rectangular piece, and the body, the center of mass is right here, which is, as you can see, it is highlighted on the screen, and then you have the follower roller, which is at this location. So these are the different bodies that are used, and you have these are the various graphics that are used: the graphic for the cam, the graphic for this follower shaft, the follower roller, and some other small graphics like this is the cam pivot graphic. So you have another bolt that goes inside, which is represented by another graphic. So that's another cam pivot graphic, and then the roller pivot graphic, and the one inside the cylinder which is inside that, so that's the second graphic, and then this follower translational joint. Okay, so these are the different graphics that are used to create this model. Okay, and now let's see the joints that are used to create this model. Okay, we have the cam pivot joint here, which is a revolute joint, so which allows the cam to rotate along one particular axis. Okay, and then we have the follower translational joint here, so which allows the reciprocative motion of this follower, and we have the follower roller joint here. So this roller is allowed to roll along surface of this cam. Okay, so here we define a ball joint. So here we have a revolute joint, and then we have a translational joint here, and here we have a ball joint. Okay, so 3 different types of joints that are used here, and we have just the one marker, which is the global reference frame, and we are using many hard points to create these bodies. So this is the overview of the model, of the partially built model. Now we'll continue building it further and try to simulate the curve to curve joint. So now let's start by adding curves for the cam profile. So we can directly go to the toolbar here, right click to create the curve. So let's start by giving meaningful names. So let's call this cam profile. So once you've given a meaningful name to it, say OK. So then you come to the curves panel. So in the curves panel, you need to create a 2D spline now. Okay. So from the properties tab, you can go to the file, the open folder option or the icon in the panel. So it comes to your working directory, and you have a file called as camprofile.csv here. Okay, try to load in this, say open. Okay, it's got imported. So now you'll have to do a couple of things here. So change, so this cam profile, let's go ahead and open this in Excel and see what it looks like. Okay, so as you can see, it has 3 columns. Okay, so it is a 3D spline and not a 2D spline. So let's go back. We've already imported the spline here. So here from 2D Cartesian, you can change it to 3D Cartesian. Okay, so now you have X, Y, and Z, and this option from open curve, change it to closed curve. So once you do this, you can keep for the X radio button, you can keep block 1 and column 1, and for the Y radio button, you can choose block 1 but column 2, and for the Z direction, try to load in the same model, same CSV file, and you can go to column 3. So we have X values that will be taken from column 1 from this particular Excel file. Y values will be taken from column 2 from this Excel file. And then the Z values will be taken from column 3 from this particular Excel file. Okay, so this is your cam profile. So you got a 3D spline for this cam profile. Okay, so now let's create a follower profile. For that, let's create another curve. Right click on this and give meaningful names to it. Call this follower roller profile. Say OK. So here we want to enter it as an expression, so or a math function. So first you change this from 2D Cartesian to 3D Cartesian. Okay, once you do that, you'll be selecting from for the X radio button, you'll be selecting math. Okay, and then you start typing in your function here. Okay, so you can go in between these curly braces and start typing 5 times sine into 2 pi times, then you have to give the time interval. So 0 is to 1, is to 0.01. So close two braces here, and then you have the curly braces after that. So just click on this evaluated to see, okay, it says error evaluating. So there's something that we've added extra while adding the braces. Okay, so here we need to open the parenthesis here. So we have three parentheses open and we're closing three. Okay, so this should be right. Let's go to evaluate it and check if the expression is right. Yes, perfect. So you got math function for the x values. Okay, so what this expression does is, let me go back to the function builder. So the expression that you've given here, it will create an array of points from 0 to 1 in the increments of 0.01. Okay, that's what it means. So, so 0 is to 1 refers, it has to create the array of points from 0 to 1 in the intervals of 0.01 or in the increments of 0.01. So that's what it will do. Okay, and that is multiplied by 2 pi times 5 times the sign of this value is multiplied by 5. So that's what this expression is about. And now let's go to the y values. Again, I want it to be a math function. So I'll go here, go to the expression builder. So here, let me give a cos function. So 5 times cos of 2 times pi times 0 from 0 to 1 in the increments of 0.01. So this should be right. And create a similar expression for the z direction from 0 to 1 in terms of 0.01. Okay. So now I'll basically explain why I'm trying to do this. So when I define this cam profile curve in the z direction, if you go and open the file, you can see that the third column is all zeros. Similarly, if I go to the follower profile, it's again the third column is all zeros. So I'm basically doing this to give you an example how we can work with the 3D splines as well. Okay. So, but in reality, these two curves will be 2D splines. So the cam profile and the roller profile will be 2D splines. So I'm just trying to give the 3D Cartesian and using the z values, but I'm giving all zeros there. So just so that when you have an application wherein you have to specify the third column, you know how to do it. Okay, that's the reason I'm doing this. We'll be changing this option from open curve to closed curve. Okay, so now both of them have the curves defined. That is the cam profile as well as the roller profile. We have for cam profile, we have it from an Excel document. And for the roller profile, we have it from the math functions. So now what we'll try to do is set up a CV constraint between these two curves. Okay. So first, let's start creating markers. That. So go to this option. This is to create markers. Right click. So you can give the name as cam marker, and variable name also you can mention it as cam marker. So here you need to select the parent body, the origin, and you want and the axis along which you'll be aligning it. So go to the parent body here, double click on this body option, and for the origin point, the point at which this marker has to be placed, you need to select the pivot point. Now for the axis, you can just accept the defaults and you can start adding one more marker. So right click and you add a second marker. That's basically a follower marker. So if you start giving meaningful names for each of the entities that you create, it will be really helpful if you face an issue later during the model building process. If you get an error or something, then you can just go back. If you've given them meaningful names, then you can go back to the exact same location and do the corresponding changes. So try to make this as an habit to give meaningful names for, especially when your simulation or the model is going to be a little bit complex. So call this as follower marker, the variable name. And I also want to remind this in case you have forgotten that the variable name can only be changed at the time when you're creating a particular entity. It cannot be changed during the model building process, whereas the label name can be changed anytime during the model building process. Okay. So say OK, and here you'll be selecting the follower as a parent body. You'll be selecting the follower roller, and the origin you'll be selecting the follower revolute joint, that is this particular. So you can see that a marker gets created at this location on the roller and at this location for the. So now what all we have done is we have created the two curves, we've created the markers, and now it's a time to create the CVCV joint. So now we need to know where the CVCV joint is located. So if we go to this joints option and right click, and if you just see it in the drop down menu, you can notice that the CVCV joint is not in this location. So these options that you can see here are related to your constraints. Okay, so these are the icons that are related to your constraint. So this particular icon that you can see in the end, okay, is labeled as advanced joint. So this particular joint, CVCV joint, it comes under advanced joints. So you need to go there. Okay, so you can give a label name as CVCV. In here CVCV, and you can go to this location and select curve to curve, and then say OK. So it brings up the curve to curve joint panel. So you'll be in the connectivity tab. So in the connectivity tab, you need to select the curve. Okay, so curve 1, double click on this and select cam profile and say OK. So you can see that this trajectory is created. Okay, and go to curve 2 and select the follower roller profile as curve 2 and say OK. After you define the two curves, you're supposed to give the reference markers. Okay, so the reference marker 1 will be the cam marker, and the reference marker 2 will be the follower marker. So now you can see that a trajectory of the path is created here and on the roller as well as on the cam. Now let's specify the cam motion. Okay, so for this, let's go to the model browser. Let's add a constraint. So right click, add a constraint. That's nothing but the motion constraint. Okay, so let's call this cam motion. Cam motion. So even here you can give cam motion. Okay, and say OK. So in the connectivity tab, let it be defined on the joint itself. Okay, so you double click on the joint, and then you want this motion to be placed at the location of this cam pivot joint. Say OK. So this will apply the motion to this particular revolute joint here. Okay, and this default type is a displacement rotation. So here you can see that it is taken as displacement. So go to the properties tab here, and let's try to give an expression for this motion. In the last exercise, we had given the motion as curve, but here we'll be defining the motion as an expression. So a very simple expression. Let's go to the function builder expression. Let's go to the expression builder and then just give 10 times the simulation time. Okay, so once this is done, there's one more important thing that we got to do in this particular simulation, wherein we need to specify the gravity. That's because since the shaft is along the y-axis, we want to give the gravity to be in the negative y direction. Okay, so in order to specify that, let's go to gravity. So if you expand this miscellaneous and if you expand forms, you can find gravity. So click on this and go to the y component here and give minus 9810. So this will be in mm per second square. So once you do this, you need to specify the output request. Okay, so what we want to do here, we want to basically monitor the reaction on this CVCV joint that we have created. Okay, since it can help us to verify the correctness of our results. So we've established the CVCV joint, but now we want to get the reaction at the CVCV joint. Okay, so by the end of this demo, I'll discuss in detail about the lift offs of this particular cam follower mechanism. So now let's go ahead and apply this particular output request so that we can monitor our CV-CV joint. Okay, the reaction on our CV-CV joint. So to add a output request, you can either go to file, you can either go to model, right click on the model, add general MDL entity, and you can go to the output, or you can directly go to this option and right click and you can add the output request. Okay, so you give a label name here called CV-CV reaction. Okay, so CV-CV reaction and say okay. So change this option from displacement to expressions, and in the F2 expression box, go to the expression builder and specify an expression. Let's go to the force tab and click on CV-CV. And the CV-CV joint, basically it has 4 arguments. So the first argument is the ID, second argument is the J flag. Okay, if it is 0, it gives the reaction on the I marker and 1 on the J marker. Okay, so if this particular the first one is the ID of the CV-CV joint, the second argument is basically the J flag. So if you give if you basically mention 0 in the second argument, it gives the reaction of on I marker, and if you give 1 in the second argument, it gives the reaction on the J marker. And this is the component of reaction, the third argument. And the fourth argument is basically the reference marker. Okay, if it is 0, then it implies the global reference frame. Okay, so let's try to give that. So go to the first argument. In that, go to properties. So let's try to give the CV-CV joints ID. So joint, so it should be under advanced joints, not joint. So let's go to advanced joint, CV-CV joint, and its ID string. Say add. So we got the ID string of that, and here we will specify the J component or the J flag to be 1. So we want the reaction on the J marker. And then here we'll give it as 2. So this is the component of reaction force. And then the last option we'll specify as 0. So we want it to be in the global reference frame. So let's see if this is right. Okay, so there are no errors. This is the right expression. Okay, so now what we'll try to do is go ahead and start running the model. So go to the run option here, and we need to change certain things. For example, the end time, we can increase it to like 6.28 seconds because I've run the simulation before. I know exactly what end time I need to give, or the simulation time I need to specify. And the print interval, we can leave it as it is. But then let's go to this tab here, which is called as the simulation settings. And here, let's go to the transient tab, which is the second tab. And here, change the DA index from 3 to, so when you change the DA index from 3 to 1, so this DA index 1, it adds system velocities to the error control, okay, which will generally compute a more accurate answer for the same integration tolerance setting as 3. So it is DA index should be set to 1 if you're trying to, if your system has a lot of velocities involved in it and you want to monitor that. So it adds the system velocities to the error control. So you need to change the parameter from or the value from 3 to 1. So once you do that, say close. So you can try to save this as camp follower constraint .xml. So let's go to animate and see if our animation looks right. Okay, so this launches HyperView in the second window. So the simulation looks good. Okay, so let's come back to MotionView. Let me stop this animation. Come back to MotionView. Now we want to plot some graphs. So go to plot. This will launch hypergraph. So here you try to plot. Go to in the Y type, go to body. So after going to body, go to the follower shaft and its displacement in the Y direction. The displacement of this particular shaft, which is having this reciprocating motion in the Y direction with respect to the ground. So say apply. So this is what you're expecting. So the maximum displacement of this shaft that you're seeing, the follower shaft, will be 25 mm. Okay, at the peak position. Okay, so I hope it's clear. Okay, and there's one note. that I have to mention here. So this is basically regarding the liftoff. Okay, so in a real physical world, the dynamics, it causes the follower to lose contact with the cam. Okay, so this is something that we've modeled in virtually, but if you take actual scenario, okay, so there will be some cases when because of the dynamic forces, the roller follower that you have, it can lose contact with the cam. Okay, so this particular thing is called liftoff. Okay, in such cases, modeling the system using the CV-CV joint will give us totally incorrect results, because in CV-CV joint, it basically constrains the follower point to be always on the curve. Okay, so if you want to simulate such cases wherein you wanted to model it close to the reality, then you need to use force-based simulation. In the sense, you need to set up a 3D contact between the cam and the follower, and then you're supposed to measure its output. Okay, so to see if there is any liftoff or not. But this is a quick way of simulation, and it takes very less time for doing this. But if you want to set up a 3D contact between the follower, the roller follower, as well as the cam, then it is going to involve some complexities, and also it's going to take a longer time to run. But that is more closer to the physical world compared to this. So that's one note I wanted to make. So at the end of the next chapter, which will be on the 3D contacts, you can try to use the same model and try setting up a 3D contact between the cam and the follower, and try to simulate the model and see what results you get. So this brings you to the end of chapter 10 demo. Thank you. Welcome back to the 11th chapter in Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. In this chapter, we will focus on one of the most important topics in the MBD world regarding the 3D contacts. MotionSolve has a very fine and sophisticated capability when it comes to contact modeling. It has 4 built-in algorithms from which the user can choose the best one that fits his or her needs. It can effectively handle complex contact scenarios, especially between the rigid bodies. So there are 2 basic elements that you need when you want to create a contact. So the first element is that you need to identify the geometries on one body that will be interacting with a different set of geometries on the other body. And the second element is that the user should have a good idea of the physics behind the model that he wants to build, so that he can specify accurate contact material properties such as coefficient of restitution, etc., leading to more realistic results. So in CAE, we mentioned one thing, that if you input garbage, then you're going to get an output as a garbage. So you need to be very careful when you choose to select particular parameters, particular values for certain parameters like friction. You need to have a good knowledge of physics so that you know what to choose for, say, a dynamic friction when compared to static friction, etc. So in CAE, if you give garbage in, then you're going to get garbage out. So make sure that you use realistic values when you're specifying these content, when you're specifying these parameters. The concept of contact simulation in MotionView can be defined in the following manner. The solver basically keeps a track of the proximity between the specified geometries to each other throughout the simulation. A force depending on the defined contact properties gets developed when there is any penetration between the bodies that interact with each other. So this force is called as the contact force. Okay. So in MotionSolve, both the frictional forces as well as the normal forces can be modeled. So it has a very good capability wherein you can incorporate both the normal forces as well as the frictional forces. When the interacting bodies get separated, the contact force between them becomes 0. So this is the entire concept of contacts in MotionSolve. In order to set up complex contact models, it is necessary that you know the basics very well so that you will not face any issues in setting up the models for contact simulation. If you need to set up the contact model in MotionSolve, you need to concentrate on 4 key features. They are efficient model building of the body geometries that are in contact, detecting the onset of or the commencement of the contact, applying the contact force. The fourth point is detecting the end of a contact event and deactivating the contact force. So we will get into the details in the upcoming slides. Now let's move on to the first criteria. The first requirement to set a contact model in MotionSolve is to create acceptable geometry for the contact simulation. I will explain what I mean by acceptable in a while. So the geometries for contacts are represented through meshed surfaces. This mesh basically consists of interconnected triangular elements, as you can see on the screen. Okay, so there are several options for defining the geometry of the bodies in contact. For simple shapes, you may use the MotionSolve primitive graphics such as cylinder, box, plane, frustum, and ellipsoid. More complex geometries may be defined using a CAD package and imported into MotionView by using the CAD import utility after translating them into the H2D format. So this translation is automatically performed by MotionView. The 3D file contains tessellated geometry that MotionSolve understands. So in the case where the user is importing an external CAD, there are certain criteria that have to be followed for the mesh geometry to be acceptable in contact simulation. They include the mesh surface must not contain any T connections. It must enclose a complete volume. The meaning of an enclosed volume is that all the elements share an edge with an adjacent edge. When more than two elements share an edge, then the T formation takes place. So when you're trying to mesh any external CAD, then you need to keep in mind that there should be no T connections in your meshed surface. So this will happen when more than two elements will share a common edge. So we need to avoid this in our meshed surface. So for instance, if you're trying to create a contact between a road and an automobile tire, the road should be modeled as a 3D cuboid with some thickness and not by using a rectangular planar geometry. If you try to use the rectangular planar geometry as a road when you create a 3D contact with a tire, then the solver will give you an error and you cannot proceed further. The next requirement for the mesh model preparation is that the mesh size should be relatively uniform, meaning there should be no large variations in the length of the element edges. So in HyperMesh, when you try to mesh a model, it is always a good practice to have relatively uniform mesh size. So if you try to use a primitive geometry and if you import the geometry using the CAD import utility, then you can make sure that this mesh size can be relatively uniform. And if you're trying to interactively use HyperMesh to do this, then you need to have a good idea how to create a relatively uniform mesh before importing the model into MotionView. The third requirement is that the element normal must point in the direction of the expected contact. So the element is basically a vector which is normal to the plane of the element and along the same side of the element determined by the sequence of the node connections. So this follows the right hand rule as shown in the particular slide. So if the element normal is coming out of the slide in this particular case, so the node connection will be 1, 2, 3. And if the node connection is done in anti-clockwise like 1, 2, and 3, then the element normal will be going into this particular slide. So here in this scenario, it is coming out of the slide or out of this page. And in the second right hand side, you can see that it is going into the page. It depends upon how the nodes are numbered. Okay. Or it depends upon the sequence of the node connections. So please note that the MotionView's CAD import utility has the ability to import the geometry that fulfills all the above criteria. Also, MotionView will automatically try and set the normal vectors for the elements to point outward from the enclosed volume when you're creating the .h3d file. Okay, now moving on to the next slide. I'll be explaining regarding the mechanism of the detection of point of contact and the series of events that occur within the solver. When the onset of collision occurs, at any particular time step. The collision detection algorithm that we learned about in the previous chapter gets activated and returns the set of interfering geometries. For those, MotionSolve computes the point of contact and the surface normal vector, relative tangential slip velocity between the bodies, and also a magnitude representing the direction of the normal and the friction forces. So all this happens in the background when you try to set up a contact simulation. So to improve the precision with which the time of contact event is detected and thereby the accuracy of the results, a sensor can also be used along with the contact entity through the MotionSolve statement sensor evaluate. So you can use a particular statement called sensor evaluate in order to install a sensor to detect the onset of your contact simulation. So by using this feature, the solver can be forced to take a step back and proceed with a reduced maximum step size. So I'll be explaining about this and we'll talk about sensors somewhere in the later part of this course. Now, I need to highlight something that is very important and interesting here. When you're dealing with spherical analytical geometries, MotionSolve uses an analytical description of the geometry based on the radius and the location of the center of the sphere while calculating the contact point, normal, etc. So this approach is followed whenever MotionSolve detects a primitive spherical geometry. So there are two advantages of using an analytical description for a spherical body. Since there is no surface mesh, there are no errors due to the approximation of the surface by a triangulated mesh. This means that the contact forces are more accurate. The second advantage is that the solution time is typically much smaller for contacts involving a sphere and a generalized 3D mesh. So this is something that I wanted to highlight here, that if you try to use spherical geometry, spherical primitive geometry, then your contact simulation results are going to be very accurate, and the solution time is also will also be considerably less when compared to the other contact models. Now it's a time to discuss regarding the different algorithms that are used to create the contact force. Once the point of contact and the surface normal vectors are known, the magnitude of the normal force are computed using one of these following methods or algorithms. So they are the impact method, the penalty-based Poisson method, volume method, and by using the user-defined subroutine. Now let us look into each of these in detail. So before that, let me quickly explain the meaning of contact force and what it is comprised of. The normal contact force is basically the sum of the elastic spring force, okay, and the dissipative damping force. So when you say a normal contact force, it is going to be the sum of these two, spring force plus the damping force. The friction force is calculated using the Coulomb friction model, which will be explained in the upcoming slides. So even when you talk about the contact force, it's divided into two things, okay? One is the normal contact force and the other one is the friction force, okay? And the normal contact force again has two components. One is the spring force, the other one is the damping force. So there are four methods in which you can, or the four algorithms to calculate this normal contact force. That is what we'll be learning about in the next few slides. So now let us start with the impact contact model. So this algorithm or approach, or it can also be called as a model, can be picturized as a non-linear spring damper introduced in the system when there is penetration between the two geometries that are in contact. The four main parameters required to define the impact contact model include stiffness, stiffness exponent, maximum damping, and the penetration at maximum damping. So the stiffness value that is provided should be a non-negative value. The stiffness exponent determines the exponent of the force deformation characteristic. The values of the maximum damping and the penetration at maximum damping should be provided as an input from the user, either by physical testing knowledge or experience, or by using the physical knowledge. The accuracy of the simulation depends on the accuracy of these input parameters defined by the user. Finally, the impact function calculates the normal force at each node when the collision detection algorithm detects contact, penetration depth, rate of penetration, and the above 4 parameters. So this is the concept behind impact contact model. And by default, when you set up a 3D contact simulation in MotionView, it usually uses this particular contact model to calculate the normal contact force. Now let's move on to the next normal contact force algorithm or model, which is the Poisson contact model. So let us get into the mathematics behind the computation of this force. Okay. So we know that the normal contact force is basically the sum of the spring force and the damping force. In this case, the spring force is given by multiplying the penalty parameter K, which is an user input, and the penetration Z raised to the power of 1.5. And the damping force is given by multiplying the negative of the spring force into an exponent, which will be a function of the coefficient of restitution, and the step function involving the velocities at which the objects approach each other, and the normal transition velocity, which is called as V-trans, which is again an input by the user. Okay, so I mentioned coefficient of restitution and penalty parameter in my previous sentences. So these parameters play a very important role in contact modeling. The penalty parameter refers to the stiffness of the contacts. A large value of the penalty parameter means large stiffness. So this results in lesser penetration and vice versa. So the penalty parameter and penetration are both inversely proportional to one another. The next parameter, which is the coefficient of restitution, controls the relative velocity of approach to the velocity of separation. In order to understand this more clearly, you can imagine a ball bouncing. A coefficient of restitution of value 1 implies that a perfect elastic collision has occurred, meaning the separation velocity will be the same before and after the collision, and thus the energy gets conserved. So the energy is neither created nor destroyed, but it gets conserved. On the other hand, if you have a value of coefficient of restitution that is equal to 0, it refers to a perfectly plastic collision. Hence, the bodies will stick to each other after the collision. The normal transition velocity controls at what approach velocity the damping force starts to get smaller, and the transition to damping force when the objects are moving away from each other. So this is the mathematical formulation behind the Poisson's contact model. I hope it's clear. So now let's move on to the mathematical formulation of the next type of contact model, which is the volume contact algorithm or the volume contact model to calculate the normal contact force. In the volume model, the elastic spring force component of the normal force is modeled very similar to the impact model, which is the first algorithm that I covered, while the damping force is computed by using a damping coefficient. So in this method, the spring force is basically the product of the area of contact of the interacting bodies and the contact stiffness K and the contact penetration depth Z to the power of the force deformation characteristic. The volume model makes an assumption that both the colliding bodies are surrounded by a layer of springs whose stiffness is determined by the elastic modulus properties and the depth of this particular material layer. So now I'll show you the mathematical formulation of this volume contact model. So here is each individual stiffness for each body I and J. So wherein the stiffness parameter Ci is basically the ratio of elastic modulus M of the body to the depth of the layer of the body. So which is D. So for body I, the stiffness parameter Ci is the ratio of Mi to Di, and for body J, the stiffness parameter Cj is equal to the ratio of Mj over Dj. So now the equivalent contact stiffness can be calculated by assuming that both of these springs for body I and J are in series. So then you get the equivalent contact stiffness K is equal to Ci Cj divided by Ci plus Cj. And this equivalent stiffness K has the units of force per cubic length. So this algorithm uses the contact area and the penetration depth to retrieve the contact force in Newton. The elastic modulus M, sometimes also called as the P-wave modulus, for both the bodies in contact is calculated using the bulk and shear modulus. So these can be specified in the contact panel in MotionView. So the elastic modulus is given by M is equal to K plus 4G by 3. Where M is the elastic modulus, K is the bulk modulus, and G is the shear modulus of the respective materials. And this shear modulus G is basically E divided by 2 into 1 plus nu, where E is the Young modulus and nu is the Poisson's ratio. And K in this equation is E divided by 3 into 1 minus 2 nu, where E is the Young's modulus and nu is the Poisson's ratio. So both the elastic modulus and layer depth determines the value of the equivalent contact stiffness. Since for a given material, the elastic modulus is typically a constant value, you may change the layer depth to obtain an appropriate penetration in your module. The volume force model thus lets you to derive the contact stiffness from the physical material properties of the colliding body. So this is the last method to define the normal contact force, and that's by using the user subroutines. So this user subroutines is basically used by the advanced level users. They can define their own contact algorithm using the CNF subroutine for the contact normal force. Again, the user can write the subroutines in various languages such as C++, Fortran, Python, or MATLAB. So now this brings you to the end of the different contact models which are used to define the normal contact force. Now let's step into the friction force. Okay, so the friction force can be defined by using any of these two methods. The first one is the Coulomb friction method, and the other one is by using the user subroutines. So let's concentrate now on the Coulomb friction. In this algorithm, the Coulomb friction law is used, which models the friction as a coefficient of friction multiplied by the normal force. The coefficient of friction is basically modeled as the function of the slip velocity. The friction force will be modeled as a viscous force. MotionSolve offers the ability to apply friction either in static and dynamic regimes as well as dynamic regime only. So when you're trying to build a model that involves friction, please keep in mind that you need to give realistic values as input to obtain reasonable values as output. For instance, you need to know that the static friction value should always be higher than the dynamic friction. Also, please note that you should always try to keep your models as simple as possible. So only after you know that your model runs well without even applying friction, then you can try to increase the complexity of the model by first applying the static friction and then going and applying the dynamic friction. Okay, so the Coulomb friction is totally dependent on the concept of the Coulomb friction law. Okay, now when we talk about the user-defined friction, it's similar to the normal force, normal contact force. Okay, the users can create their own code using the CFF subroutine to model the friction force. Note that if both the normal and the friction force are modeled as user subroutine, both the subroutines have to be provided in the same DLL Python or the MATLAB files. So you need to keep in mind that if for the normal contact force you used any of these languages to write the subroutine, then even the friction force should be provided in the same subroutine. Okay. So MotionSolve can separate across individual threads of a processor the calculations involving the interaction of individual contact geometries. In other words, MotionSolve can process in parallel individual contact elements. For example, if a model contained 5 contact pairs, MotionSolve can use 5 threads of processor to calculate the contact interaction in parallel. To change the number of threads used for a simulation, we can go to the General tab in Simulation Settings dialog box open from the Run panel. So I can show that to you when I go back to the graphical user interface. Okay, so now let's get into the contact modeling tips and tricks. So contact modeling isn't everybody's cup of tea. It requires sound knowledge in physics, and you can become better at it only with experience. So I've tried to put together a list of contact modeling tips and tricks, which I will go through one by one so that you'll have a strong foundation in contact modeling. So the first point in that is you need to use the control coarseness for contacts option in the CAD import utility while importing the geometry. I think I've already mentioned this to you earlier. Let me switch back to the graphical user interface. So when you try to import a model in MotionView using the CAD import utility and you're trying to set up a 3D contact simulation, please make sure that this option which says control mesh coarseness for contacts is checked, and you try to keep this at a recommended value of 5 or 6 depending upon the complexity of your geometry. Okay, so this is something that you need to follow when you're trying to deal with the 3D contacts. Okay, so let's go on to the next point. You need to verify that the normal of the elements are in the expected direction using the highlight contact side option in the contact panel in MotionView. So let me go to the graphical user interface. So here, this is the option to create contacts. So when you create a contact, say OK. So once you have the two geometries that you want to create a contact between, then you can check and you can put you can click this particular option to put a check mark on this which says highlight contact side, and you will get to know if contact normal is in the right direction. Okay, so I think I'll illustrate this when I try to do the demo when I have two geometries and I'm trying to set up a contact 3D contact between them. Okay, so let me go back to the presentation. The next tip is that make the contact stiffness as low as possible so that it captures the system behavior. Okay, large values for the penalty or the stiffness, they decrease the penetration between the geometries that will be in contact. So they'll which will also lead to decrease in the integrator step size. So make sure that you do not give large values for the stiffness, because you know stiffness and penetration are inversely proportional to each other. So if you try to give a high value of stiffness, then the penetration between the two bodies that are interacting with each other will be very less. So this poses a problem for the solver. Next point is that the contact force computation will be much smoother and more robust in case if you have larger values of penetration. So make sure you have a good trade-off between the stiffness and penetration values that you input as a user. So some experimentation is usually required for fine-tuning the contact parameters to get realistic and stable results. So I'd like to say, I'm not trying to discourage you, but I'd like to say at this point that when you're trying to set up your first contact model with your first model with the 3D contact, it's not going to be very easy. So it will take some experience and some experimentation, some trial and error method to get the right contact parameters to get stable results. So this is something that you'll have to do from your end. It only comes with practice. So as I mentioned earlier, the next point is that you need to confirm that the model runs without any problems even before adding contacts. Because once you start adding contacts, you start to put in complexity in your model. So even before that, you need to check, you need to save your model at every step and you need to check if your model runs properly even before adding contacts, so that it will be very helpful during your troubleshooting. The next point is that, so you start your modeling with the contact force set to off, and then you add it to the model. I think I also mentioned this in the previous slide when I was talking about the friction contact. Okay, so even before going ahead and using the friction in your model, please make sure it works well just by adding contacts. So the way how you go about it is, you try to simulate your model even before adding contacts, and then you apply contacts and run your model. Still, if it runs okay, that's the time when you add your friction into the model. So this is a procedure that you need to follow when you are trying to set up 3D contacts in your model. So if there is an integration convergence failures, here are some of the options that you can try. So you can decrease the maximum simulation step size, okay, the max step size in the transient tab of the run panel. So I'll just show this to you in the graphical user interface. So if you go to the run panel, so in that, if you go to the simulation settings, and then if you go to transient, so if you're having some issues with the convergence, so this maximum step size for as default will be set to 0.01. So you can try to reduce this even further if you're facing any convergence issues, okay, like 0.001 or 1e to the power minus 4 or 1e to the power minus 5. You can use that as the maximum step size. But as you increase the maximum step size, the simulation time is also going to increase considerably. And the next point is that you need to turn on the find precise contact event to try and increase the accuracy of any contact event. Okay, so going back to the graphical user interface, when you try to model contact, so you need to go to the advanced tab here and try to put a check mark on this particular option which says find precise contact event in case you're facing any issues with the convergence. Okay, let's go back to the presentation, and a few other steps what you can follow to in order to avoid the convergence failures are, you can try to decrease the value of contact stiffness as long as penetration is not too large for a system to handle. Next, you can try adjusting the integration error tolerance. Smaller values might be helpful and they might be useful when you're creating the 3D contacts. So that particular option, the integration error tolerance, can be found in the simulation tab. So run simulation settings. So here, the integrator tolerance, this is something that you can vary and play around with this particular parameter if you are facing any convergence issues. Okay. So next, in the simulation settings dialog box, under again the transient tab, you can set the DAE index to 1. Okay. And also you can go to the show advanced parameters and set the active control to on. Okay, if you set the DAE index to 1, it will ensure that the displacement, velocity, and the acceleration of the constraints in the model are consistent. So turning on the velocity control will ensure that the velocity states of the system are within an error tolerance of the integration error multiplied by the velocity tolerance factor. So this is getting into more complicated stuff and fine-tuning of the parameters. So you don't have to worry much about this. So just make sure that I'll show that to you in the graphical user interface. So if you're still getting some convergence failures, you can go to simulation settings, change the DAE index from 3 to 1. Okay, and you can click on the show advanced parameters. Okay, and you can put a check mark on the velocity control. Okay, so these are some of the things that you can do if you're facing any convergence issues with a solver. Okay, so below is like a table which I grabbed from the Altair material. Okay, so wherein they've given some of the issues that are commonly faced by the users and some quick remedies for them. Okay, so specifically for the 3D contacts. So this is some useful material. Okay, so when the body's if the issue is if the bodies are passing through each other, then you need to decrease the maximum simulation time step, or you can try to decrease the integrated error tolerance. You can try to increase the contact stiffness. So if the bodies are trying to pass through each other, it means that the penetration is too much. So we know that penetration and stiffness are inversely proportional to each other. So in that case, you can increase the contact stiffness. Okay, and the other thing that you can try to do is to check the element normal in the contacts panel. So these are some of the remedies if you're facing this kind of an issue. Next, I already discussed about this. If you're facing integration failures, then you can start activating the contact one by one to see which particular contact is creating a problem. You can decrease the penalty. You can decrease the maximum step size. You can try to fine-tune your mesh size either by using HyperMesh, or in the CAD import utility, you can try to make a mesh size more finer from a level of 5 to 6 to like 8 to 9. And next one is to increase the integration error tolerance, to decrease the coefficients of friction, and to increase the friction transition velocity, and also by increasing damping. But all these things should be used only if you're facing the integration failure, because any of these steps, if they're incorporated, then it is going to cost you a lot of time. Okay, the simulation time is going to increase by some folds. So be careful of it. Only if you're facing the integration failure, try to incorporate these steps. Okay, and if an integration fails at the start of the simulation, then you need to check whether the parts are penetrating at the model configuration. And if the contact locks the bodies together, then the main issue in that will be because of the surface normals. So we need to ensure that the surface normal vectors coming out of the mesh or coming out of the interacting geometries are correct. Okay, so you can use the contact panel in MotionView, and you can try to see if the element normals are in the right directions. So these are some of the common failures and the remedies to be followed so that it will make your lives much easier. Okay, now it's the time to discuss about some of the limitations of MotionView. Okay, so the first, when it comes to the 3D contacts, the first limitation is that MotionView does not have a very good flexible body contact that is supported. It has, although it has a very good capability of handling rigid contacts, it does not have that great capability to handle the flexible body contact. So as a workaround, you can use the deformable surface on the surface of the flexible body and create a point to deformable surface contact, okay, to establish this particular flexible body contact. I think I already spoke about this when I covered the point to deformable surface contact in the higher pair constraints. Okay, but this particular topic will be beyond the scope of this class. Okay, and the next point is that the contact between 2D geometries such as curve, arc, circle is not supported in MotionView. That's the reason when you are trying to use a point to curve or curve to curve contact, it is best to go ahead and use the curve to curve joints. Okay, so these are some of the limitations concerned with the contact simulation in MotionSolve. Okay, so now let's come to the different ways how we can create contacts in MotionView. Okay, so let me go back to the graphical user interface. So there are two ways of creating contacts in MotionView. The first way is to go to your model browser, right click, add. It's a force entity. So go to force entity and click on contacts. Okay, so this is one way of adding the contact. You have rigid to rigid contact and you have the point to deformable surface contact. So this is the usual contact that we use for the rigid bodies, the rigid to rigid contact. Say okay. This is one way of adding contact, and the next way of adding contact is directly from the toolbar, which is a shortcut. Just right click on the contact icon and say okay. So this is the second way of adding contact. And if you already had contacts in your model, then you can just go ahead and click right click and then say add contact. It's going to add the next contact. Okay, so these are the different ways of adding contacts in your model. Okay, let's go back to the presentation. So we just covered this. So the next slide indicates defining the various properties in MotionView. Okay, so after you create a contact, you get three particular tabs. One is the connectivity tab, then you have the properties tab, and then you have the advanced properties tab. So in the connectivity tab, you're supposed to select the two bodies that you want to create the contact between. So body I and body J, and then you're supposed to select the graphics between which you need to create a contact. So here, this particular body, it has these graphics. Okay, and when you select this body, it has these two graphics, and you're supposed to tell between which two bodies you're trying to create contact. Okay, so you're supposed to indicate that by using these check marks, and then this is where you set up the connectivity. And then you'll be going to the properties tab, and you will be selecting the type of the contact model that you'll be using to establish the normal contact force. And then you'll be going to the friction tab. Okay, if you go to the friction tab, like, as you can see, you have the different you have flexibility to select the either if you want just a static, both static and dynamic contact friction, or if you just want dynamic only, or you can disable the contact force, or you can also use a user subroutine or user defined friction force. So you have all these options, and this is your static friction, this is your dynamic friction. So these are some of the things that you can give in the properties tab. And then if you go to the advanced tab, as I already showed you earlier, you have these two. You usually try to keep these two checked on when you're trying to deal with 3D contacts. Okay, so I think that's clear now. Okay, so now there's one more thing that you'll have to remember regarding the 3D contacts. Okay, so when you have a number of contacts in your model, so in the next exercise or in the chapter 11 exercise, which we'll be doing right now after this theory, there are several contacts that will come into picture. So the model that we are trying to build, that we'll be building, will have many contacts. It will have around 12 contacts in the model. So in that case, it becomes increasingly difficult if you try to go to each of these contacts and try to change the parameters or set the parameters for normal force and for friction force. In that case, you can directly go to the contact properties editor, okay, and try to select some of the or all the contacts, and if they're going to have the same value for both the static friction, dynamic friction, you can give the values accordingly, and you can select all of these and give the values at one shot. So it will help you save a lot of time. Okay, so we'll be using this particular technique when we are doing the exercise demo. So to just show you in the graphical user interface where it's located, you can go to this vertical toolbar. Here you can click on this. So right now we are having contact 0, 1, 2, 3 that we've created. So you can select all of these by holding your left mouse button and selecting all of these, and you can try to give the values for these contacts. Okay, so this is the easiest way of modifying the properties of all the contacts all at one shot. Okay, so we're done with this slide. So this brings to us to the end of the theory on 3D contacts. So next, let's get into the demo of contact simulation. Thank you. Welcome back to the 11th chapter demo exercise. So in this chapter, we will import a ball bearing model and try setting up the 3D contacts. In the end, we will try reviewing the contact forces between the ball bearings in this particular MotionView model. Okay, so let's get started. So here we'll be importing the ball bearing model that's been already built. So let's go to the CAD import utility. Okay, so in this particular section, I want to import the CAD along with the mass and inertias. So I leave it as it is for the first option for the import. And then the file that I want to import is a parasolid file, so I keep it as it is. So I go to this particular icon and go to the 11th chapter. I have ball bearing.txt. So this is a parasolid file, and next I'll be going and putting a check mark on this, since I mentioned in the theory class that for 3D contacts it's always preferable to put a check mark on this and set the slider to an average value of 5. Okay, so once this is done, you can leave all other options as it is and just hit on OK. So MotionView invokes HyperMesh in the background that basically imports the CAD, applies a mesh on the solid surfaces, and it calculates the volume, center of mass, and the mass of inertia. So once the HyperMesh process is complete, the import CAD dialog box opens once again, and it contains a table of components along with the density information, okay, the mass, density, and the volume information. So in this particular table, you can go ahead and if you want to change the mass of any of these components, you can change the density of any of these components by clicking on the particular component, going here and changing the value and clicking on apply. Okay, so the density cannot be changed once the import is complete. So if you want to change any value, it's at this time that you're supposed to do it. Okay, so you can leave everything as it is and say OK. So it says importing the file succeeded. So there were no other error messages, and it successfully imported the model. Okay, so now let's go ahead and review the model by navigating through the model browser. So just expand bodies. So as usual, we have the default ground body, and this is the rim that you can see, which is the outer component here. It gets highlighted. I hope it's clearly visible. That's the rim. The inner race refers to this red disc or red cylinder that you can see. Is basically the inner disc or the inner race. The outer disc is the blue structure. Okay, and the rim will be the yellow part that you can see. Okay, so once that is done, this is ball 1, 2, 3, 4, 5, and 6. So there are 6 balls in this ball bearing, and we'll try to set up the contact between each of these balls with the inner race, outer race, and the rim. Okay, so to hold them in space. So now let's save this model as ball bearing contact.mdl. So file save as model. So ball bearing contact.mdl. Okay, so I just did that. Now let's review the mesh and create the joints. So go to the graphic option here, okay, and click on the model that selects this entire model, and then click on the mesh lines. So you'll know how finely this particular CAD is meshed automatically. Okay, so this is how it's meshed with uniform, almost uniform mesh size. Okay, so this is a very good quality mesh that's used on this model. So you need to create now the joints for this particular model. Okay, so let's go to the joints, create joints icon on the toolbar. Okay, let's give meaningful names as an enable name for creating the joints. So we'll call this fix outer race. Let me use underscores. So fix outer race, and in the variable name I'll give fix outer race. Okay, and this is supposed to be a fixed joint. So I'll go to the drop down menu and click on fixed joint. Okay, and the type is single, so say OK. So the body 1 is gonna be the outer race, and the body 2 will be the ground body. Okay, and the origin will be the race center of gravity. Okay, so outer race center of gravity, and say okay. So you got a fixed joint here, so it fixes the outer race. And next let's go to the rim. So to create another joint, so call this the rim joint. The variable name will be rim, and here we're going to create a revolute joint. Okay, so say okay, and the body 1 will be the rim, and body 2 will be the ground body, and say okay. So the origin will be the CG of the rim, so which is at the same location, and now we need to create the orientation for this revolute joint. So that should be about the global x-axis. Okay, so this is right now about the global z-axis, so you need to change the orientation so that it aligns itself to the global x-axis. So you need to go to this drop down menu, click on vector, double click on this vector option, click on global x. Okay, so now you can see that it's oriented in the right direction. Okay, so once you set up these two joints, now is the time to go ahead and create other contacts. So you will be individually creating contacts between the inner race and the balls, the outer race and the balls, and also the rim and the balls. So this means you're going to have 6 times 3, so you'll have 18 contacts in this contact model. So you can right click on the contact. So the two ways of creating contact, you can either go to the model browser, right click, add, force entity, and go to contact, or you can go and directly add contacts from this toolbar. Okay, so I'll go here, I'll give a label name saying it's a contact between ball 1 to inner race. Okay, so the variable name will be ball 1 inner, so ball 1 inner. Okay, and it's going to be a rigid to rigid contact, and click on OK. So please note that an output is automatically created for each contact entity that will be creating. Okay, so do keep a watch on this as and when I create new contacts. So here for this, in the connectivity tab, for the body 1, double click on this and click on ball 1 and say OK. And for body J, this is contact between the ball and the inner race, so select inner race and say OK. So you can click on the highlight contact side. Okay, so you can get to know that this is shown in red color. Okay, so the contact side of both the bodies in contact are as shown here. Okay, so this gets highlighted. You can see the difference when I uncheck this and check this. Okay, so MotionView automatically tries to orient all the mesh elements surface normal along the force of direction during the import CAD utility itself. Okay, so in the case the contact is not assigned as per what the user desires, you can go and click on the material side to swap the direction of the contact normal. Okay, so right now it looks good, so I'm leaving it as it is. Okay, and one more thing that you'll have to notice is this particular option which has mesh errors is grayed out. This means that the meshing has been done properly and there are no mesh errors involved. So if you try to use an external CAD model and interactively mesh the model in HyperMesh and when you try to import, and if it is either not enclosed or if it has T connections, then this particular option will be highlighted. So you can get to know that there are some meshing errors in your mesh model. Okay, now let's go to the properties here. So in properties, go to the normal force tab. So we'll try to use the impact contact model. So we'll use the default value, which is 1000 for the stiffness, 2.1 for the exponent. The damping is 0.1 and the penetration depth is also 0.1. Okay, now you can click on the friction and you can verify that the friction is disabled. So neither the static nor the dynamic friction is applied here right now, so it's disabled. And go to the advanced tab. Okay, so even these options are not needed to be checked for this particular exercise. Okay, so this advanced tab, basically it offers more options to control the contact simulation, and also it basically controls the simulation when the contact is first detected, and it is only useful in case of those models which have intermittent contacts to provide more accurate results. So only in those cases when we have intermittent contacts, only then we try to use these two options. Otherwise, for this particular model, we don't have to check these two options. We can leave them as it is. Okay, now we'll repeat the same thing that we did for the other contacts as well. So let's move forward and create the other contacts. So right click on this, call this ball to inner. Ball to inner is a rigid to rigid contact, and the body I will be the ball 2 and the body J will be the inner race. Similarly, ball 3 inner race, ball 3 inner. Okay, so body I will be ball 3 and body J will be the inner race. Next one will be the ball 4 and the inner race. So it is ball 4 inner. Click on OK. So this will be ball 4 and body J will be the inner race. Say OK. Go to the next contact, ball 5 inner. So here ball 5 inner race. So you can add inner race here and say OK. So there should be ball 5 and body J will be the inner race, and next one should be the ball 6 and the inner race. So here it is ball 6 inner. Say OK, and this should be ball 6 and inner race. Okay, so all these contacts have been set up right now. Okay, so now let's go ahead and create the contacts between these balls and the outer race. So same way, call this ball 1 and outer race. Ball 1 outer. Click on OK. So here this time the body I will be ball 1, but body J is going to be the outer race. Okay. So similarly do for the rest of the balls. So ball 2 outer race, Next is ball 3 outer race. And another contact, which is ball 4 outer race. Say okay. So ball 4 and outer race. Similarly, ball 5 outer. And then ball 6 outer race. Okay. So now you set up the contacts between these balls and the inner and the outer rims. So for each contact you're creating, you can see that the outputs are also getting created automatically. Okay, you have 6 more contacts to go. You need to also create a contact between the ball and the rim. Okay, so go here, call this ball 1 rim. Okay, so the body I will be ball 1 and body J will be rim. Okay, second one ball 2 and the rim. So even the last time I forgot to change the variable name, but now I cannot go forward and I cannot change this name. Okay, because the variable name can only be changed at the time of the creation of a particular entity. So it is ball 2 rim. Say okay, ball 2 and body J will be the rim. Right click on this, ball 3 rim. So the body I is ball 3 and body J is the rim. Next ball 4 and the rim. So here body I is ball 4 and body J will be the rim. Next it is ball 5 to the rim. Here ball 5 rim. So ball 5 and body J will be the rim. And now we create the last contact, which is the ball 6 and the rim. Okay, we forgot to change the variable name here. That's fine. So for ball 6 and the rim, let's select ball 6. Body J is the rim. So now all these contacts have been set up. So there are 18 contacts in this particular model. Okay. So now what we'll try to do is we'll go just in order to save time further, instead of changing the properties of each of these contacts, we can directly go to the contacts property editor, which I spoke about it when I concluded the theory session. So if you just go here and you can select whatever contacts you want and you can assign the properties at one shot. So this is something I spoke about in the theory class. So we'll make use of that in this demo session. Okay, so click on all these contact that you've created right now. Okay, so the way how you have to select all this is select the first one, hold your hold your left mouse button and drag till the end. This is the way you select all the contacts. Okay, so you turn off this particular box which says edit friction force, so you turn this off. Okay, also turn off the edit event control, okay, under the normal force. Okay, so after doing this, under you can also turn this off under normal force. You can turn this off, so you can just keep this one active under the friction force. You can just keep this active. Set this to on dynamic only, wherein you can apply the dynamic friction. Okay, so once that's done, you can apply the default values. You can leave all these values as it is and then say OK. So now the dynamic friction value is applied to all the contacts. To just check that, you can verify by going to say this particular contact. If you go to properties, if you go to friction tab, you can see that it was disabled earlier. Now the dynamic only radio button is selected, and these are the default values that are assigned. Okay, you can just go to some random contacts and verify that this has been done in all the contacts. So it's there right now. Now let's try to specify motion to the inner race. Okay, and then run the model. Okay, so let's give motion to the inner race. So let's minimize all these in the model browser. So right click on the motion icon. So right click on this motion icon, and you can give a label name as inner race motion. Okay, so here you can specify something called as inner race and then say OK. So here you are defining the motion by using markers. So say by using markers, and select the rotation about x-axis of marker 2 in this particular drop down box. Okay, rotation about x-axis of the marker 2. So once this is done, for marker 1, double click on this, go to the body's drop down menu, and then you go to the inner race and select the marker same. Okay, and then select OK. And for marker 2, you go to the bodies and then you go to the outer race and select markers, center of marker. Okay, center of mass marker. So you selected those two. After you've given the connectivity options, go to properties. So you'll be giving this motion as an expression. So let's go to the expression builder. So it will be 360 times time. So 60. So say evaluated and OK. So we gave the expression now. Now let's go to the run option. So in the run option, you can go to the simulation settings. Okay, and then go to the transient tab, and in transient tab you can change the maximum step size to 0.001. okay, so this will help us in avoiding any convergence failures because we've set up so many contacts in this model. And then you close this dialog box. Okay, provide a name for this XML, say ball bearing contact completed, and say save. Okay, and now click on run and see if you're going to get any error message in this message log. Okay, so you can see that because it involves a large number of contacts, it's taking some time for solving it. So let's wait till the solver completes the simulation and gives us results. Okay, so its simulation is completed, and now it's writing the H2D model and the result files. Okay, That's done. Now I can just say close and close. And for reviewing the results of contact simulation, we don't really go to animate or plot, because a report is automatically created when you do the 3D contacts. Okay, to invoke that, you can go to view. To invoke the reports, you can go to the analysis option on the toolbar and then click on view reports. So here it basically shows all the reports which has been generated previously. So here you'll have to select the latest one that was generated. So and then click on OK. So then it will load multiple pages of HyperView and also hypergraph, and it will show you the results. Okay. So if you navigate through the pages, you should be able to see the report. Okay. So if you're not seeing this particular animation on the screen or a figure on the screen, then just go to the different pages and press fit. Okay. So there are 5 pages that are generated. So and this is the contact force plot. It has force on the y-axis and the time domain on the x-axis. So it's time versus the contact force. Okay, for the various contacts that you've created. So this is the 5th page in your report. Okay. So the first page is nothing but your MotionView page itself. Okay, let's go to the next page. So here you have the animation of the contact force. So just click on play. So wait till this completes and you can see simulation of a ball bearing. And to notice how the forces are acting, you can go to this particular option which says vector. Okay, so you can pause this for a second. So you can put the contact force total and you can select X, Y and Z components and go to display option. So here scaling you can choose around, you can put around 1. Okay, and click on apply. So try increasing this to 10. That's a bit too much. 5. So you can see the way in which these contact forces are acting. Okay, so let me play now. So you can see that, right? So this is how the contact forces are acting in the various directions. Okay, so this is the total contact force that I've chosen. You can also choose just the normal or the tangential contact force, or you can choose the contact penetration depth, velocity, or also the slip velocity. So you have all these options in the drop down menu. Okay, and in the next page you can get the contact overview. So you can get to know from this contour plot where you have the maximum contact force. So the highest value that you can see here is from this, it's okay, there is some red region. Okay, if you go and look at this location, it's red in that location. Okay, so that's where the highest contact force is there. So this is the contour plot that you can see. Okay, so once you get to know where you have the highest contact force, you can go ahead and try optimizing that particular area to get the best results. Okay, so this is how it is useful. So this is the contour plot, and in the next page it gives the animation of the penetration depth. Okay, so it says the maximum penetration depth is around 0.614. So this basically gives the animation of the penetration depth. And if you go to the next page, it is the plot of the contact force versus the time. Okay, so here you have all these curves. So, and that's why it's like, kind of looking very messy. So here, if you point out, you can get to know that the contact force of the fourth ball to the outer race is the maximum, right, from this plot. So you can try to isolate only that. Okay, so the ball 4 to outer, right? So it should be this one. So I'll try to switch off all others and keep only that one open. So control, I'm holding control key and selecting all this, and then right click and just say turn off. Okay, so this is how the contact force is there between the fourth ball and the outer race, and that's like, you know, reaching the maximum value very close to, like, you know, 0.1 second or something, or even lesser than that. So this is how we analyze the report that gets generated after doing the 3D contacts. Okay, so let's go back to the first page, which is the motion view. So this completes your demo in contact modeling. Thank you. Hello everyone, welcome to the lecture 15 of Multibody Dynamics. Today we'll be talking about flexible body simulation. We have successfully completed with 7 weeks of Multibody Dynamics course. And here's a quick recap. We started with the basics of model building, and then we simulated the free falling of a stone. We then built a simple pendulum and continued building our final model to finally simulate the motion of an automobile trunk lid using the 4-bar mechanism. In week 6, we concentrated on the higher pair constraints and simulated the cam follower mechanism using the CV-CV joint. In the last week, we covered the topic on contact simulation, which included both theory and a practical hands-on demo for simulating the contact forces acting on a ball bearing. This week and the next week, we shall cover one of the most important topic currently trending in MBD world, which is flexible bodies. So this video lecture series on flexible bodies consists of 4 lecture videos. I have covered the theory on flexible bodies in the first 2 videos, and the hands-on demo is incorporated in the 3rd and the 4th video. Please listen to all the video lectures carefully, and we can have a Q&A session on the 10th of March during the live webinar. Let's begin with an introduction to flexible bodies. In this chapter, we will cover the following topics. First of all, we will understand the advantages of simulating with flexible bodies when compared to using the rigid bodies in our simulation. Here, we will understand the importance and the purpose of flexible body simulation and why it is very popular in the industry and the research domain when compared to the rigid body analysis. Next, I will show you how we can create flexible bodies in MotionView, MotionSolve. It is very easy in the software to create the flex bodies when compared to other software tools, since it has built-in FlexPrep utility which makes it very user-friendly. The FlexPrep tool in MotionView can be used for the following: for generating the flexible bodies and also for converting the flexible bodies to other file types. I will illustrate both the applications of the FlexPrep utility in this demo video. Next, we will see how to animate the flex body modes in HyperView, which is Altair's post-processing software. This is the software that we used in all our exercises for animation. So we'll be using the same software to animate the flex body modes. We should also learn to swap the existing rigid body with a flexible body for performing a flexible body simulation. In the exercise demo, I will be replacing the rigid lower control arm of an automobile suspension with a flexible body to capture the deformation and the stress and strain effects. In CAE, we should always aim in building models that are very close to the structures in the real world and try to obtain results that correlate well with the test results, so that we can minimize the cost of physical testing in the industries. Finally, the analysis that we'll be using in this exercise demo is a quasi-static analysis. So I will give a small briefing on quasi-static analysis before we dive into the simulation. Okay, so let's first understand what is a flexible body. Most of us from the FEA background are well aware of the fact that the finite element models have very high number of degrees of freedom. Hence, it is difficult for the MBD solvers to handle these models. That's one of the main reasons why the FE models take a longer time to converge when compared to the MBD models. Hence, the key fact is that we need to condense the FE models to create the flex bodies. So thus, we can form the definition for flexible bodies. A flexible body is a modal representation of FE model. It is an approximation of a deformable structure used in CAE analysis. It can be used in combination with various CAE solvers to capture large deformation and stress-strain effects on the structure. This data is very useful in various domains such as design, durability, etc. Okay, moving on to the next point. I believe you all would have heard the word superposition. It is basically the net response caused by two or more stimuli. It is the sum of the responses that would have been caused by each stimulus individually. So another way to picturize or understand what a flexible body is by correlating the formation of the flexible body to the concept of modal superposition. This makes it very efficient for the solvers that need to model structures as non-rigid. I will explain in detail how this happens in the upcoming slides. Let us continue our discussion on flexible body and understand its details. I believe all of you would have studied Fourier series in your mathematics course. So you will use that knowledge here to interpret what I will be explaining in this slide. The way MotionSolve determines the deformation of a flexible body to an applied load can be correlated to the Fourier series analysis for periodic functions. Now coming to the meaning of periodic functions. A periodic function is a function returning to the same value at regular intervals. It can be estimated by the sum of sine and cosine functions of varying frequencies that are multiplied by coefficients, illustrated in the figure shown in this slide. So this is a square wave, sawtooth wave, triangle wave, and a semicircle wave. So all these can be considered as the examples of periodic functions. In the same manner, MBD solver will calculate the coefficients for the various deflection modes calculated in the component mode synthesis methods, which then added together produce the resultant deformed shape. Please make a note of this component synthesis method or the CMS method. It is very important and we will discuss this in detail in the upcoming slides of the lecture. Now let us deep dive into the concept of modal superposition. As I mentioned in my previous slide, the idea behind a flexible body is that the final shape can be synthesized by adding a set of modal participation factors and mode shapes. Let us now consider the below example in 2D. The first coefficient or the modal participation factor is 0.7. It is multiplied by the first signal, which is a sine wave. Now, this is added to the second modal participation factor or the coefficient, which is multiplied by the second signal or a second sine wave to give you the resultant signal. So this comes under the domain of signal processing, where you have a primary signal and then it combines with a carrier signal to provide an output, which is a resultant of the primary and the carrier signal. The same concept of signal processing and modal superposition can be applied to the flexible bodies in 3D to obtain a shape. As you can see in the current slide, the images that you see here is of a flexible lower control arm. For instance, a coefficient or the modal participation factor of 0.2 is multiplied with the first 3D shape, which is combined with the second modal participation factor multiplied to the second 3D shape, again which is summed to the third modal participation factor multiplied by the third 3D shape to finally give the deformed shape of the structure. The 2D signals can be related to the 3D shapes of the structure. This is called modal superposition. When I say it can be for any response, when I say shape, it can be for any response such as deformation, stress or strain. Okay, now We have thoroughly understood the manner in which the flex bodies are formed and the concept involved in their creation. But now, let's go back to our first statement that I mentioned in my first slide regarding the fact that finite element models have a very high number of degrees of freedom, and it is very difficult for the MBD solvers to handle these models. Thus, this concept of modal superposition matters in a way that the solvers only need to calculate these modal superposition factors as shown in the current slide by multiplying with the 3D shape, and that is orders of magnitude less work for the solver than calculating for thousands or 10,000s of nodes and elements in an FE model. I hope now you realize the importance of the flexible bodies in the MBD world. Now, let's concentrate on the two key aspects in the modal superposition. They are the number and the maximum frequency of the mode shapes. Increased modes and higher frequency enable more curvature in structure in responses such as deformation, stress, and strain. If you can see in the images, the one on the left has low frequency, which can be correlated with the large wavelength in 2D, hence resulting in a broad curvature, while the image on the right illustrates the high frequency shape, which can be correlated with small wavelength, resulting in a tight curvature. Please note that the stress or strain generally have higher curvature and require more modes to capture their effects when compared to deformation, which can be captured with lesser modes and lower curvature. Okay, now let's discuss regarding the applications of flex bodies. Why was there a need for the evolution from rigid bodies to flex bodies? It is due to the following main reasons. One of the most important reasons is that the flex body can capture large deformations that we usually see in the physical world more realistically when compared to the rigid bodies. So, the CAE results from the flexible body simulation will be very close to the actual test data. The second reason is to improve accuracy in load predictions. This plays a major role in FEA since the loads calculated from the MBD analysis will be used in the FE models to conduct further analysis. Hence, it becomes very important that the predicted loads from the MBD models are highly accurate to support the FEA work. The third reason is that it is possible to capture the stress or strain distribution in a body using the flex bodies, and it is not possible by using a rigid body. This is one of the basic requirements in the CAE world. It is not just sufficient if we compute the forces, torques, accelerations, displacements at various locations, but it's very crucial that our model has the capability to deliver the stress or strain results depending on the user's request. This is possible only if we build our model using the flexible bodies. Moving on to our next point, flexible body helps in generating loads needed for fatigue analysis. And as I mentioned earlier, these loads are highly accurate, which will avoid any errors creeping into the FE results. Okay, now let's move on to the next point. If you guys remember, in chapter 7, we dealt with the redundant constraints. So apart from using J-prints, flexible bodies also help in removing redundant constraints. Lastly, the flexible bodies provide an excellent trade-off between accuracy and simulation time. The degrees of freedom are reduced drastically when compared to the FE models, thereby yielding faster results. You can compare that by seeing these two illustrations on this current slide. Now consider the figure on the right hand side of the slide. It represents the cylinder of an engine with a piston, connecting rod, and a crankshaft. For instance, let us consider that we want to compute the stresses in this particular connecting rod. We can only get this information if we model the connecting rod using the flexible body rather than a rigid body. Also, Moving further, if we want to capture accurate forces exerted by the piston on the cylinder block, then we must make use of the flexible bodies rather than the rigid bodies. This term, interface nodes, plays a very important role in the flexible bodies. So let's understand what interface nodes are. The flexible bodies connect to the multibody dynamic system through the interface nodes. There is no rule that all the interface nodes on the flexible body need to be used. However, any node with a force or any kind of constraint must be an interface node. The outputs such as displacement, velocity, and acceleration need not be an interface node. So what I'm trying to explain here is that if there is any node on the flexible body with any kind of constraint or force associated with it, then it will be tagged as an interface node. Okay, now let's move on to another important topic in flexible bodies, which is the component mode synthesis methods or the CMS methods. I had mentioned regarding the CMS method in my previous slides. Now, let us discuss about it in detail. There are 3 component mode synthesis methods supported in OptiStruct that will reduce the FE model to a set of orthogonal mode shapes. Basically, the CMS method is used to condense a FE model into a flexible body. There are 3 CMS methods. They are the Craig-Bampton method, the Craig-Chang method, and the Craig-Bampton geometric stiffness method. Now let us discuss about each of these methods in detail. In Craig-Bampton method, there are 2 sets of modes that are computed. First, the fixed interface constraint static modes are calculated by applying a unit displacement at each interface nodes in each degree of freedom individually while leaving all the constraints active. Second, the fixed interface eigenmodes, which are calculated with all the interface nodes constrained where the number of modes is specified by the user. So finally, both these set of modes are orthogonalized, producing the modal matrix of mode shapes which will represent the flexible body. Now, let's move on to the second method, which is Craig-Chang method. In this method, again, 2 sets of modes are computed. They are the inertia relief attachment static modes, which are computed by applying unit displacement on each of the interface nodes in each degree of freedom individually, while leaving all the interface nodes free. So this is the main difference between the Craig-Bampton and the Craig-Chang method. In the Craig-Bampton method, unit displacement is applied at each interface nodes in each degree of freedom, leaving all other constraints active. And in Craig-Chang method, the interface nodes are free when the unit displacement is applied. When calculating the static modes, the model is mathematically constrained by inertia. Hence the word inertia relief. So, to produce structural deformations, the mode shapes will be required for calculating. So these are the first set of modes created by Craig-Chang method, which are the inertia relief attachment static modes. Now, coming to the second set of modes created by the Craig-Chang method, and they are the free eigenmodes. They are computed without any constraints on the body. Now, the first and the second set of modes are again orthogonalized, producing the modal matrix of mode shapes that represent a flexible body. The third method is the Craig-Bampton geometric stiffness method. It is nothing but an extension of the Craig-Bampton method, but it further includes the effect of non-linearity, the geometric non-linearity. So, thus I have explained the 3 component mode synthesis methods that are supported in OptiStruct. In the next video, I will explain the applications of these CMS methods. Thank you. Welcome back everyone to the second video lecture on flexible bodies. In the last lecture, we discussed regarding the 3 CMS methods supported in OptiStruct. They are the Craig-Bampton method, the Craig-Chang method, and the Craig-Bampton geometric stiffness method. I hope everyone is clear with these three different CMS methods used for generating the flexible bodies. However, just knowing the three different methods will not be of any use without knowing their practical applications or when we are supposed to use a particular type of the CMS method. So in this slide, let's discuss regarding the selection of CMS methods for different applications. It is highly recommended to use the Craig-Bampton method when most of the degrees of freedom of the interface nodes are constrained by the MBD model. The Craig-Chang method can be used when most of the degrees of freedom of the interface nodes are not constrained in many degrees of freedom by the MBD model. In other words, this method is very effective when the interface nodes are free. The Craig-Bampton geometric stiffness method is supposed to be used when you are analyzing slender structures that have large influence of geometric stiffening effects, especially during spinning, such as in a case of helicopter blades or ceiling fans, etc. Moving on to the next slide. I believe all those having a background in FEA understand the meaning of normal modes analysis. For those of you who don't know what it means, here's the explanation. A normal mode is a motion where all parts of the system are moving sinusoidally with the same frequency and in phase. All observed configurations of a system may be generated from its normal modes. Each normal mode has a characteristic frequency, that is, its eigenvalue. The Craig-Bampton and the Craig-Chang modes are not the same modes as calculated using the conventional normal mode analysis. They may look really similar, but strictly speaking will not compare exactly with the normal modes analysis. So if you compare the modes generated by Craig-Bampton and Craig-Chang methods, it won't be the same when compared to the normal modes analysis. Now let's see how we can calculate the number of modes generated to represent a flexible body. It is equal to the number of degrees of freedom restricted for each interface node, which are nothing but the static modes, in addition to the number of fixed interface or the free eigenmodes that are requested by the user. Let us consider an example to make things more clear. If a flexible body has 4 interface nodes and the user requests 10 free eigenmodes, the number of modes generated to represent a flexible body will be equal to the 4 interface nodes multiplied by the 6 modes per node, which makes it 24, plus the 10 free eigenmodes requested by the user, which will give you 34 modes in total. Another important requirement in the CMS method is that the exterior grid points must be able to move independently of the interior nodes of the flexible body. A common case that causes CMS failures resulting in an error during flex body creation is when the center point of the rigid spider, which is defined as a flexible body interface node, is dependent on the displacements of the outer nodes, which is nothing but a RBE3 element in OptiStruct. This is shown in the figure on the right hand side of the slide, where the node ID 4887 is represented by letter D, and this is the node of a RBE3 element. The user can change the configuration of the RBE3 element to a RBE2 element with an independent center node in HyperMesh. This will be illustrated in the exercise demo in the next video. We will interactively use the FlexPrep utility to invoke HyperMesh during the creation of the flexible body to change the RBE3 spider into RBE2 spider. Okay, now let's move on to the next topic, that is eigenvalue solver. This topic is covered in this chapter only to introduce you to the two different algorithms used in OptiStruct to perform normal modes analysis. They are the Lanczos method and the automated multi-level substructuring eigenvalue solution, also called as the AMSYS method. The eigenvalue data extraction for Lanczos is specified on the EIGRL data cards, and for AMSYS it is specified using EIGRA data cards. Now I will give you a brief explanation on both these methods. Lanczos method. The Lanczos method has the advantage that the eigenvalues and the associated mode shapes are calculated exactly. This method is efficient for calculations in which the number of modes is small and the full shape of each mode is required. The disadvantage of the Lanczos method is that it is very slow for large problems with millions of degrees of freedom, for which hundreds of modes are required. The run times for these types of problems can easily stretch into days. Now, let's concentrate on the pros and cons of the AMSIS method. The AMSIS method has the advantage that only a portion of the eigenvector needs to be calculated. Since only a portion of the eigenvector is calculated, the disk space is greatly reduced. This leads to much shorter run times. For a typical multibody dynamics system's frequency response analysis, there's only about 100 degrees of freedom of interest. The major disadvantage of the AMSIS method is that the calculations are not exact. However, the modal frequencies are still accurate to a few digits. But by default, the solver algorithm is set to Lanczos method. Now, let's concentrate on the flexible file or the flexible body generation using the FlexPrep utility in MotionView, which basically runs OptiStruct in the background. So the user can generate flex bodies in MotionView in the following ways. We can either use the FlexPrep utility in MotionView interface to create the flexible bodies, or we can use HyperMesh to set up the model and run it in OptiStruct. The third way is for the advanced users to manually edit the FE input file before solving it in OptiStruct. In this method, we can include cards to reduce the size of the flexible body. However, in this chapter, we will build our flexible body using the FlexPrep utility tool. Once the FE solver creates the flex body in the H3D file format, it is imported to MBD model and connected to MBD model constraints, motion, forces, etc. Finally, the MBD model with the flexible body is simulated using MotionSolve, Adams, or other compatible Multibody Dynamics systems solver. Please note that Adams simulations require a file conversion from .h3d or .mnf. In this slide, I will explain the FlexPrep utility used in MotionView interface. It is found in the Tools menu. You need to click on the Flex Tools options in the toolbar and then click on the FlexPrep option to invoke the utility. I have pasted a screenshot from the MotionView GUI in this particular slide. I'll be switching now to the software to explain the dialog box in detail. So this is the MotionView GUI. Here you can find the Flex Tools in the menu bar, and then when you click on the Flex Tools, you need to click on the first option, which is called the FlexPrep, to invoke the FlexPrep utility dialog box. The first radio button is OptiStruct Flex Body Generation. So this radio button has three options in the drop-down menu. The first option is to create OptiStruct preparation file and also generate the Flex Body H3D file. The second option just creates the OptiStruct preparation file. And the third option, it creates the Flex Body H3D file using a pre-existing preparation file. The second radio button basically is used for translating the Flex Body files from one format to another. It has 5 options in the drop-down menu. In that, the first option is to translate the Adams MNF file into H3D file format. The second option is used for mirroring existing H3D flexible body across a particular plane. So we will be using this particular option in our exercise demo to mirror the left lower control arm to the right lower control arm. The third option is to translate the H3D file format into Adams MNF file format. The fourth option is to translate the H3D file format into Adams MTX file format. And the last option here is to translate the H3D file format into DADS file format. The third blank that you can see here is to import the FE model that you want to convert into the flexible body. So you can click on this folder icon here and you can select your required FE model that you want to convert into the flexible body. The fourth option here is your flexible body location. So you can give the location to store your flexible body and also the file name for your flexible body. And it will have a .h3d extension. The fifth option allows you to select the CMS method that you want to use. I have already covered the topic on how to choose the CMS methods earlier. So depending on the applications, we can select the CMS method. So you have the three CMS methods here, the Craig-Bampton, the Craig-Chang, and the Craig-Bampton geometric stiffness methods. And by default, it is the Craig-Bampton method. In the next option, you can specify the interface nodes. Please make sure that you separate the interface nodes with a plus sign, as shown in the syntax here. So for example, let me give you an illustration. So if your interface nodes are 98, 9898 and 9899, then you need to separate them using this plus sign. In the next option, you can specify the frequency cutoff type and its value. It is nothing but the user specified value for the number of modes of the flexible body. Here, you can specify the eigenvalue solver mode. And as I mentioned earlier, it is always defaulted to the Langsour's method for creating the flexible bodies, and it cannot be changed. On the right hand side of the dialog box, you can see the Create RBE2 Spiders option. If you click this particular option, it will invoke HyperMesh on the fly and allow you to convert all the RBE3 spiders connecting the interface nodes into RBE2 spiders. If you do not have these RBE3 spiders, then you really don't have to worry. But if you have these RBE3 spiders, then you should make sure that all the RBE3 spiders, which are the interface nodes in your flexible body, will be converted to the RBE2 spiders. Otherwise, you will be ending up with an error. Now, you can see this additional options tab on the dialog box. If you click this, it brings up this particular dialog box, wherein you need to check the perform stress recovery and the perform strain recovery options in order to get the stress and strain results. And the rest of the options in the dialog box you can leave as default. Now let's go back to our presentation. So now let's talk about the units. A consistent set of units is defined as, for example, one force unit is one mass unit into one acceleration unit. One acceleration unit is equal to one length unit divided by one time unit square. One density unit is basically one mass unit divided by one length unit cube. Fortunately, when creating a flexible body .htd file for MotionView, the values entered in the fields are not required to form a consistent set of units. For instance, the mass unit can be in kg while the length unit is in millimeters. OptiStruct manages the units for the flexible body output through the DTI unit cards. For units to be consistent between the flex body and the MDL model by which the flex body is utilized, the units of the FEA model must be identified. This unit information is stored in the .htd file, and all the affected parameters in the solver flex body matrix file are scaled accordingly. Now let's discuss about the quasi-static analysis and its solver settings. We will understand the following in this particular slide. The first thing is the definition of the quasi-static simulation or the quasi-static analysis, and then the solution overview. So definition. So physically, quasi-static means almost static, which means that the system is being driven extremely slowly so as to not engage any transient dynamics into the simulation results. Mathematically, quasi-static simulation is a sequence of static simulations performed over a given duration. It is useful when the model contains time-dependent forces or motions and the user is interested in the sequence of equilibrium configurations the model passes through for a given period of time. And this is the solution overview. The forces or motions are a function of time. Velocities, accelerations, and any time derivatives are set to 0. The generalized coordinates and constraint forces are the unknowns. MotionSolve calculates the static force balance problem at every time step. Governing equations are algebraic in nature and solved with Newton-Raphson method. So, we'll be creating and simulating the flexible lower control arm in our exercise demo. As you can see, we can get the suspension system which is already there in MotionView library, and then after importing the suspension system, which has the rigid lower control arm, we'll be replacing it with the flexible lower control arm, both on the left hand side as well as on the right hand side. And then when we perform the analysis and run the animation, we can see the stress and strain distribution on the lower control arms. So the steps that we'll be following to do this particular simulation are: in step 1, we'll be using the FlexPrep utility tool to generate a flexible body. Next, we'll be creating the RBE2 spiders, meaning there are RBE3 spiders in the FE model. So we'll be going to HyperMesh and we'll be converting the RBE3 spiders to RBE2 spiders to make the center node independent. In step 3, we'll be ensuring that the interface nodes are independent. In the next step, we return to the FlexPrep utility and run OptiStruct. In step 5, we'll view the model and verify the results. In step 6, we'll be using the FlexPrep utility to mirror a flexible body. So here, we'll be mirroring the left lower control arm to get the right lower control arm. In step 7, we'll be replacing the rigid bodies with the flex bodies and solving it in MotionSolve. And in step 8, we'll be viewing MotionSolve flexible body results in HyperView. So I'll be doing the exercise demo in the next video. Thank you. Welcome back everyone to the video lecture series on flexible bodies. For the sake of convenience, I have merged the third and the fourth video together so that the full exercise demo is covered in one video only. So now, let me begin with the exercise demo. So click on the Flex Tools option and then the Flex Prep option to invoke the Flex Prep dialog box. Now, you can leave the first option as it is because we are creating the OptiStruct PRP file and we're also generating the H3D Flex Body file. So we'll keep the first option as it is. Next, we need to load the .fem file, that is the FEA file that we want to convert into the flex body. So let's load our .fem file. So it's in chapter 12. So first let's work with the left lower control arm. So I'll select this file SLA flex left.fem. So this gets loaded in. Now let me go to the fourth option. Here I will be saving the file, my flex body file, as SLA flex left. I'll call it test1 and the file extension will be .h3d. So then I hit save. So I want to keep the component mode synthesis method as Craig Bampton method, and then for the next option I want to specify the interface nodes. So for my model, the interface nodes are 4887, and if you can remember, I had mentioned that we need to separate the interface nodes with the plus symbol. So I'll be separating the interface nodes with the plus symbol. So the first interface node is 4887, the second one is 4888, and the next one is 4890. And the next option, which is the cutoff type and the value, I'll leave it as it is. Okay, so this is the maximum modes requested by the user, so I leave this as 15, and by default the solver mode is Lanxos, and I will leave the rest of the options as it is. So I'll go to the additional options and I will check on the perform stress recovery and also the perform strain recovery options in order to get the stress and strain results for the body. Then I close this. Now, I hope you all remember what I told you in the previous video. We need to convert all the RBE3 spiders into RBE2 spiders. So let me just click on this particular option which says create RBE2 spiders. So when you click this, HyperMesh will be invoked on the fly. Okay, so we can see that happening now. Let's give it some time. Yes, so it took you directly to the HyperMesh GUI. Okay, so first thing what we need to do here is go to this particular option which says user profile, Okay, and we need to select this as OptiStruct and say OK. So once we do that, and now if we zoom in, we can see that this is RB2 spider. So no problem with that. Now we need to create an RB2 spider here. So we come here and click on the utility tab and then the user tab here. So and then click on the super spider and select one of the nodes here and say proceed. So automatically we get a RB2 spider that's created at this particular interface node. Next, then we need to convert them into RB2 spiders. So let's check what the spiders are. So let's go to the card edit and then change this particular option to elements and then select these elements. Say edit. So what does it say? RB3 here. So these, or the spider is basically it's an RB3 spider. Okay. So we need to convert this to RB2. Now let me check with the other spider that we have here. So again, go to the same option, card edit. Click on these elements, say edit. These are RB2. So this is all fine. So what we need to do is we need to convert these elements from RB3 to RB2 before doing anything with our flex body. Okay. So still keep in mind, this is not a flex body. It's just the OptiStruct file. It's a .fem file. And once we run our flex prep utility, we'll be getting the .h3d file. So this is just a pre-processing part of it. Okay. Now I'll be converting the RB3 spider into RB2 spider. So please concentrate on how I do that. So click on the 1D option here. Okay. The 1D radio button basically. Now you can go to config edit option here and select these elements and then click on new config and select rigid link as the option, and then you can hit on switch button. So this means that the RB3 spider has been converted to RB2 spider. Now you return and you can check that. So go to the same option, which is the card edit option here, and click on the spider and then say edit. So you can see that it is converted to the RB2 spider. So now we're all set. So once this is done, you can just say save and close. So you can save this particular file as capital SLA flex left test1.fem. Okay. So yeah, it will be saving it in .fem format itself. So no need to worry about that. Okay. So once it gets saved, I think you guys observe that it directly came back to MotionView. Okay. So now that's done. So now we should continue with the process to build our flexible body. So I'm just checking once again if the additional options, these two options are checked. And yes, these two options are checked to perform stress recovery and also the strain recovery. Okay, now let's close this and say OK. So OptiStruct runs in the background to generate the flexible body. Okay, so it generates this particular report, which means that, and it says end of report, and we don't see any errors. So it has successfully completed converting the .fem file to the .h3d file, which is nothing but converting the FE model into the flex body. Say OK. Now what you can do is just switch to HyperView. So if you want to just take a look at the flex body, just click on HyperView and load that model. Okay. So this is the SLA flex left test1.h3d. So you've loaded the model. And these are the interface nodes that you can see on the screen. Okay. And now let me just do a contour plot. So here we have displacement, stress and strain. Okay, so let me just select displacement and say apply, and here are the different modes and the frequencies. So let me just select a particular mode, and I will set this particular option to set modal animation and then click play. So I'm just reducing the speed of the animation. So you can see that the maximum displacement at this particular frequency happens in this region. Okay. So this is your flexible lower control arm, and this is on the left hand side of suspension. Okay. Now let's just go back to motion view. Okay, so now we've generated the left lower control arm. So now what we have to do is we need to again use the flex prep utility to basically mirror the left lower control arm and generate the right lower control arm. So for that we need to select the second option or the second radio button, which says translation of flexible body files. So here select the second option, which says mirror existing H3D flex body, and then here you need to specify the original H3D file. So you need to click on the folder option here and then go back to the same location. Okay, so we have our first flexible body file here, which is on the left hand side of suspension. So we take this as the original file, say open, and then specify the mirrored H3D file name. So the one you want to mirror it as. So we need to change from left to right, right? So just click on this particular option, select the same file, but make sure that you change from left to right. Okay, then hit save, and you will be mirroring it across the XZ plane. Okay, and then say OK, and it's done. So instead of again creating the whole flex body for the right lower control arm, this is how simple it is in motion view using the flex prep utility. You have the left lower control arm, you just have to mirror it across a particular plane, which is the XZ plane in this case, to get the right lower control arm. And now say OK. And now what we'll do is we'll just go to the model option here, assembly wizard. So this I'm doing to get the suspension system, the built-in suspension system that's available in MotionView library. So first I will load in that, and it has a rigid lower control arms. So I'll be loading in this particular model. So I'll be selecting the front end only, then hit on next option and then say no driveline, select next. Here I'll be changing the suspension system to front SLA suspension one piece LCA. So make sure you change from the default MacPherson suspension to the third option here. Okay. Then click on next, next, again next. So you can leave these options as it is, and then again click on next. So here leave the compliant option as yes, and then say finish. So you got this suspension system from the MotionView model library. Okay, and you can see that, so these are the lower control arms, the red bars that you can see, these are the lower control arms. Okay, and these are now rigid bodies. Okay, they're modeled as rigid bodies. So what we'll be doing is, we already have a flexible body files, so we'll be replacing these rigid body files with the flexible body, and then we'll be running our analysis. Okay, and the analysis that we'll be running will be a static ride analysis. So go to the analysis option, select the task wizard, and here for the task or the type of analysis, we'll be selecting the static ride analysis, say next, and then finish. So you can leave all these parameters as it is, next, finish. Okay, so you got this particular test rig for the static ride analysis. Now your only job is to replace these rigid lower control arms with a flexible lower control arms that you just created. Okay, so for that you can just expand the front SLA suspension, this particular model, expand that, and under that you can expand the bodies, and under the bodies you can go to lower control arm. So this highlights the lower control arms. Now what you can do is, it's already in properties, uncheck the symmetric properties and you get this particular dialog box. Okay, so when you get this particular dialog box, say retain the values. So just hit on retain. So it retained the values for the left hand side and the right hand side. And now check this flex body option. So it asks you whether you want both the sides to be deformable. So yeah, you want both the left and the right lower control arms to be deformable or flexible bodies. So hit on yes. Okay, so you're on the left hand side now. So you need to basically load in the flexible body file, which is nothing but the .htd file for the left lower control arm. So click on this folder option. So you have these two flex bodies available. So click on the SLA flex left and say open, so that it gets loaded in. And once you get this, just click on the notes. Why I do that is because you can see that the model is just brought in, the flex body is just brought in, but it is not connected yet. Okay, so for that you need to basically put a check mark on this particular option which says only search for interface nodes. Make sure only this is checked and then hit on find all. Okay, so it finds all the interface nodes and then you can see that it is offset by this distance. So then you can say align all and you'll get a particular warning message saying, are you sure that you want to move the listed entities? Say yes. So when you do that, you can see that you can close this now. So you can see that it is now perfectly connected to the suspension system. Okay, the left lower control arm. Now I'll be doing the same steps for even the right lower control arm. I'll be switching the tab to the right. I'll be going to the folder option and selecting the SLA flex right test 1 and say open. So once you get this, go to the notes. Make sure that this is checked. Only search interface nodes and then click on find all. So you can see that it is offset by this distance. So just say align all and then yes for this particular option. So this perfectly goes and connects at the interface nodes with the multi-body dynamic system. In this case, it's a suspension system. And one more thing that you got to remember is here, if you click on the left tab, so and go to the modes, so you can see that the first 6 boxes are left unchecked. So these are the 6 rigid body modes and we don't want to see any rigid body modes. So hence we're leaving this unchecked. So leave this as it is. And the total number of modes for the flexible body will be equal to 39. Okay. Say close. The same thing even for the right hand side. Okay. So go to the modes. So when you go to the modes, you can see that the first 6 are the rigid body modes which are left unchecked. And these are all the flexible body modes which are all checked. You again have 39 flexible body modes. Okay. Say close. So once this is done, we're all set for analysis. Just click on run. And the simulation type, because it's a static right analysis, it's a quasi-static analysis. So you can go and click on the folder and you can save your particular file as SLA flex model test1.xml So save it. And the end time, I don't want it to be for 10 seconds. So I'll just reduce it to like 4 seconds. And the print interval, I'll be using 0.01. And you can leave the rest of the options as it is and hit on run. So now MotionSolve runs in the background and you can see how fast you get the solution. Okay, it's just in a matter of few seconds. So now MotionSolve is running in the background and this is the message log that you can see. Okay, so yes, it's all done. Say close. I can close for this. And now click on animate. So when you click on animate, HyperView opens in the second window. So now let's go to contour plot and then just select these two components because we just want the contour plots for these two control arms, right? So we go there, click on components, select the left lower control arm and the right lower control arm. Okay, then close this and say apply. So you can see the contours now and hit on animate. So now you can see the animation. Okay, so this is basically the result type is displacement. So this is the displacement. And you can see the maximum displacement is at this particular location. Okay. So similarly even here. And because we have checked the perform stress recovery and strain recovery options, it's also calculated the stress and strains. So you can just click on stress and say apply. And you will get those results. And you can, if you zoom in, you can see that the maximum stress is at around this location. Okay, so and this is only possible if you use the flex bodies, and we cannot capture this particular deformations in rigid bodies. Okay, so that's the application of the flexible bodies. So yes, we are done with this exercise demo. I can pause it. So one thing I'd like to discuss before I end this particular video is some tips on modeling the flexible bodies. Okay, so the first main thing is to avoid selecting the interface nodes that are very close to each other. So please make sure you do this because this increases the likelihood of the modes being almost linearly dependent and which can cause a difficulty in the convergence of the solution. So make sure that the interface nodes are not too close to each other. The second tip is basically deactivating modes in your flexible body will gain computational speed, but at the same time at the sacrifice of accuracy. So please keep in mind that if you want accurate results, you can keep the flexible body modes, you can keep them all checked. What I mean by this is, let me just go back to the MotionView GUI. So I'll just expand this. So here, if I go to the lower control arm, and here if I go to the modes, so make sure that all these options are kept checked. If you uncheck any of these flexible body modes, for sure the size of your animation file will be reduced, but the results won't be that accurate. Okay. Next, fine mesh is usually not necessary for the component mode synthesis, as only a few fixed interface eigen modes are needed. But most often people do use a very fine mesh rather than a coarse mesh. So depending upon your model, you can choose what type of mesh you want. Like in a sense, the degree of the fineness of the mesh you can choose depending upon the models you will be simulating. So you can choose fine mesh if you want the stress or strain computed in the body. And also, please use the CBG, that's the Craig-Bampton geometric stiffness method when the deformations are above the linear range. Okay, so that brings you to the end of this lecture series on flexible bodies. Thank you. Welcome back to the 13th chapter of Multibody Dynamics using Altair, HyperWorks, MotionView, MotionSolve. Till now, we have learned how to build mechanisms, apply joints, forces, motion, contacts, etc. And we've also learned regarding the trending technological developments in multibody dynamics using flexible bodies. Now, it is time to put in all that we've learned so far in building more complex and parametric systems. The subsequent chapters will help you in building a full model using a modular building approach and setting up parametric relation between the various parameters involved in the simulation. You will learn to appreciate the usefulness of these chapters once you go on to build complex models which are a combination of two or more subsystems. From chapter 13 to 15, you will build a simple car model from various systems of a model that you will be either creating or importing and attaching to the rest of your model. Along the way, you will also learn regarding the various building blocks of the MotionView models. In this chapter, we will discuss the following topics: container entities, creating, importing, and exporting systems, and the spring damper entity in MotionView, which we'll be using in the exercise. Now let's move on to the first topic in this chapter, where I will be providing an overview on the container entities. MotionView basically encourages a modular model building approach. This means that various entities can be grouped into containers and arranged into models, basically into a systematic collection of different subsystems. This allows a model of any level of complexity to be systematically arranged in a hierarchical manner. This organized approach helps the analyst and also his or her fellow analysts to work on a certain complex model in an organization simultaneously, though it takes some initial efforts to plan and organize the model in the right manner. The major benefits of using this particular type of approach includes the following. It provides a clear understanding of various subsystems or the assemblies involved in a complex system. Any person in your team can easily identify the content in your model, no matter how complex your model may be, just by visualizing the model tree in the model browser. The second advantage is that if the model is not running in the correct manner, that is, if there are any issues associated with the model, these container entities can be deactivated or activated in just one click, which is really useful while debugging a model. Another major advantage is that these sub-assemblies can be reused in different models. The container entities can be exported to a definition file and can be easily reused in a different model that requires a similar subsystem present in your model. For instance, take an example of a parking brake mechanism, which consists of several components, joints, forces, and other entities. This system definition can be exported to a system definition file and can be reused multiple times in different vehicle models. There are basically three types of container entities: system, assembly, and analysis. Systems are basically intended for modeling mechanisms. Assemblies are intended for modeling mechanisms using external files for reference. And analysis are intended for performing analysis, but may also include modeling entities. But in this current chapter, we will focus on the systems. System may contain any other modeling entities like points, bodies, forces, joints, etc. It can be reused as many times as you like. A system can be a child of another system, or other container entities. The image below shows a simple model of a hatchback door of a car. The model has been arranged into a system called as the hatchback system, which in turn has two subsystems, the door system and the damper system. The door system contains the door along with its hinge joint, and the damper system contains the damper bodies along with their joints with the ground and the door. These systems can also be connected to other systems via attachments, which you will be learning in the upcoming chapters. The parent or the subsystems created can be easily reused for other applications as per the requirements of the user. Okay, now let's go to the MotionView graphical user interface to learn how to create, import, and export systems. So systems can be created in two ways. One way is by right-clicking on this particular icon, which brings up the Add System or Assembly dialog box. The other way of getting to this particular Add System dialog box is by right-clicking on the model, going to the Add option, and then clicking on this System or Assembly. So it takes you to the same Add System or Assembly dialog box. And then you can click on the System Radio button and then click on the Next button. So when you do this, this indicates that the parent system is going to be your model, which is the system that is created by default when you start your MotionView. And then you need to define the variable name, the label name, and the definition name of the system that you'll be creating. So please note that the variable name can only be changed during the creation of a system and cannot be changed during the model building process, whereas the label name can be changed during the model building process. The definition name basically defines the single template of the system, which can be reused multiple times to create multiple systems. Also, please note that the system is always created within the parent system that has been selected. So say in case you have another system, say model, and a second system called as model A, then you need to select which particular parent system that you want to assign this subsystem to. So in this particular case, we have just the model as the parent subsystem. Okay. After giving the appropriate variable names, label name, and the definition name, you can click on OK, and you can see that this particular system called as system 0 is created under the parent system model. Okay, now let's move on to the importing and exporting of systems. So when you create a particular system, you can see that there is this import export tab in your systems panel. So you can, for importing a system, you can click on the import radio button and you can select a particular file and then say open. Okay, and then click on import. So it's that easy to create or to import a particular system. Next, to export a particular system, you need to click on the export button and then select the required system and select the required system and then click on quick export. The system can also be exported with or without the model topology and with or without property data. So these options allow you to separate the data from the topology if desired. So that can be done by enabling and disabling this particular checkbox for the property data. Okay, now let me go back to the presentation. So we've covered all these topics in the graphical user interface. Now coming to the last topic of this chapter, which is regarding the spring damper entity and I'm explaining regarding the spring damper entity because we'll be using this in the exercise. The spring damper panel allows you to create and edit the properties of the spring damper force elements. So it will be better if I explain this by using the graphical user interface. So let me switch back to the MotionView graphical user interface. And here you can find the icon for the spring damper entity. So you can right click on this particular icon and it brings up the Add Spring Damper dialog box. So here you can give the label name for your spring damper and you can also give the variable name. So as I mentioned earlier, the variable name can only be edited during the creation of this particular entity and cannot be changed during the model building process. And you can create two types of spring damper entities. One is the coil spring and the other one is the torsion spring. The coil spring generates a translational line of action between 2 points on the two bodies, that is a function of the distance and the relative velocity between the 2 points, whereas the torsion spring produces a moment between two bodies, that is a function of the relative angular displacement and the relative angular velocity between the two bodies. So first, let's say we select coil spring. Okay, and you can also create explicit graphics for this particular coil spring that you're creating. And you'll understand this in more detail when we do the exercise for this particular chapter. Okay, so then just click on OK. And then this is the spring damper panel. So you can see that the spring damper system that you've selected is the coil spring. So you'll have to select body 1 to which the spring damper is attached. And then you'll have to select the body 2 to which the spring damper is attached, and then the first point on the first body to which a spring damper is going to be attached, and then the second point on the second body. So if you change this to torsion spring, you can see that these options change, wherein you'll have to specify the body 1 and body 2 to which it will be attached, and also the origin point to which the torsion spring damper will be attached, and also you need to specify the alignment axis. Either you can specify a point or a vector which can be along global x, y, z. And here in the properties tab, you can specify the stiffness and the damping ratio for your particular spring damper entity. Okay, and in the preload, you can specify the preload or the free angle in case of the torsion spring damper. But if you change it to coil spring, then you can give the preload value or a free length or a combination of both. Now let me switch back to the presentation to explain this preload in detail. So preload is basically the initial force or the torque in the spring in the model position. The total preload, which is Fp, is given by this particular equation, which is equal to P, which is the preload value, plus stiffness into the initial length minus the final length of the spring. Okay, so MotionView creates a coil spring damper with a default value free length as the distance between the two endpoints that you've specified while creating your spring damper entity. Okay, so you'll understand this in more detail when we do the exercise for this particular chapter. Okay. So now it's time to move on to the demo on chapter 13. Thank you. Welcome back to chapter 14 of Multibody Dynamics using Altair HyperWorks, MotionView, MotionSolve. In the penultimate chapter of this course, we will learn regarding the attachments and datasets. which are very important during the construction of a model in the modular approach. First, let's concentrate on the attachments. During the assembly of a model with different subsystems, it is often necessary to link or refer entities in one container to the entities in another container, which may include systems, assemblies, etc. To retain modularity of the container entity so that they can be reused in a different context, it is recommended that you define connections to external entities by declaring them as attachments. To make you all understand better, I will give you some physical analogies that you can relate to. The ports on an electric device can be considered as the best physical analogy for attachments. These ports are local to the device and act as media to connect an external device. For example, an HDMI port on a TV, which allows a DVD player to provide data to the TV to display. Now, for those who have a background in programming, I will also share another analogy that you can relate to. The argument that is passed in a function can be compared to attachments. For example, consider you have defined the following pseudo function, okay, times 2. So this is basically double times input variable, and the result is going to be 2 times input variable. In this case, the attachment can be compared as an analogy to input variable. The pseudo function times 2 that we created can be used as many times as we like by passing different arguments like x is equal to times 2 of 2, y is equal to times 2 of 4, etc. It is also important to note that the argument input variable must be used within the function for the function to work correctly. Similarly, an attachment must be used within the function. Similarly, an attachment must be used within the system created by you for it to function in the right manner. Since attachments is a very important topic and needs to be understood thoroughly before proceeding further, I will demonstrate a quick example in MotionView to help you understand the usefulness of attachments. I will first show you the wrong way of doing it without using attachments, and then I will show you the right approach. Okay, now let me switch back to the graphical user interface. Okay, consider the scenario. You're user 1 and your colleague is user 2. You create a subsystem in your parent system model, and the joint that you'll be defining in your subsystem needs to be used by your colleague, but he wants to specify different entities for that particular joint. So let's see how to do this in the wrong way. So say user 1 has defined a body and he has also defined a point, just 0.0. And then user 1 is going to create a system, okay, called as system 0. Say OK. And then user 1 is going to create another body, reference entity, body within system 0. Okay, so let's just call this body A. Okay, and then user 1 also wants to create a joint, add constraint joint. So let's call this joint as joint A. Okay, and he wants this joint to be defined between body 1, which is referring to body 0, which is in the global parent system model, and body 2 is the local entity within the system 0, which is body A, and the origin is basically at point 0 in the global parent system model. Okay, so this is the model of user 1 within system 0. Okay, so now what user 1 is going to do is you'll be exporting the system 0. So let's go to the import export tab, click on export. So in this folder called as test, let's create a system called as system 0. That's basically created by user 1. Save, click on quick export. Okay, so now the system 0 has been exported as a model definition file. Now let's refresh the session. So this represents the graphical user interface of user 2. So this user 2 has a body named N, okay, and he also has point named N, okay, and now what he wants to do is make use of the system that was created by user 1, okay, and replace the body 0 and the point 0 that was referenced in the joint by body N and point N that is created by user 2. Okay, so for that, first the user 2 needs to import the system that is created by user 1. So you go to the import export tab, go to the import option, and then click on the system 0 that was created by user 1. Open, and then click on import. Say OK. So now you can expand system 0 and you can expand joints. And when you click on joint A, you can see that body 1 and the origin are unresolved. So now this is the wrong way of doing it. So even though he wants to reference body N and point N, the system that was created by user 1 to help user 2 is of no use. So now let's go through the right way of doing it by making use of attachments. Okay, so file, new session. So now this is the graphical user interface of user 1. So what he's going to do is create body 0 and create a point 0, and then he's also going to create a system called system A. Okay, so right click on this, add, go to system or assembly, click on next. I'll just rename this as system A. Okay, so once this is done, user 1 is going to create a reference entity which is body as body A. Okay, and he's also now going to create attachments. Okay, so click on the system A, go to the attachments tab and click on add. So once you do this, you can specify the attachment label name. I'll call this attachment body 0. Okay, and select the type to be body. Okay, and I can also change the variable name right now because I won't be able to do it later. So attachment body 0. Okay, and now once I create the attachment, then I need to resolve the attachment. So click on the body and select the body 0 and select the body 0 that was basically specified in the parent system model. Okay, click on OK. Now this user 1 also has to create another attachment for the point that needs to be referred. So I will rename this as attachment point 0. Okay, so the variable name will be changed to attachment point 0. Okay, and the type needs to be changed to point. And then click on OK. So once the attachment is created, you need to go to point and click on point 0, which is referred in the global parent system, which is model. Click on OK. So once this is done, user 1 is also going to create a joint called as joint A. Okay, click on OK after renaming the variable name to, and then now body 1, you're not going to select body 0. Instead, you'll be expanding system A, and under attachments you'll be selecting attachment body 0. Okay, and it turns blue in color, showing that now it is parametrically defined. Next, for body 2, it will be something that will be defined locally. Okay, the body that was created within system A, which is body A. And the origin will be again under system. If you go to attachments, you have attachment point 0. Okay, so now you've created the attachment and also resolved it in the right manner. So now what user 2 wants to do is make use of this particular joint A and attach his body 0 and his point 0 that he's created in his parent model. Okay, so once you do this, what you can do is go ahead and export the system. So I'll go to import export tab, click on export, and then I'll be renaming this as system A. Okay, so save and click on quick export. So now user 1 has created a subsystem called system A, and he is exported it to be used by user 2 by creating attachments. Now let's refresh the session. Okay, so this represents the graphical user interface of user 2. So what he's going to do is first click on model and import the system that was created by user 1, which is system A. So open and import. Click on OK. So now this user 2 is going to create a body called body 0 and a point called point 0. Okay, now if you go ahead and click on joint A, you can see that it is no more not resolved. Instead, it is referred to body 0 and point 0 that is referred in the parent model of user 2. So this is the way how you can make use of attachments, and it will help in the modular building approach and also for the reusability of your model or the entities that are created between two users. Okay, so I hope now it's clear. Let's go back to the presentation. So just to summarize what I have shown in the demo. So system 0 will be the parent system. And we have another system which is system B under system 0. And then system BA is another system under system B. So if an entity in system BA requires to be referenced from system 0, then attachments need to be created between system BA and system B, and also between system B and system 0. Only then you can reference something from system BA in system 0. Okay. So before moving to the next topic, I hope this is clear to everyone, because attachments are really useful and need to be used when you are building complex models. And also, to just recapitulate the process, please remember there are 3 important steps involved in attachments. The first step is that you need to create them, and then they need to be resolved, and then the third step is to use them. Okay, so now let me go back to the graphical user interface to quickly recapitulate these steps on creating the attachments. Okay, so once you go to a particular system, you need to click on the attachments tab and then click on the add option. So this brings up the add attachment dialog box. So here you need to specify the label name for your attachment, and then you're going to specify the variable name, and then select from the drop down list the type of attachment that needs to be specified. Okay, these are the different types of attachments that exist in MotionView, and you can select any of them and then click on OK. So once an attachment is created, the second step is to go ahead and resolve. So you need to go and select the particular body that you want to create as an attachment. Okay, so for example, body 0. Okay, so this is the way how you create attachments in MotionView. And this topic will become more clear when we do the exercise on chapter 14. Let me go back to the presentation. And let's move on to the next topic of this chapter, which is on datasets. So now consider that you're building a suspension system model. You need to define the stiffness and damping values for several spring damper entities in your model. Let's say you need to perform a static ride analysis using different values of stiffness and damping for the various spring damper entities that you've modeled. Can you imagine how difficult it would be to change the value for each and every entity in your model? It would surely be challenging, time consuming, and I'm sure that you'll be bound to make mistakes. So instead, you can create design variables called stiffness and damping ratio and parameterize all the entities using these design variables. So you just have to change the value once and it automatically gets updated in all the entities using these datasets. So a dataset in MotionView is a group of design variables. It can be of different types. So design variables are basically variables that exist in the design time in MotionView for the purpose of building a model. They no longer exist when a MotionSolve model is created. This can be used to help define other entities in your model and make modeling simpler, easier, and more organized. And datasets also have their application in design of experiments, optimization, and stochastic analysis. So these are the different types of datasets in MotionView, which include real, string, Boolean, integer, and options. So datasets are organized in tables according to the object. So please note that the fields for variable name and object type cannot be changed in the dataset panel. Now let me quickly switch back to the graphical user interface to show how to create these datasets. So there are two ways of creating datasets. You can simply go to this particular icon on your toolbar, right click on it to create a dataset, or you can go to your model, add, go to the general MDL entity and click on dataset. So these are the two ways used to create datasets. Then you need to specify the label name and the variable name and click on OK. So in this dataset panel, if you go to data members, you can go ahead and click on add option and select the required type of data set that you want to enter. For example, real. Okay, you can specify its a variable name and variable name. You can specify its variable name and label name and click on OK. And you can check this. You can go ahead and modify if you want. Okay. And also you can, if you no longer want to use a particular dataset, you can just select this and delete. Okay, so this is the way how you'll be creating datasets in your model. And even this topic will become more clear once we do the demo on this particular chapter. Okay. So now let's move on to the demo on chapter 14. Welcome back to the demo on exercise 13. This exercise is the start of a series of exercises to build a simple car model. The car model is not a realistic one. The intent is to use this particular exercise in introducing many basic modeling ideas in MotionView that are generally applicable to all models. In the end, you will be building a full vehicle model, the front and rear suspension, a body, and a steering system, and also learn how to submit more complex analysis. So let us start by opening the model. So File, Open, Model, and you'll be selecting the simple car model in chapter 13 folder. Okay, so there are no errors detected in this particular model. Say clear. Okay, now first, before adding entities to this particular model, let's go on exploring what's already there in the model. So it has three bodies, which is the ground body that is created by default, knuckle, and a body for the wheel and tire. And it has two graphics for the wheel and tire and the knuckle. It also has two joints, one for the wheel to knuckle, which is basically a revolute joint, and then the knuckle to body, which is a cylindrical joint. It has three motion. One is the motion which represents the motion of the wheel. Next is the motion that represents the motion of the steering, and then the motion that represents the static ride motion. And then we also have 5 hard points that are created. The global origin, which is created by default, the wheel center, the knuckle top, the knuckle center of mass, and the damper middle. And as you can see, as I click on these hard points, you may notice something interesting. It is pointing out to 2 points. This is because these points have been created as pairs and not a single entity. Okay, so I will show that when I'm going to create the spring damper entity for this particular model. So thus the right hand side or the right point will be parameterized with respect to the left point. Okay, so these points that are created are in pairs. So whenever you're dealing with models that contain the left hand side, which is symmetrical to right hand side, then you can use the pair type when you're creating the different entities. Okay, now we've explored what's there in this particular model. I'll just click on run and run this model. Okay, let's go to results. Click on animate. Okay, so this is the animation that you can see on the screen in the HyperView software. Okay, let's go back to MotionView and let's start adding the spring damper entity. Okay, so for that, there are two ways to create the spring damper entity. First one is to right click on this particular icon, or the second method is to go to model, right click, add. Okay, and then you need to go to force entity and then click on spring damper. Okay, so these are the two ways of adding the spring damper. So let's just click on the icon that's there on the toolbar, which is the most easiest way of doing it, and add a spring damper. And we want to create a coil spring, but we want it to be a pair. Okay, so at one shot we are creating two coil springs for the left hand side and for the right hand side. And I also want explicit graphics associated with this particular coil spring. So I am putting a check mark for this option. After doing this, you can click on OK. Now you need to specify body 1, which is the ground body, and the body 2, which is the knuckle, and then the point 1, which will be the knuckle top, which is nothing but this point, and the point 2 is the knuckle center of mass, which is this. So you can see that the coil spring is now created along with its explicit graphics. And I want to make sure that I put a check mark on this particular option, which is symmetric properties. And when I click on this, I get this particular set symmetry dialog box, which asks which side should be the master side. So I can either click on the left or the right, but for now I'll be clicking on the left option. Okay, so whatever properties you apply on the left hand side will get automatically applied to the right hand side too. Okay, so now let's go to properties. So you need to specify the stiffness and the damping ratio for this spring damper. So let's give a value of 100 for the stiffness and say 10 for the damping ratio. Okay, and you can click on the preload tab and you can see that a default value for the free length is already defined here based on the starting point and the ending point of this coil spring. Now what we're going to do is we're going to modify the graphics for this particular coil spring. For that, I will go to the graphic that's been created. Okay, and please note that whatever changes now I do to this radius of this particular spring and also the visualization is just for the sake of visualization. It is not going to affect anything during your model building process. Okay, so here the number of coils or the radius of this particular spring, if I change, it will be just for the sake of visualization. It's not going to alter anything during your model building process. So please keep in mind and don't get confused. Okay, so this is just to make the components or the entities look more prominent. So I'll be changing this value from 35 to 70. You can see that if I just change it for the left hand side, the right hand side also changes automatically. Okay, and just for the sake of visualization, let's select alloy for to change its color, and you can go to the right hand side and also click on alloy to change its color. Okay, so now that's the explicit graphics for the coil. Okay, now it's time to go ahead and create explicit graphics for the damper. Okay, so for that, let's go to the graphics option. Let's start giving meaningful names. Okay, let's call it damper top. And let's also change the variable name. And as I've mentioned multiple times earlier, the variable name can only be changed during the creation of a particular entity. So let me give the same name, damper top. Okay, and I want to create a pair, so I'll leave this type as it is, and I want the entity type to be a cylinder. Okay, and then I click on OK. Now I need to select the parent body, origin, and the direction for this graphic. So for this parent body, I'll be selecting the ground body, and for the origin or the starting point of this graphic or the cylinder, I'll be clicking on point and then selecting the knuckle top. Okay, and then for the direction, I'll be selecting damper middle and then click on OK. You can see that the small tiny cylinder is created now. Okay, so I want to increase the radius of that cylinder that's been created. So I will go to properties and change the radius from 10 mm to 60 mm. Okay, so that the graphic becomes more prominent. And the color, I want it to be like aluminum alloy. So I go to the left and right tabs and change it to aluminum alloy. But again, please remember that you're not changing anything in your modeling. It's just for the sake of visualization you're doing this. Now we've created a graphic for the damper top. Now let's also create a graphic for the damper bottom in the similar manner. So right click on this graphic option. Let's give meaningful names again. Damper bottom. Even here, the variable name should be changed to damper bottom. And I want the type to be pair and the entity type to be cylinder. So click on OK. So go to the connectivity tab. So here for the parent body, select knuckle. And for the starting point of this, select knuckle center of mass. And the ending point, select damper middle. Okay, so you can see that this cylinder is created now. Now again, let's change the properties from 10 mm to say like 40 mm. And the color, you can change it to aluminum alloy. Okay, for both the left hand side and the right hand side. Okay, now this is done. Now it's time to go ahead and create output for the spring. So there are two ways, as I mentioned earlier, to create the output. One is to right click on this particular icon, or you can go to the model browser, say add, and go to general MDL entity and then click on output. Okay, it's basically the same thing. And here I will call it spring damper force. Okay, spring damper force. And I'll change the variable name to spring damper force. And here one more important thing to note is that the label name can have these dashes in between them, but the variable name cannot take these dashes. Okay, so for example, just see when I change it just to dash and try to create an output with this particular label name and this variable name, it's going to give me an error. Okay, so it says that please specify a valid variable name. So that's the reason the variable name should contain only underscores and no spaces also. Okay, it should be just underscores. So now click on OK. So now I'll be changing the displacement type to I'll be changing the type to force. Okay, and it will be on a entity itself, but it won't be on a particular body. Okay, go to this drop down list and select the spring damper. Okay, so once you do that, click on the spring damper and select spring damper left and then click on OK. Now let's animate the model and test the model whether it's working fine. So let's go to run and click on the run option. Okay, so you can close this and click on animate. So refresh. So this is your hyperview. So you can click on animate to see how this model works. Okay, so I also want to visualize the forces here. So what I can do is I can go to the vector option here and the result type should be force, and I want to display both the X, Y and Z components, and go to the display tab. Here the size you can select by magnitude and you can give a particular value. So let's give it around like 0.02. Okay, and then say hit on apply and then click on animate. Okay, so you can see the forces, the force vector that's actually acting on this particular spring damper. Okay, so the animation looks fine. So let's go back to MotionView. Okay, now we've come back to the MotionView graphical user interface. Now it's time to create a system from this model so that it can be reused later to create a simple vehicle. Okay, so here let's go and click on the model, right click and say add system or assembly. So you get this add system or assembly dialog box. You can click on system radio button and then click on next. Now let's start giving meaningful names for our system. So for the variable name, let's give simple suspension. Okay, here its label name is going to be simple suspension. And please note that in the label name, spaces are allowed, but in the variable name, it's just going to be the underscores. Okay, so even here, I will change it to simple suspension. Okay, once I do this, I click on OK. So you have this new subsystem that's created, which is simple suspension. Now what I'm going to do is cut and paste all that I've created in this model into the simple suspension. Okay, please take a look at this carefully. So I'll be selecting the bodies, the graphics, joints, motions, outputs, points, and the spring damper. Okay, so and then I'm going to say right click, cut, and I'm going to click on this, right click, and I'll say paste. Okay, it's that simple. So all those entities that I created in the parent model, I've basically cut those and I've pasted it in the simple suspension subsystem. Okay, so you can see that all the required graphics, joints, motions, okay, outputs, the spring dampers, all that they have been successfully pasted into the simple suspension system. Now let's go ahead and run this particular subsystem to see if it works correctly. So let me save this as simple simple suspension system. Okay, So save. Okay, now I'll be running this. Okay, it's completed. So click on animate. It launches HyperView. Yes, it does work in the correct manner. Okay, so you can pause this. Go back to your motion view. Okay, now what we need to do is we need to export this particular system for our future views. Okay, so for this, click on the Import Export tab and then click on the Export option. Okay, and then select the file. So you'll give a file name, call it Simple Suspension System. So that's been already created. So go to all files and it's basically the simple suspension system.mdl. Okay, it's not here. So, okay, let's do one thing. Go here and create that simple suspension system. Okay, so it will be saved as a model definition file called the simple suspension system. And after you do this, just click on quick export. Okay, so now if you go to the same folder, you can see that it is created. So let's go there. Let's go to desktop. So here, let's go to model files. So in model files, chapter 13. Okay, you can see that the simple suspension system.mdl has been created. Okay, so that's done. Now what we'll do is we'll close this session. Okay, so I'll open a new session and now I'll try to import that system that I've created. Okay, so right click on this. So just click on the model and then go to Import Export tab and then import. You can click on this particular folder and this is the model that you have exported previously. So you can click on this, say open, and then click on import. Okay, so while importing, it will ask you this whether this is the particular definition that I've given, the label name and the variable name. So everything looks right. So just click on OK. So you can see that the model that you created earlier can be imported easily into this particular parent system. So this simple suspension subsystem has been imported successfully into this model parent system. Okay, so this brings you to the end of this particular exercise demo. Thank you. Welcome back to the exercise on chapter 14. This exercise picks up from the previous exercise and adds to it. You will take the suspension system that you created in the previous chapter to create a rear suspension and add this to the vehicle body. Okay, let's get started. So file, open, model. So let's go to the chapter 14. Okay, so this is where you had stopped in the previous chapter. Okay, now you can click on model and import the vehicle body system. Okay, for this you need to select the parent model, go to the import option in the import export tab, and then click on the folder. Then you need to go to the same folder, chapter 14. So you have the vehicle body system already present in your chapter 14. Okay, select this and click on open. So once you do this, it gets loaded in this particular path, and now click on import and click on OK. So the vehicle body got imported into your parent system. Okay, so now just explore what this vehicle body system contains. So expand this. So it has the vehicle body, which is nothing but this cuboidal box, and then that's the box graphic, and it has several hard points. So we have the vehicle center front, and please make a note here that it is a point pair and not a single point, because we have the left and the right tab, and we also have vehicle center rear. Again, it's the point pair. Okay, now let's go on and add attachments to the suspension system. So select the suspension system in the project browser and click on add in the attachments tab. So here you'll create an attachment that will get a point from another system with the intention of basically getting it from the vehicle body. So here you can enter as wheel center point, and it should be a pair. Okay, and then here click on the variable name and then mention P_WC. So this just indicates point for the wheel center, and then click OK. So this creates an attachment object, which is somewhat like a variable that stores the data of the point and thus acts like a point. So once that is done, okay, here we did one mistake wherein the type was not selected to point. So you can go ahead and delete this particular attachment. Okay, go to the add option. Here, let's redo this. Wheel center point. Here it is P_WC, which indicates the wheel center point, and we need to change the type to point. So just scroll down, select point, and the type should be selected to pair, and now click on OK. So you can use the attachment to define the point location of the wheel center point in the system by using the variable name of the attachment, which was specified as arg_p_wc, okay, which is basically the attachment of the point wheel center. So what you need to do is double click on this. So now we need to resolve this attachment that you've created. So then in the model browser, you need to select, or you need to expand the vehicle body, expand the point, and select the wheel center front and click on OK. So this is the key part, wherein once the attachment has been created, you need to resolve the attachment. And the third step will be to use the attachment that you've created after resolving. Okay, so now this is resolved. So the attachment itself is basically just a variable that stores something in the model, which in this case is the point pair from the body system that will be used by the suspension system. So you can use the attachment by entering the attachment variable in any expression that I'll be showing in the next few steps. Okay, so now you need to select the wheel center. So you need to go here and select the wheel center front. Okay, so these are the locations for the wheel center front hard point. Okay, so now what you need to do is go to this points under simple suspension, expand this, click on wheel center. Okay, and then you need to go to the left tab. Okay, because the left tab has been selected as the master side and the right side will be following the left side. Okay, so it is parameterized with respect to the left tab, but the left tab is selected as the master side. So you need to go here, go to the X coordinate, go to the function builder. Okay, here you need to enter the expression. So for that, it's basically expanding this simple suspension, expand the attachments, expand the wheel center point, and this is the left point that you are going to parameterize. So expand the left point, and then this is the X value that you'll be defining. So click on this and say add. Okay, and then you can just click on evaluate it to see if there is any error in evaluating the expression. So there is no error in this particular expression. So then click on OK. So you can see that this tab gets highlighted in blue, which means that it is parameterized now. So the similar thing needs to be done for the Y and also the Z values. Instead of absolute values, we'll be parameterizing them. So clear this, go to the function builder, and you need to parameterize them with respect to the attachment that you've just created. So expand the attachments folder under suspension system, and then expand the wheel center point, and then click on or expand the left point and select its Y value and say add. Say OK. So now the Y value got parameterized. Same thing will be repeating for the Z value. So we'll come here, click on attachments, expand attachments, expand the wheel center point, expand the left point, and then select the Z value. Say add and OK. So the wheel center point in the suspension system will now get its location from the attachment, which is in this case from the vehicle body. So thus the vehicle body locates the suspension wheel center point. So you can also see in the display area, it is located in the right location now. Okay, so now let's create and use the attachment to define the vehicle body. Okay, now return to the simple suspension system and we will be creating another attachment for the vehicle body. Okay, so click on add and let's give the label name as vehicle body. Okay, and here it's a small letter B that represents body underscore vehicle body, and please remember that there should be no spaces or dashes when you're defining the variable name. Only underscores are allowed, and you need to change the type of this attachment to body and just select single radio button, so it's a single type, and then click on OK. So you've created the vehicle body attachment, and now the second step is to go ahead and resolve this attachment. So you need to click on body, go expand the vehicle body system, and then expand the bodies and select this vehicle body and click on OK. So now this attachment vehicle body has been resolved. Okay, so now you're supposed to do a few things. first thing is you need to come to the simple suspension system here, expand the graphics folder, okay, go to the damper top, and the damper top basically was connected between the ground body and the knuckle top. Now you'll be changing the ground body to the vehicle body attachment that you've just created. So expand simple suspension, expand attachments, and select vehicle body. Okay, so it gets highlighted in blue, which means that it gets parameterized. Now expand joints and select the knuckle to body joint, which is the second joint in the model browser. Here, the body 2 should be again replaced with the attachment vehicle body. Okay. Similarly, the same thing has to be done even for the spring damper system that's present. So click on the spring damper. So here, go to connectivity tab. Here, instead of body 1 being ground body, you need to replace it with the attachment vehicle body and click on OK. So once all these steps are done, you need to export the revised suspension system. Okay, so you can minimize this, click on the simple suspension in the project browser and go to the import export tab. Click on the export radio button and then click on this folder, and you can save it in chapter 14. So let's go here. So let's save it as simple suspension system revision 1. Okay, .mdl. So click on save, and then don't forget to click on quick export. Only then this suspension system gets exported. Okay, so now we need to import this suspension system again in order to create the rear suspension system. Okay, so click on the model and then click on import, go to the folder option and then click on the simple suspension system revision 1 that you just created. Click on open and then click on import. So once this is done, just change the label name to rear and the variable name also to rear, and then click on OK. So you can see that another system got imported as simple suspension rear. So you can just go here for the existing simple suspension system, right click and just rename it as simple suspension system front. Okay, so now you see the how useful it is to create systems, and because of the fact that they are reusable. Okay, so you can go to the simple suspension system rear. The only thing is you need to resolve the attachments. Okay, so click on this, go to the attachments tab. So here, instead of the point where being resolved to the wheel center front, you need to select this and go to the vehicle body, expand the points and select the wheel center rear. Okay, so when you do this, the same thing gets aligned to the rear wheel center points. Okay, so once you are done with this, the body, you can just make sure that it is resolved with respect to the vehicle body. Okay, so that's done. Now we should have a system that looks like this. The next thing is you need to add a fixed joint to keep the vehicle body grounded. So for this, let's click on the vehicle body, right click on this and then add a constraint entity and then click on joint. So give meaningful names for the joints. So here define it as vehicle body. So the variable name should also be changed. And then we need to define a fixed joint. Okay. Once that is done, you need to select the body 1, which will be the vehicle body. And the body 2 will be the ground body, which will be present in the parent system, which is model. And then the origin is the vehicle CG. So that is found under the vehicle body system. If you expand points, you have vehicle CG under this. Click on OK. So once this is done, go to the run panel and click on run. So you should see that your wheels should move in the similar manner that you saw in your previous animation. The animation that you saw in the last chapter. Okay. So let's go to animate. And if you click on animate, yes. So it is behaving in the same way. It's just that we copied the suspension system in the front to the rear and we have established attachments to the vehicle body. Okay. Now let's go back to the MotionView window. Now it's time to create data set for the suspension parameters. So for that, you need to right click on your model and go to add option and then click on the general MDL entity and then select the data set. So here, let's give meaningful names for the data set. So let's call it vehicle parameters. And you can also change the variable name. Vehicle parameters. And then click on OK. So once this is done, click on the data member tab. And then you can click on the add button and change the type to real. And the variable name can be changed to suspension stiffness. And the label name can also be changed to suspension spring stiffness. And then click on OK. Now repeat the same steps to create another data set. So click on add, change this to real. The variable name can be changed to suspension damping. So the label name can be changed to suspension shock damping. So once this is done, click on OK. And now we need to add an attachment to the suspension systems to use these dataset values. Okay. So in order to use these values in the dataset, you need to create an attachment in the suspension system to retrieve this entity information from another system. So for this, let's go back to the simple suspension system front. Click on the attachments tab and then click on add. So here, let's give the label name as suspension dataset. Okay, and the variable name must be changed accordingly. And the type should be selected as dataset. And then click on OK. So once you've created this attachment, you need to resolve the attachment. So for that, you need to select the dataset, double click on the dataset, expand the datasets in the model browser, and then click on vehicle parameters and click on OK. So now the attachment has been created and it has also been resolved. So now it's time to use this attachment. So now select the spring damper under the simple suspension system front, and you can go to its properties, and here you can now set a parametric relationship between the stiffness and the damping values. So you can go here, delete this absolute value, go to the function builder and parameterize it with respect to the attachments created. So you need to expand the simple suspension system front, expand the attachments folder, then expand the suspension data set. And the first thing is the suspension spring stiffness. So you need to expand this and then select the value and click on add and then select OK. So now it is highlighted in blue, which means that it is parameterized with respect to the dataset attachments that you created. Next, the same thing is done for the damping as well. So just delete this absolute value, go to the function builder, expand the simple suspension system front, expand the attachments, expand the suspension data set, and this time you'll be expanding the suspension shock damping. And click on the value and click on add. OK. So now both the stiffness as well as the damping have been parameterized with respect to the attachments that you create. Okay. So now once these are done, let's go back to the vehicle parameters in the project browser and then go to the properties tab. So here you can enter the value for the stiffness and the damping. Say we give 100 for the stiffness, or say 1000 for stiffness and 10 for damping. Okay, so once you define it in the data sets, now just to quickly verify, you can go to spring damper and you can see that these values are automatically updated because you parameterized them with respect to the data sets. Okay, now you can export the simple suspension system. So what you can do is click on the simple suspension system front. Okay, so before you export them, you can also go ahead and change the vehicle parameters as you like. So for example, you can change this value from 100 to 1000 to 100 or to 10. Okay, so let's leave it at 100 and keep the damping value as it is. Okay, so just so that we're sure that it's getting updated, click on the spring damper and you can see that the value for the stiffness has changed from 1000 to 100. Okay, so now let's go ahead and export this updated simple suspension system front with the data set that we've just created. Okay, go to the import export option, click on export, click on the folder, and we can rename it as simple suspension system with data sets. Okay, then click on save and then click on quick export. So once this is done, what you can do is you can delete the old simple suspension system rar, because we are going to re-import the simple suspension system front and rename it as rar and resolve the attachments. Okay, so what we need to do is go to model, go to import option, and then select the simple suspension system with data sets that we just exported. Go to Open, click on Import. Here, instead of simple suspension front, we'll be changing it to simple suspension rear. Similarly, in the variable name. And then click on OK. And you can see that this particular system has been imported. Now, the only thing that you need to do is go to Attachments, and in the point pair, you need to select the vehicle center rear. Sorry, the wheel center rear point. Okay, so you can see that now the model gets updated automatically. And if you just go ahead and expand this, if you click on the spring damper, you can see that these values are also updated automatically to 110. Okay, so this completes the modeling. Let's go ahead and run the model. Okay, let's go to animate. Okay, so we've completed the modeling and this analysis. So we've completed the modeling and the simulation for the chapter 40. Thank you. Welcome back to the last chapter in Multibody Dynamics course using Altair, HyperWorks, MotionView, MotionSolve. In this chapter, we will conclude the model building and simulation of the simple car model that we have been working with from the past two chapters. In this chapter, we will concentrate on the system initial conditions and couplers. The initial conditions tab on the system and assembly panel allows you to specify initial conditions for the systems. The checkbox to the left of each initial condition indicates whether the initial condition is applied or not. When the checkbox is on, the solver default is used. We have the following options to specify in the initial conditions panel. We can specify the translational velocity in the X, Y, and Z direction, and we can also specify the rotational velocity in the X, Y, and Z direction. Initial conditions can be applied to any system in the model. Please note that the initial conditions applied to a system are automatically applied to its subsystems. If the initial conditions of a subsystem are set separately, the settings override those of the system above it. Each initial setting that is overridden by a subsystem is listed on the right side of the parent system's initial conditions tab. Now let me switch to the graphical user interface where I can show you how to use the initial conditions option. So you can click on the model, and here you find the initial conditions tab. You just need to select the particular velocity that you need to apply and give its value. So if you have other subsystems under model, say system A, system B, system C, then all these subsystems get the initial conditions of the translational velocity in the X direction of 1000 mm per second. And if those subsystems have different initial conditions, then they'll be overridden by this particular value for the velocity in the X direction, because they'll be defined under the parent system model. Okay, now let's switch back to the presentation and move on to the last topic of this chapter, which is on couplers. A coupler defines the ratio of displacement of one joint with respect to another joint. The couplers panel allows you to define the properties of a coupler. Couplers can connect three types of joint combinations. revolute to revolute, revolute to translational, and translational to translational. Okay, so let me switch back to the graphical user interface where I can show you how to create couplers. So the first method is you can right click on this icon on the MotionView toolbar and then click on OK. This brings you to the coupler panel. This is one way of creating couplers. The second way is by right clicking on the model, going to add and then the constraint entity and then selecting coupler. Okay. And please note that you can input the number of joints to constraint. So if you select 2 as a number here, then there'll be 2 joints that will be displayed that you need to resolve. And if you change it to 3, then you get an additional joint that needs to be resolved. So if you go to the Properties tab in the Couplers panel, then you need to specify the displacement of one joint with respect to another. In case of 2 joints, and if you specify 3 joints, then you specify 2 of those ratios. Okay, so for example, if you select number of joints to constrain as 2, then if you go to property, the value you specify here will be the displacement of joint 1 with respect to joint 2. For example, for a ratio of 2, the second joint will be displaced 2 units for every 1 unit of displacement of the first joint. And if you select a 3 joint coupler, an additional displacement ratio text box is displayed. Okay. So now let's move on to the exercise demo of chapter 15. Welcome back to the exercise on chapter 15. The vehicle created in the previous exercises had 2 suspensions with a wheel and a vehicle body. In this exercise, you'll be adding a steering system and also a road on which you'll be running your vehicle. Okay, so go to File, Open, Model. You can also use the model from your previous exercise, or if you've not completed that and if you have some issues, you can also start with the simple car part 3 start.mdl file in chapter 15. So click on this. So this is exactly where we stopped in exercise 14. Okay, so now let's go ahead and import partially completed steering system. So go to the model, go to the import export tab, and then select the import radio button and select the steering system in complete.mdl file. Click on open and then click on import and click on OK. So the steering system gets imported into the graphical user interface. Now just try to explore what the system contains. So it contains a body called a steering wheel, and it has 3 graphics, which is a steering wheel, steering shaft, and an indicator. And it has a revolute joint between the vehicle body and the steering wheel, and it has a steering motion. Okay, so these are the entities which are present inside this steering system, and as you can see, it is incomplete. Okay, now you should also note that this steering system also has attachments. So the steering wheel center attachment, the vehicle body attachment, steering shaft attachment, and also the left cylindrical joint and the right cylindrical joint. So these are the joint attachments. Okay, so you will be basically using these 2 joint attachments to couple the motion of the steering to these joints in the front suspension system. So now right click on the steering system and go to the add option and then go to the constraint and click on couplers. So we need to create couplers to connect the steering to the front wheels. So let's start by giving meaningful names. So steering to left wheel, and please change the variable name to steer to left. So make sure that you give meaningful names. It doesn't have to be the same thing. Okay. Now you need to create another coupler. So just right click on this, say add coupler. So this is another way of adding couplers. So here, give another name, left wheel to the right wheel. And in the variable name, we can give left to right. Click on OK. So please note that these two couplers are placed under the steering system. Okay. So now we've just created the couplers, but still we have to resolve them. That is, we need to provide the joint 1 and joint 2. So select the first coupler, which is the steering to left wheel. Go to the connectivity tab. Let these number of joints to constraint be equal to 2. Now select joint 1 and then select or expand the steering system, expand the joints, and then click on the steering wheel joint and click on OK. For joint 2, expand the steering system, expand the attachments, and you need to select the left cylindrical joint, which was created as attachments in the steering system, and click on OK. And here make sure that the type is changed to rotational. Now go to the properties tab and enter the ratio of the displacement between the two joints. So we'll just specify it as -1 for now. And please note that this 1-to-1 ratio is basically exaggerated, basically to make us aware how the wheel is rotating, and we'll make it and we'll give it more realistic value once we run the initial simulation. Okay, now you have to follow the similar procedure even for the other coupler. So click on the left wheel to right wheel, go to the connectivity tab, but in this case for joint 1 you need to select from the attachments the left cylindrical joint, and for the joint 2 go expand the steering system, expand the attachment, and select the right cylindrical joint. And in this case both needs to be changed to rotational. Similarly, go to properties, and for now just give a value of -1, and we'll be changing to a more realistic value after our initial simulation results. Okay, so after these are done, you need to deactivate the steering motion of the front wheel. So go to the simple suspension system front, expand this, and then expand the motions, and then deactivate the steering motion. Okay. So now the steering motion from the simple suspension system front is deactivated. Now what you need to do is you have to go to the steering system and modify the steer motion. Okay, so click on this and go to properties. Here you need to change the type from linear to expression, and then start defining an expression in the expression builder. So go in between these two expressions and give an expression of 30 times sine 2 into pi into time. So time is nothing but the simulation time that we'll be specifying into dTOR. So this expression dTOR is basically to convert from degrees to radians. It is recognized by the MotionSolve solver. Okay, you can click on evaluate it to see if you have any errors in your expression and then click on OK. So that's created now. Now you can go ahead and run the simulation to test your model. So here we can keep the defaults as it is and click on run. So in this simulation, you should look for the steering wheel turning and the front wheels turning at the same time as the rate of the steering wheel. Okay, so let's go to the results. So can you see that? Let me just zoom in. So this is the indicator that we created. It's moving at the same pace as how the wheel is turning, the steering wheel is turning, right? But the wheels are, are taking a turn in a more exaggerated way. So we need to fine tune the coupling ratio. Okay, so now let's get back to this. So we need to update the coupler ratio. So go to the first coupler and then change the value to around -20. Okay, once this is done, again you can go ahead and run the model. Okay, you can animate the results. So now you can see that the movement is very less. I mean, the turning is not that as drastic that we saw earlier. There's a slight turning of the wheels. Okay. Now let's get back to the MotionView window. Now we need to run the model on a road. Okay, so we'll be importing a road that contains contacts to represent the tire forces along with the road geometry. So for that, go to the model, go to the import export tab, import radio button, and then select the road and the contact system. Click on open and then import. Click on OK. So now you can see that the road is created. Now let's explore what is present in the road subsystem. So it has 4 contacts. Okay, so the contact front left, the left for the left wheel, the contact to the right wheel, contact to the rear left, and the contact to the rear right. So these are the 4 contacts that have been established, and because we are using contacts here, please make sure that this road surface is not 2D. It has to be a 3D, otherwise you'll be getting an error when you're trying to establish contacts. Okay, so for the same sake, we have been using a cubical graphic as a geometry and not just it's not a thin sheet. Okay, it's not a 2D geometry basically, it's a 3D geometry. So that's the graphic that we're using, and these are the hard points for the rear contact points. Okay, so now the next steps will be to drive the vehicle along a straight path. with an initial velocity and along the road. So for that, let's minimize all the systems. Okay, now expand the simple suspension rear, and here you can go to steering. Okay, this one, because you don't need any steering for the rear wheels, so you can specify this expression to be 0, and that can be done by just multiplying it by 0. Okay, and please make sure that you do it for both the left as well as the right. It doesn't get updated automatically, so you need to do it separately for the left as well as for the right. And you'll also have to deactivate the right motion, as well as the wheel motion in both the rear as well as the front suspension system. So deactivate and deactivate. Okay. So you'll also have to deactivate the fixed joint on the vehicle body. So that's there in the vehicle body subsystem. So you have to go to joints and you need to deactivate this particular fixed joint. Otherwise, your vehicle won't move ahead. So let's deactivate this. Now let's specify an initial velocity for the vehicle. So click on the apparent model, go to the initial conditions tab. Okay. And here you need to specify the velocity in the X direction. Okay, you can give whatever value you want. Now this is, I've given it a minus 10,000 mm per second. That's because you can see the global coordinate axis, the X is pointing towards the right. So I want the vehicle to go in the opposite direction along the X axis. Okay, so that's the reason I've given a minus sign here. Okay, now it's time to run your model. So here you need to change the simulation type to static plus transient. Okay, so once that is done, just click on run. Okay, with all these contacts established, it's going to take a bit of a time for solving this analysis. So please give it some time. Yes, so solved. Now let's go to animate. Okay, now click on the animate button and you can see that your vehicle is moving forward. Okay, so let's bring it back. Let me zoom in. So can you see the vehicle is moving a little bit towards the left and a little bit towards the right? Okay, let me replay this animation for you. And you can see the steering wheel turning. Okay, that's done. And what do you expect when it comes to the end of this road? It should fall off, right? Because of the gravity. So let's continue to play the animation. So your vehicle falls off the road. Okay. So this completes all your chapters in the Multibody Dynamics course. Okay. So what you can do is, if you don't want your vehicle to fall off, you can either switch off the gravity, or you can come back to your motion view window, and here for the simulation time it can be just like 3 seconds. So now let me just run the simulation once again. Okay, animate. Let me expand the window. So then you can prevent your vehicle from falling down. Okay, you just have to reduce that simulation time. Okay. Okay, then that's the end of this particular chapter. Thank you.